In this video, we'll recognize the challenges associated with monolith applications in the cloud along with benefits afforded by microservices. When we follow monolithic application approach, architecture is usually self-contained. But yes, you'll have all the components tightly coupled, and that will create a challenge. The challenge would be related to execution. It means whenever we execute or compile monolithic software, all the components should be available or the build will fail. It means even if you are going with monolithic application approach, you need to ensure that business layer, data access layer are separated at runtime. Even though various different components are separated, but when you'll go at runtime, all of them will come together and run as one process. After understanding monolithic application, which means that it is self-contained and all components come together at runtime as a single process, let's go and identify critical components of monolithic application. And that will help us to understand monolithic application architecture. Three fundamental components are user interface, which takes responsibility of handling all the user interactions. Business logic layer, which is depicted in the current diagram in form of Business Service 1 and Business Service 2. These will contain implementation of business cases. In short, whenever request will come from user interface, it will invoke a business service, and that business service may interact with database layer, which is the third important layer that keeps all the data following structure of database. One business service can invoke other business service as well. But yes, user interface, business service 1, business service 2, which is currently displayed in form of a diagram on the screen, they all will be part of a single process. Now, what all are the critical problems that we face when we go and adopt monolithic architecture to build our applications? First fundamental problem is large code base. This is the scenario where the code line outnumbers the comment by a great margin. In the same code, you need to ensure that components are interconnected, and that will create lots of repetitive code base. Second problem is too many business modules. We will have multiple different business modules coupling with each other. And since one business module is dependent on other business module, you will have high module coupling. If you have high module coupling, that will create complex code base where you will have chance of code breaking due to fix required in some of the dependent modules or services. And finally, it also creates complexity in deployment because you may come across multiple different minor changes that would need entire system to be redeployed. Apart from this, there are other problems which you will face when you go with monolithic architecture in order to build your monolithic application. And that is, one module failure will affect the entire system. From perspective of scalability, monolithic architecture based applications are not highly scalable because this requires the entire system to scale up, not just those modules which are handling more load. And finally, when you plan to modernize your application from monolithic application, you will find issues. So it is difficult to modernize because again, you have to upgrade entire system. Now, who comes to rescue with all these problems? All these problems can be taken care if you adopt Microservices Approach. Microservices Approach provides you various different capabilities. Let's try to understand using a diagram which is currently displayed on the screen. At the center, we have microservice ecosystem. And surrounding that particular circle, we have multiple different features of microservice ecosystem. Let's start with the first feature. And first feature is it provides independent services, which also helps to increase the speed of experimentation because each and every service will be treated as a single unit. Another benefit that you get when you adopt microservices is it drives innovation through composing services. So you can have multiple different services where each service is independent. Still, you can go and you can create composition. Third benefit is from perspective of managing service. You have to start with approach of build small and independent services, and that facilitates in simplifying the development and management. Next benefit that we realize when we go and we adopt microservices is its capability of having an independent lifecycle for each and every service. Microservice provides you capability of utilizing diversified set of technologies. And finally, microservice ecosystem provides capability where you can have autonomous teams responsible for each service. Now let's go ahead and quickly compare monolith and microservices. And that we will do using a diagram which is currently displayed on the screen. On the left side of the diagram, we have monolith architecture, where we have user interface from where user will invoke request to consume a service. That request will be intercepted by business service 1 in our case, and it will delegate responsibility to execute certain methods of business service 2 and will also pick up data from database. Now this service can be simplified because all the components, which includes user interface, business service 1 and business service 2, are in a single system in case of monolith application, which provides you one single process. So if you want to scale business service 2, you need to scale entire architecture. That can be taken care by second approach, which is microservice. Diagram at the right indicates that you have user interface from where request will get invoked, and you have independent module business services which can be invoked by user interface. It's module business service 1, module business service 2. And interesting here is each service will have their own data repository where they will maintain data. It can be a database as well to provide data to the service. By adopting this architecture, you will be able to manage module business service 1 and module business service 2 independently. After comparing monolith and microservices, now let's go and identify some of the critical benefits of microservices. And first benefit is its capability to eliminate complexity. And it does it by decomposing application into independent set of manageable service. Second benefit is it enables each service to be developed independently, where your focus can be on a single service that you want to facilitate in that application. And third benefit is it reduces any potential barrier of adopting new technologies because developers are free to choose whatever technology makes sense for their service, and they are not bound to utilize only those technologies which were decided at the start of the project. Apart from that, we do have certain other benefits, out of which first is each microservice can be deployed independently on diversified infrastructure. And finally, each microservice can be independently scaled. After realizing benefits, let's go and conclude by evaluating feature of monolith and microservice on basis of various factors. We can see a table on the screen where first column is feature, second and third columns are monolith and microservices. Let's start comparing it on basis of first feature, that is technology stack. In case of monolith, you will be logged into original technology stack and framework that you selected. And all functions are developed with a single programming language because you will have only one runtime. But when you adopt microservice, each microservice can be developed using different technologies based on objective or the purpose of the developer as well as their preferences. You can also use multiple different languages for different services. From perspective of second feature, that is scalability, in case of monolith, functions cannot be scaled independently. You always need horizontal scaling, and that too entire application. In case of microservices, each microservice can be scaled independently depending on need. Now, what about change management feature? In case of monolith, entire application requires retesting even if you have made a small change. Apart from that, change and testing processes are complex and it takes lots of time. In short, it is time consuming. But when you go with microservices, You don't need to test all the microservices if you have made change in one. And this is the reason they can be tested quickly. They also provide independent release cadences. And finally, from perspective of deployment, monolith applications will have deployment files which will be large. If they're large, they will have slow startup time and also may incur downtime. When you are going and adopting monolith, you don't have any practical methodology to use agile DevOps methods and tools because you will be using softwares which cannot be tuned in DevOps. But when you go with microservices, they can be deployed independently, and since they can be deployed independently, you can use agile DevOps methods and tools effectively. So whenever you are planning your architecture, you need to have a comparison between monolith and microservices and decide whether you will adopt microservice approach or monolith approach. In this video, we'll quickly recall the path of transformation that we can adopt to transform monolith applications to microservices. First, we need to understand monolith architecture and its deployment mechanism. And that we will do using a diagram which is currently displayed on the screen. At the left of the diagram, we have monolith architecture, which provides three layers. First layer is user, who will interact with monolith application using browser. Browser will be using HTTP protocol in order to communicate with the service, and monolith code base will have all the services part of a single web application. Your web application will have a descriptor file which will describe what services can be mapped with what endpoint. All the services will be interacting to relational database for persistence management of business data. This is a simple monolith architecture. Now let's go ahead and understand from perspective of monolith deployment. And that we will do by discussing diagram which is there at the right hand side. Again, user, browser, internet are the components that will help us to create connectivity of the user with the deployed component. Then comes monolith code base, which need to be deployed in web server. In the current diagram, we can see services are deployed in two web servers, web server 1, web server X. You can have multiple different web servers which will host replicated services. Access will be provided using load balancer. So now whenever request comes, it will come to load balancer. Load balancer will be deciding which web server is healthy in order to serve to the current request. All the services will have access to the same database. So when you deploy, you need to ensure that you are able to identify how many web servers you are going to use, and entries of those web servers need to be made in load balancer configuration file so that load balancer can decide which web server is healthy to serve the current request. And that information is kept by load balancer by receiving health information of each and every web server, and then it adopts a particular algorithm to route the request. So this is how you will be planning your monolith deployment. Now what about microservice architecture? Assuming the previous example, we'll come up with microservice architecture where, as the diagram indicates, you'll have user, browser, internet. So accessibility will be through the same channel. But when it comes to deployment, you will have load balancer who will decide who need to serve the service. Load balancer will have references of the services, but each and every service will be independently deployed as the diagram indicates. Service 1 will have its own deployment architecture. Service 2 will have its own deployment architecture. So depending on need, you can decompose services of monolith, create independent services, and then deploy it on microservice compliant application servers. Now let's try to understand deployment of microservices. As the diagram indicates, you'll have user, browser, internet, and now you are using load balancer, which is deployed in gateway. Gateway will have references of all your services, and each service will be independently deployed in microservice environment. Now, as the diagram depicts, we can have a load balancer per service. in order to ensure that if one service is busy serving some other request, it can create a new service instance and that service instance can serve the user. This can be done in all the services that you have created. So by adopting load balancer compliant architecture of microservices, you'll be able to scale and you'll be able to have proper architecture in place in order to manage load on each and every service. Now let's go ahead and understand how do we transform from monolith to microservices. And that we will do using a diagram which is currently displayed on the screen. The diagram indicates 6 different phases. In each phase, you need to do certain activities for transformation. Let's start with phase 1, where your objective is to decouple monolith. And after decoupling monolith, you need to add service layer, which will be a facade. You will add service mediation layer as well in order to mediate the service so that protocol mediation and request response mediation can be implemented. Then comes phase 2, where you start developing local microservices, for which you need to identify microservices, you need to develop interface definitions, and finally develop the microservices itself. Now your microservices are ready. You'll move to phase 3, where you have to implement local microservices with objective of migrating the data, testing and conducting parallel runs, and also using swing channels to microservices. Now you have implemented local microservices as well. Phase 4 is to go and deploy microservices to the cloud so that it can be accessed by various diversified clients. And to do that, you need to implement API gateway provided by cloud provider and then deploy microservices in the cloud. Now, post-deployment, you need to move to phase 5, where you need to implement microservices in the cloud. So now you have definition ready in cloud, you have microservice deployed in cloud, you need to migrate data as well to cloud, run parallel in cloud, and swing channels to API gateway instead of microservices that you did in phase 3 in case of implementing local microservices. And finally, phase 6 is decommission monolith, means unplug monolith, divert all the service calls to the recent microservices that you have implemented. This is how you will be able to transform from monolith to microservices. Finally, we'll conclude using a scenario that is end-to-end transformation scenario, where we are going to discuss about various different components which are essentially needed in order to complete transformation. The diagram which is currently displayed on the screen specifies about channels. Those channels of interaction that can be invoked by clients need to be mapped to the service, and that role is played by service mediation, which is deployed in runtime and is controlled by runtime controller. Once your service mediation layer is up, it will transform the request compliant to microservices. And that is what is displayed in the diagram. You have microservice layer, you have services layer, and you have monolith. So from monolith, you are transforming to services layer using SOA, that is service oriented architecture. And then finally, you are adopting microservices. Accessibility to microservices will be configured in cloud using API gateway. Now let's try to understand the process that we follow. First is migrate functions and data to microservices. Second is swing channels to microservices. Third is migrate microservices to cloud, and finally swing channel to cloud. And that we will achieve by using F, which is the function we can see in the diagram in monolith box. Then you have A in the service layer, which is adapter, and finally you have M, which indicates that it is microservice. So by using the current architecture which is being displayed on the diagram, you'll be able to quickly migrate your microservices, deploy it in cloud, make it accessible using API gateway. This is how you can adopt transformation from monolith application to microservices. In this video, we'll recall the concept and benefits of container orchestration. Before we start talking about container orchestration, let's try to understand what is container. Container is a standard unit of software that will package not only code but all its dependencies so that applications can quickly and reliably run on your computing environment. Transition of container which is packaged from one environment to other environment is also simplified because container comes with feature of being lightweight, standalone, and has capability of building executable package of software that will include everything that is needed to run application, which includes code, runtime, system tools, system libraries, as well as settings. Now let's try to understand architecture of container using a diagram. At the lowest level, which is indicated in the diagram at the extreme left, you will have infrastructure. On top of infrastructure, you will have host operating system. And host operating system will have container engine installed on it. Once you have installed container engine, it will facilitate with capability of creating containerized applications packaged with all the components that are required in order to build runtime environment for execution of application. Now, after understanding container architecture, let's go and understand what is container orchestration. Container orchestration can be considered as an automatic process of managing or scheduling individual container tasks. Primary focus of container orchestration is to manage the life cycle of containers as well as facilitates in maintaining dynamic environments. You can use container to manage clusters with multiple nodes in order to deploy and manage complex containerized applications. And finally, container orchestration can be employed to manage simple clusters as well as individual containers. Now let's take up a scenario of container orchestration, and that we will do using a diagram which is currently displayed on the screen. Now, container orchestration typically works with orchestration tools. Kubernetes is one of them. As the diagram indicates, you will have container orchestration software which will provide you capability to automate various different activities that includes configurations, provisioning, availability, scalability, resource allocation, load balancing, as well as health check. These all will be automated using configuration file, and finally that configuration file will be executed that will facilitate you with an application environment with multiple different containers. We need to also understand that container orchestration tools can work in any environment that has capability of supporting container, and that is done by installing container runtime. Now, what all are the critical benefits that we will realize when we go and when we adopt container orchestration mechanism? Let's start with first one, that is, it provides improved application development. We all know that with container application development, testing, and production can be accelerated. Whenever new versions comes with new features, they can be set up quickly in production and you can roll back whenever you need to. So we can say that containers are ideal choice for agile environments. Second benefit is it decreases the resource requirement. Now, since containers do not need or include operating system image, they are considered more lightweight as compared to virtualized environments. Apart from that, they also simplify the way you operate and maintain container machines. Now, container orchestration tools will help us to do resource management, where they will take responsibility of facilitating resource capacity as needed. Third, container orchestration facilitates in providing microservice architectures. Because traditional applications are mostly monolithic in nature, they are tightly coupled, so you will not have isolated components. Whereas microservices are characterized by loose coupling among application components where each service can be scaled or modified separately. And containers comes into play when you are talking about specific microservices. Container orchestration plays essential role in order to allow containerized services to act better in conjunction with other services. Fourth benefit is related to the simplified installation and deployment. Now you'll find that everything related to the application is present within the container itself. So application installation is simplified. Now whenever you need to scale up because of demand or traffic, container orchestration will facilitate to easily set up new required container instances. Fifth benefit that we realize is better productivity and improved security. Now, containers are already being used because they provide rapid testing, deployment, patching, as well as scaling. Role of container orchestration here is to make these processes faster. Now, with application and their processes being isolated in containers, application security can also be enhanced. We need to know that container orchestration tool also ensures that the only specific resources are shared among users. And finally, container orchestration facilitates by providing capability of dynamic allocation of resources and spreading of workload across all the available containers. This is how you will be able to realize benefit of container orchestration by setting up right architecture, ensuring that you have selected right container runtime and container orchestration tool. In this video, we'll describe the different container orchestration options and container orchestration deployment options that we can adopt to manage containerized deployments. Before we go and discuss about container orchestration options, let's try to understand container orchestration architecture, and that we will do using a diagram which is currently displayed on the screen. There are four essential elements that we need to focus on. Let's start from the right. We have containerized applications, which are typical applications packaged in a standardized manner to have runtime environment as well. Containerized application will need container engine because it is container engine that manages all the containers. Now comes orchestration, which is facilitated by orchestrator, and orchestration is all about scheduling, communication, service discovery, load balancing, enabling self-healing feature, providing rolling updates. Apart from that, pipeline management and federation. All these roles are of orchestration, which will be facilitated by orchestrator. And finally, you have container management system, which is a comprehensive tool that helps you to have better security controls, apply image security scanning, provides you a centralized management tool that helps you to manage application lifecycle as well as enterprise component management. All these components put together will help you to create orchestration architecture. Now, you do have certain options of container orchestration which are available. First is Docker Swarm, which is Docker's own tool for cluster management and orchestration. Second is Marathon, which is a production-grade open source framework built for container management and orchestration. It is internally based on Apache Mesos, and its intention is to work with applications or services that will run over long period of time. Third is Kubernetes, which was designed by Google, provided as an open source, typically manages Docker containers. Kubernetes also supports various other types of containers, and best part of Kubernetes is it uses a single master server that manages multiple nodes using simplified command line interfaces. And finally, you have Amazon ECS. Amazon provides ECS as a service, and it has capability of only running on instances of Amazon Web Services. So far, there is no support for any external infrastructure. Apart from that, there are two others. One is Azure Container Service, which is Microsoft's container orchestration solution, typically built for Azure Cloud Computing Platform. And you have Nomad, which is again a free and open source solution built by HashiCorp, which facilitates cluster management and scheduling. Now let's try to understand container architecture in the cloud. And that we will do using a diagram which is currently displayed on the screen. Let's start from the right, where we have no orchestration, which means that you are not using orchestration capability. Your cloud infrastructure can host container runtime. Second is custom orchestrator, where you are selecting your own orchestrator, which facilitates to manage orchestration on cloud infrastructure and provides with feature of container orchestration. Container orchestration will manage all the container runtime. Let's move to the third one, where we have container as a service, which manages cloud infrastructure and provides container orchestration capability as well. So now you are moving from custom orchestrator to container as a service, which is facilitated by specific cloud providers. And finally, platform as a service, which manages cloud infrastructure, utilizes container orchestration capabilities. Apart from that, it also manages all the application platform, which will be packaged and will run in container runtime. So these are different architectures of container in the cloud. Finally, let's go ahead and discuss different container orchestration deployment options. First is self-managed, where typical use cases are when you use on-premises container orchestration, or you go with infrastructure as a service hosted container orchestration, or you go with hosted service providers. But in all these cases, it will be self-managed. Second is provider managed, where you get container orchestration in form of service that will be applied on container instances. So depending on your choice, whether you go with self-managed, where you need to facilitate in configuring orchestration, or you go with provider managed, where provider will take responsibility of providing you service to manage your container orchestration. So these are two different container orchestration deployment options. Now let's try to understand it using a diagram which is currently displayed on the screen. We can say self-managed and provider managed. Provider managed comes with container as a service. Self-managed can be in on-premises container orchestration, which facilitates in orchestration of applications, all the worker nodes, control plane, as well as cluster infrastructure. When you go with infrastructure as a service hosted container orchestration, which is self-managed, you don't need to worry about cluster infrastructure because it will be managed by infrastructure provider. You need to manage control plane, worker nodes, and applications. Third option for self-managed is hosted services provider, where you need to not worry about cluster infrastructure and worker nodes, but you have to configure control plane or master and applications. Now let's talk about provider managed, where in case of container orchestration service, you need to just take care of applications and worker nodes. When you go with container instances, you will be responsible for only applications because provider provides you container as a service. These two are different ways in order to implement capability of container orchestration deployments. This is how, after going through different container orchestration option and deployment options, you need to decide what container orchestration option and what container orchestration deployment type fits your need. In this video, we'll recognize the role of Cloud Native Computing Foundation and evolution of Kubernetes. Let's try to understand what role is played by CNCF. CNCF provides Linux Foundation projects with objective of managing container technologies. Primary role of CNCF is to incubate and graduate projects to mature process level. It also helps to build sustainable ecosystem for cloud native. Another role of cloud native computing foundation is to provide map that reflects the full extent of cloud-native solutions. And finally, it also outlines open source cloud-native technologies that are hosted by the foundation, can be used by multiple providers who supports cloud-native applications. Now, cloud native suggests certain principles that need to be followed in order to derive the right architecture. And first principle is it is designed for automation. Automation is one of the key in order to ensure that you are able to change configuration management from manual to automated through scripts. And this is the reason why cloud native adopt principle that is focused on design for automation. State management is critical. Cloud native principle includes principles that helps to manage state of applications effectively. It is considered as one of the most critical and difficult tasks, specifically when you are building business-driven applications where you need to manage states. Third, cloud native principle prefers use of managed services. And this is the reason why cloud becomes one of the essential components, because they come up with various different managed services which are ready to use. Apart from this, there are two other principles which are adopted by cloud native. And first is it adopts defense in depth. In short, it has moved from perimeter security to defense in depth. And finally, cloud native principle includes all the tasks that should provide continuous refinement, simplification, and improvement of existing system architectures depending on the required changes. Now let's discuss evolution of Kubernetes, which started in 2000 when you had non-virtualized hardware. In 2001, virtualization came up. VMware was the major provider, and in 2006, AWS came up with infrastructure as a service. In 2009, there were multiple providers of platform as a service. In 2010, OpenStack came up with commitment of providing open source infrastructure as a service, which was followed by open source platform as a service in 2011. Then came 2013, where containers were introduced and Docker became one of the prominent providers. Finally, in 2015, Cloud Native concluded its research for container management and orchestration by using a project called Kubernetes, and that's how Kubernetes evolved. Now, another interesting evolution of Kubernetes can be understood from perspective of complexity and deriving as code system. And that we will understand using a diagram which is currently displayed on the screen. Generation 1 was all about single cloud, where infrastructure as code was introduced. As the diagram indicates, AWS came up with cloud formation template. Using those templates, we can write AWS cloud formation, which provides APIs in order to automate infrastructure on AWS. Then came generation 2, where multi-cloud infrastructure as code was needed, because organizations wanted to decouple their services from one single cloud provider and move to multi-cloud providers. AWS, GCP, and Azure, as diagram indicates, provided their own set of APIs using which Terraform automated infrastructure as code on multi-cloud. Terraform files are typically with .tf extension. Finally, generation 3 was all about hybrid multi-cloud platform as code, where now private cloud can also be orchestrated along with public cloud providers. As the diagram indicates, now we have AWS, GCP, Azure, as well as your own private cloud. All cloud providers along with private cloud providers provided API which can be utilized by Kubernetes in order to create container as a service, and those APIs can be invoked by configuring Kubernetes YAML file. Kubernetes YAML file finally will get executed and it will provision and manage containers on diversified hybrid multi-cloud platforms. So this is how Kubernetes evolved, where major role was played by Cloud Native Computing Foundation to provide an open source container orchestration tool like Kubernetes. In this video, we'll describe the key features and components of Kubernetes. Let's quickly have a recap of Kubernetes features. First feature is it's an open source and platform independent container orchestrator. It has capability to group containers in a single logical unit and apply various different functionalities on them together. It facilitates and provides architecture which is easy to manage and also facilitates in simplified service discovery. Kubernetes can be used with enabled self-healing feature. And finally, Kubernetes provides scaling which can be horizontal as well as vertical. Apart from this, Kubernetes also provides features where it enables serverless with server to manage resources effectively. You can also configure your containers using Kubernetes to optimize resource usage. And finally, Kubernetes is one of the prominent choice for multi-cloud deployments. Now, what all are the essential components of Kubernetes? There are three components of Kubernetes. First is the master node, whose responsibility is to manage the Kubernetes cluster, and it is also the entry point for all administrative tasks. As the diagram indicates, user will communicate to master node, they will submit their request, and it is master node who will take responsibility of scheduling, controlling, or completing the task on various workers. Second component is worker node, which is a machine that runs the applications using pods, and it is controlled by master. And third is the interface. Cube Ctl is one of the prominent command line interface that can be used in order to manage various different API objects of Kubernetes. Now we can have a look over diagram which is currently displayed on the screen, where user makes the request. Master node uses scheduler to schedule the task, which is intercepted by API server. It can pick up related environmental values from key value store, and it can apply it on worker nodes. In the current diagram, we have three worker nodes: worker node A, worker node B, worker node C. Kubernetes master node will have various controllers in order to control those tasks. Now let's try to understand internal components of master node. First component is API server, used to expose Kubernetes API. It is the front end for Kubernetes control plane. And this is the reason in the diagram currently present on the screen, we can see that when a user places request, it goes to API server, and from API server, it is distributed to various other components of control plane. Second component that we can see in the diagram as well is scheduler, which invokes APIs using API server. Primary objective of scheduler is to watch for newly created pods with no assigned nodes and then select a node to run on. Third component is the controller manager, as it is indicated in the diagram in control plane box. Controller manager also sends requests to API server. Primary objective of controller manager is to run controller processes, and it does it for each controller, where each controller is treated as a separate process. But in order to reduce complexity, controller manager will compile into a single binary and will run in a single process. And fourth essential component is etcd, which is consistent and highly available key value store used by Kubernetes as backing store for all cluster data. Now, in the diagram at the right, we can see kube proxy, IP table, kubelet, Docker, and Docker Hub. These are various different elements which are used to select the image, create container, facilitate it with pods, and make the service available and accessible using kube proxy. Kube's proxy and kubelet will also communicate to API server. So API server is the central element of master node. Now what about worker node? Worker node comes with various different components. First component is kubelet, which is treated as an agent that runs on each node in the cluster, and its objective is to ensure that containers are running in pod. Now, kubelet takes a set of pod specs that are provided through various mechanisms and ensures that containers described in specs are running and they are healthy. Second component which will be there on worker node is container runtime interface, which is a software primarily responsible for running containers. There are multiple different container runtime interfaces which are supported by Kubernetes. And third element is the Kube proxy, which is a network proxy that runs on each node in the cluster, implementing part of Kubernetes Service concept. Primary objective of Kube proxy is to maintain network rules on the nodes. Now let's go and see the diagram. As per the diagram, we have gRPC client who will make request to gRPC server. It will be using kubelet CRI, that is Container Runtime Interface shim, to negotiate with container runtime and facilitate containers in running state. Apart from master and worker, Kubernetes also supports various different add-ons, and each add-on will have some objective. Let's go and discuss some of the add-ons. First add-on is DNS. All Kubernetes cluster must have cluster DNS. Cluster DNS is a DNS server which is present in your Kubernetes environment and serves DNS records for Kubernetes services. It is typically started by Kubernetes automatically, including this DNS server in DNS searches. Second add-on that we can use is container resource monitoring. Objective is to provide time series metrics about containers in centralized database and also provide UI for browsing the data. Then comes Web UI, which is a user interface that helps to manage and troubleshoot applications which are running on the cluster. And finally, you have cluster level logging, which is a mechanism primarily responsible to save container logs to central log storage with search and browse interfaces. These are the critical components that you may use when you are setting up a Kubernetes cluster. In this video, we'll identify the pros and cons of different recommended installation and configuration options for Kubernetes in order to select the right options. There are three typical ways in which you can install Kubernetes. First is manual, second is using installer, and third is using hosted Kubernetes. Now let's go ahead and compare these three different install options. And that we will do using a table which is currently displayed on the screen. When it comes to manual, we can manually set up and configure everything. In short, you will have better control, but it is prone to human errors, where debugging may take lots of time. Second is installer, where you will be using various different tools depending on your operating system and the environment to install Kubernetes. In this particular case, you can leverage templates and automation tools as well, but you have high dependency on tools. In case of hosted, no install is needed. They are provisioned by your hosting environments, typically provided by cloud providers. They are pre-configured, but you will face challenge while customization. In short, it is complex from perspective of customization. Now, assume that we are planning to install Kubernetes. Now, what all are the considerations that we need to keep in mind before installing? First consideration is have sufficient compute instances in place. Ensure that you have right number of CPUs allocated to those instances. Have sufficient storage volumes depending on capacity needed. Have some in-use IP addresses ready. And also configure packet filtering rule sets. So these are few considerations that you need to consider. You need to take help of your infrastructure administrators in order to help you in getting all these resources in optimum size. Apart from these, which are required for basic installation, we do need to consider number of load balancers, network subnets, and log streams. These are few considerations that you need to keep in mind before you plan installation of Kubernetes cluster. Now let's go ahead and try to understand some of the best practices that you need to follow when you configure Kubernetes. And first is always use latest API version because Kubernetes may not support older versions. You need to also prefer using YAML rather than JSON. Avoid using default values. Try to create objects and bind those objects with your resources. Fourth, prefer using version control system so that you are able to store your configuration file and reuse it whenever you need. Fifth best practice is you need to configure group related objects in a single file. It helps you to manage it in better way. And finally, always precisely specify object description in annotations so that other team members can understand. So before you start installing, you need to identify different recommendations of installation, select the right approach, and follow best practices for Kubernetes configuration. In this video, we'll list the key criteria that need to be considered while evaluating Kubernetes solutions for enterprise workloads. Before we start, let's try to understand what is workload. Primary objective of Kubernetes is to ensure that it provides orchestration capability in order to dynamically manage workload. Let's go ahead and define what is workload in Kubernetes. Any application that runs on container is treated as workload in Kubernetes. Kubernetes provides architecture which includes pods, which facilitates workload to run inside a collection or a set of pods in order to facilitate scalability. Kubernetes provides various different types of workload resources that helps to manage set of pods. Now, what all are those resources? Those resources can be grouped into multiple different categories. First is deployment, which represents a set of multiple identical pods where they will not have unique identities. Deployment can run multiple different replicas of your application, and it also facilitates in automatically replacing any instance that fails or becomes unresponsive. Who manages deployment? Kubernetes provides Kubernetes Deployment Controller, which takes care of deployment workload resource. Second is the Replica Set, which ensures that a specified number of pod replicas are always running at a given point of time. But yes, deployment is considered as higher level concept that will take responsibility of managing replica sets and provides all the declarative updates to pods along with other useful features. Third is stateful set, which represents a set of pods with unique, persistent identities as well as stable host name. It stores state information and other data for any given stateful pod, and it is maintained in persistent disk storage that are bound or associated with stateful set. Fourth, an interesting workload resource is daemon set, which ensures that nodes runs a copy of pods. Now, as soon as nodes are added to the cluster, automatically pods are added to them. And as you remove those nodes from the cluster, those pods will be garbage collected. It means whenever we delete a daemon set, it will clean up the pods that it created. And finally, we have job and cron job that are useful to create periodic and recursive tasks. You can use job and cron job for tasks like running backups or sending mails. Now let's try to understand deployment using a diagram which is currently displayed on the screen. Assume that you have configured and created a deployment, and while configuring you have specified 3 replica sets. It will create those replica sets which will be utilized by pods, and those pods will be available on specific nodes. In short, deployments are used to manage stateless services that runs on cluster. Deployment controller takes responsibility of managing all the changes from actual state to desired state. And whenever you create new deployment, it creates new replica sets. Now, what all are the essential elements of deployment? They are replicas, templates, selector, and strategy that you want for deployment. Now, when you configure deployment in configuration files, you'll be using certain fields. Now, let's try to list those fields. First is name, that provides a name to your deployment. Second is ready, which displays how many replicas of applications are available to the users. It follows typical pattern of ready and desired. Third is up to date, which displays the number of replicas that has been updated. Fourth is available. It displays how many replicas of applications are available to your users. And final field that you get that describes deployment state is its age, that displays the amount of time that application has been running. Now we'll discuss Replica Set using a diagram which is currently displayed on the screen. Replica Set will hold the deployment by internally creating container which will be bound to ports. As the diagram displays, you will have Replica Set which will have multiple containers on which you will have your application deployed, which will be bound to specific ports like port A and port B. Now let's go and discuss certain features of Replica Set. First feature is it ensures stable set of replica pods are always available and running at any given time. It is defined using fields like selector, number of replicas, and pod template that contains details about container and the image that it will use in order to build the containers. Apart from that, Replica Set will use metadata.owner_reference, and this particular field is used to link Replica Set to its pods. And finally, Kubernetes always recommends utilizing Replica Set through deployments, not directly. Third important resource is stateful set. Let's try to understand stateful set using a diagram which is currently displayed on the screen. The diagram assumes that you have created a headless service which has invoked pods, and those pods are using stateful set. Stateful set is implemented using persistent volume, which will be claimed by pod. As the diagram indicates that we have two pods, pod A and pod B. They are attached to persistent volume A, persistent volume B. In short, they will claim the volume from persistent volume A and persistent volume B, which are present on node A and node B respectively. Now let's try to understand certain features of stateful set. First feature is it is used to manage stateful applications where states of users are retained. It manages deploying as well as scaling of a set of pods. Third, it always guarantees ordering and uniqueness because it has to manage state. Fourth, it manages pods which are based on identical container specification that you have specified in your configuration files. And in order to manage state, it uses sticky identity, which is applied for each pod. And finally, it is prominently adopted when the need is to utilize storage volumes to store session-specific data. Now let's talk about daemon set. And we'll understand daemon set using a diagram which is currently displayed on the screen. You'll be creating daemon set by creating configuration, where you have to specify essential fields in order to give name to the daemon set. The current diagram indicates that when you created daemon set, it invoked daemon set pods on various different nodes of Kubernetes. Kubernetes node 1, Kubernetes node 2. Now each Kubernetes node, that is node 1 and node 2, are having daemon set pods which will be managed using principle of daemon set. Now why do we use daemon set? We use daemon set in order to ensure that all or few nodes runs a copy of a pod. It is useful specifically when you want to manage groups of replicated pods, but we need to remember that daemon set adheres to one pod per node model. Apart from that, daemon set comes with feature of automatically adding pods to new nodes. You can prefer daemon set in scenarios where you want to deploy background tasks. In short, they are useful for deploying ongoing background tasks. And finally, let's discuss about job and cron job. Let's try to understand the diagram which is currently present on the screen. Jobs can run to completion, or you can have scheduled jobs, which are cron jobs. If we want to differentiate between jobs and cron jobs, we need to understand that jobs creates one or more pods. It ensures a specific number of pods are always successfully terminated, whereas cron jobs runs a job periodically on a given schedule. And you can prefer cron job specifically for those tasks which are periodic and recurring. So after evaluating various different workload resources, we'll be able to understand what workload resource can be used in order to derive right Kubernetes solution for workload management. In this video, we'll demonstrate how to install all-in-one Kubernetes using containers to run the Kubernetes components as Docker containers on a single host. There are multiple different operating systems on which you would like to install all-in-one Kubernetes to set up your development and testing environment. We are going to try installing all-in-one Kubernetes which uses Docker on Windows. To do that, you need to first ensure that you have installed Docker Desktop. Once you have installed Docker Desktop, you need to launch it. When you will launch, you will get configuration options where you'll be facilitated with various different settings that you can manage. One of the options under setting in the left of your current Docker window will be Kubernetes. It means that Docker Desktop includes a standalone Kubernetes server that runs on your host, and you can use it to test and deploy all your container workloads on Kubernetes. Let's go ahead and set up Kubernetes on Docker. To do that, you need to select Kubernetes, which is present in the left navigation pane of your current Docker window. After selecting Kubernetes, you will get certain options where first option is to select Enable Kubernetes. When you select Enable Kubernetes checkbox, it starts a Kubernetes single node cluster whenever you'll start your Docker Desktop, and it will start it as a Docker container. Now you can also decide whether you want Kubernetes to be your default orchestrator. If yes, you need to select the second checkbox which is just below Enable Kubernetes called Deploy Docker Stacks to Kubernetes by default. So we have selected the checkbox in order to ensure that Kubernetes becomes default orchestrator. Now by default, you'll find that Kubernetes containers are hidden from commands like Docker Service ls because manual management of those containers are not supported. But yes, if you still like to see them visible, you need to select the third option, which is Show System Containers. But obviously, most of the users will not need this option for development and testing purpose. Now let's go at the bottom right of the current window and click on Apply and Restart button. Once you'll click on Apply and Restart button, it will prompt a dialog indicating that installation takes a few minutes and requires an internet connection. Ensure that you have internet connection and click on Install button, which is there at the bottom right of the current dialog. And you'll find that starts installation process. You need to wait for some time till installation is completed. Finally, it starts Kubernetes cluster, and you can see that in the status bar of the current Docker window. Internally, it might have installed kubectl.ext command. Let's go and launch command prompt. After launching command prompt, you can write kubectl and press enter. You'll find that it displays all the commands that can be used to interact with your Kubernetes service. Let's go and write kubectl space followed by version and press enter. And you'll find that it displays client version as well as server version. This is how you'll be able to install all-in-one Kubernetes using containers to run the Kubernetes components as Docker containers on a single host. In this video, we'll create and manage deployments that runs applications on Kubernetes cluster using kubectl command. Now let's go ahead and first deploy our application on Kubernetes, and for that we'll be using kubectl create deployment command. While using the command, we need to ensure that we are specifying two parameters. First is the deployment name, and second is the app image location. Ensure that you have included the full repository URL for image which is hosted outside Docker Hub. But in case if it is there on Docker Hub, you can specify Docker Hub path. In order to deploy our app, we'll be using kubectl For that, we need to launch command prompt where we have Cube Ctl installed in order to communicate with Cube Kubernetes cluster. Let's go ahead and write Cube Ctl. Write create followed by a space. We'll specify the action, that is deployment, followed by a space. We have to give name to our deployment. Let's specify deploy1. After specifying name of the deployment as deploy1, we'll give a space followed by dash dash followed by image, which is the flag that we are using in order to specify location of the image. We'll use equal to followed by the path of the image. In our case, it is gcr.io/google-samples/hello-app:2.0. After specifying the command, we'll press enter. Once we'll press enter, we'll get a message indicating that deployment is created. In short, your first application is deployed. Internally, it has done few tasks. First task is it has searched for a suitable node where an instance of application can be executed. In our case, we have only one node, so it might have deployed on that particular node itself. Apart from searching for a suitable node, it might have also scheduled the application to run on that particular node. And finally, it might have configured the cluster to reschedule the instance on a new node whenever it is needed. Now let's go ahead and list our deployments. To list deployment, we'll be using kubectl command, followed by a space, followed by get, followed by space, followed by deployments. After writing the command, we'll press enter. Once you'll press enter, you'll find that the application that you have deployed is listed in your current deployments. Now, sometimes you would also like to delete the deployment. In order to delete deployment, you can either go and delete one specific deployment of your choice, or you can also use selectors in order to ensure that you are able to delete large number of deployment at the same time. Since we have only one deployment, let's go ahead and see how we can delete the current deployment that we have made using kubectl create deployment command. To delete, we'll be using kubectl at the command prompt, followed by a space. We'll specify delete space. We need to ensure that we are using resource what we are going to delete. We are going to delete deployment, so we'll specify deployments followed by a slash and then name of the resource. Name of the resource is deploy1. After writing deploy1, which is name of the resource that we want to delete, which is of type deployments, we'll press enter. Once you'll press enter, you'll find that it has deleted the deployments. This is how you'll be able to deploy your application, picking it up from a particular repository and delete it. In this video, we'll recognize the concept of pods in Kubernetes along with the approaches used by pods to manage multiple containers. Now first, let's try to understand what are pods. Pods are smallest deployable units for Kubernetes cluster. We can also say that pods run in a shared context. Pod is also considered as group of one or more containers that will share storage as well as network resources. And finally, we can say that it contains one or more application containers which are tightly coupled. So after understanding pod, let's try to understand how pods are used in Kubernetes cluster. Let's go through the diagram which is currently displayed on the screen. Master will have API server, controller and scheduler. There will be request to create API resource. Whenever there will be request, master node will send information to worker node to create pods. As we can see in the diagram, we are using Docker engine on two different nodes, worker node A and worker node N. Each worker node is creating pod, and inside pod we have containers which are running. Containers will be created using images that will bundle your application components. Now, after understanding structure of pod within Kubernetes cluster, let's try to understand how do we use pods in Kubernetes cluster. There are two ways. First, pods that runs in a single container, which means one container per pod. This is one of the models that can be followed when you are using Kubernetes cluster. In this particular case, pod is wrapped around a single container. And Kubernetes manages pods rather than managing containers directly. Second approach is to use pods that run multiple containers that need to work together. In this particular approach, you will have a pod which encapsulates an application composed up of multiple co-located containers. And these containers are tightly coupled and need to share the resources. And these co-located containers forms a single cohesive unit of service. So these are two different ways in which you can use pods in Kubernetes cluster. Now we'll go and we'll focus on multi-container pod design patterns. And there are three design patterns. We'll try to understand these three design patterns using diagram. First diagram is of sidecar. Sidecar pattern typically contains a main application, which can be your web application. Apart from that, it will have a helper container whose responsibility will be to manage your application. But yes, this particular container would not be part of application itself. As the diagram indicates, you have pod, which has a shared file system. Now you have app container, where you have your web server, and whenever there is an activity, web server writes data to log file. You are using sidecar that takes responsibility of sending log files to bucket, and it is not part of your app container. Second is adapter. Adapter pattern is used to standardize and normalize application output or monitoring data specifically for aggregation. As the diagram indicates, you'll have app container that writes complex monitoring output, and you have adapter that serves app container by simplifying monitoring output for service, and it can utilize capabilities of external monitoring services. And this is how adapter manages your containers inside the pod. And third is ambassador, where in this particular pattern there is a way to connect containers with the outside world. An ambassador container is essentially a proxy that allows other containers to connect to a port on localhost, while you will have a specific ambassador container that can proxy these connections to external environments depending on the need. As the diagram indicates, you'll have pod, and pod will have app container. And assume that your app container needs connection to external world. In the current case, it is database. Ambassador will facilitate it by proxying database connections to external world. So these are critical patterns that can be used in order to adopt pods with right number of containers and interrelation among them. And finally, let's try to understand pod container lifecycle. And lifecycle always starts with request to create resource. Once resource creation is going on, it will move to pending state, where your pod is created and it is in initial phases. Now, until the pod is scheduled to a node and image is pulled and started, it will be in pending phase. Now, once images are pulled and started, it moves to running state. Now, at least one of the pod's container is running. So, whenever you will have one container running of a pod, it means it is in running state. Then comes succeeded. Now, pods which are not intended to run indefinitely are marked as succeeded when all the containers complete their work successfully. Now comes failed. Failed indicates that when a pod is not configured to run indefinitely and at least one of its container terminates unsuccessfully, lifecycle state will be failed. Finally, we have a special state called as unknown. Unknown indicates that the state of the pod is unknown because you will have kubelet that has stopped reporting communication with the API server. And this typically happens when worker node has failed or has been disconnected from existing network. So by using right pod design pattern and also Keeping an eye on the life cycle of pod container, you'll be able to know the status and plan management of pods accordingly. In this video, we'll list the key objective of Kubernetes Service and the different approaches of exposing those services. Now, some of the critical features afforded by Kubernetes Service are: it provides an abstraction to define a logical set of pods, which in turn will run containers, and a policy to access them. Kubernetes services are defined using YAML, which is preferred, but you can also go ahead with JSON. Kubernetes services are assigned IP address, which is used by service proxies. Apart from that, you can also map an incoming port to any target port, and that you do by configuring it in YAML file. Finally, Kubernetes services supports TCP, UDP, as well as SCTP protocols. Now let's go ahead and briefly list different types of Kubernetes services. There are 4 critical types. First is cluster IP, which is the default type that exposes the service on a cluster internal IP. Second is load balancer, which exposes the service externally, but yes, it will use load balancer of your cloud provider. Third is node port, which exposes the service on each node's IP at a static port that you have configured. And fourth is external name. They are there to map the service to the content of the external name field. We need to know that it does this by returning a value for the CNAME record configured in DNS. Now let's try to understand creating Kubernetes service with YAML file. Your file must have kind and API version. For services, we are using v1 and kind is service. Then you give a name to the service, and that you do by using metadata name. In the current case, name is hostname-service. And then you go and provide the specification, where first element of spec is type. You are specifying it to be node port. It means the current service that will get created when you execute this configuration file will be of type node port. In short, it makes the service available to network so that requests from external clients can be served. Then you have app:/echo-hostname, which is a selector that can be used in other configuration objects. And finally, you have ports, where you are specifying node port: 30,163, port 8080, and target port as 80. Where node port will access service via the external port number. Port number is exposed internally in the cluster, and target port is the port that containers are listening on. After configuring this file, you can use Cube Ctl command and create the service. We need to also understand that node port will forward requests to pods with labels of the current value, which is echo-hostname. Now let's try to understand different ways to discover services. There are 2 ways. DNS, which is recommended method, where DNS server is added to the cluster to watch Kubernetes APIs. Second is env-var, where kubelet will add environmental variable for each active service and will make it discoverable. Now, after understanding ways to discover, let's conclude by identifying approaches to expose services. And there are 3 different approaches. First, proxy-mode: user space. In this particular mode, kube-proxy keeps an eye on the Kubernetes master. It will watch for services and endpoint objects that gets added or removed. Now for each service, the mode opens a random port on your local node, and any connection to this particular proxy port are proxied to the service's backend port and reported in the endpoints. Second is proxy-mode: IP tables, where kubeproxy continues to watch Kubernetes master and its endpoints using configured IP tables. Finally, you have proxy-mode: IPVS, where kubeproxy watches the service and the endpoint, and it will call netlink interface in order to create appropriate IPVS rules. And finally, once rules are created, they can be used to access the services. This is how you will be able to work with Kubernetes service by identifying the right type of service that you need, adopting the right way to discover it, and provide right approach to expose the services. In this video, we'll create a service which targets TCP port 80 on any pod and expose the service onto an external IP address. Our first objective is to ensure that we are able to see what all deployments are created using Cube Ctl. That we have done in the video titled Creating and Managing Deployments using Cube Ctl. In order to see what all applications are running, we'll launch our command prompt where Cubectl is installed, and we'll write Cubectl followed by a space followed by get space followed by deployments. We'll press enter. Once you'll press enter, you'll find that your application is available and it is running. Now let's go and check what pods are running the application. To do that, we'll be using Cubectl command followed by a space, followed by get, followed by a space, and we'll specify pods and we'll press enter. You'll find that your current application has been allocated a pod, current status of the application is running, and it is in ready state. Sometimes if no pods are running, it means that interactive environment through which you are trying to get the details is still loading. So wait for a couple of seconds. Once you see the pods, you need to go ahead and you need to check what all are the current services which are running in your current Kubernetes cluster. To do that, you'll go to the command prompt and you'll write Cubectl followed by a space, followed by get, followed by a space, and you'll specify services. After specifying services, you'll press enter. Once you'll press enter, you'll find that it's running one service. And the service which it is running is Kubernetes, which was created by default when we installed and we started Kubernetes cluster. Now our objective is to create a new service and expose it to external traffic. To do that, first let's clear the screen. And now we'll write Cubectl command at the command prompt followed by a space, followed by expose, followed by a space. We'll specify the resource, that is deployment, followed by slash and the name of the deployment resource, which was deploy1 in our case. Next, we'll have to specify type of service. We'll give a space, we'll specify -- type equal to cluster IP, which is the type of service, followed by a space, followed by -- port, followed by a space, and then you'll specify the port number, that is 80. After specifying the command, we'll press enter. Once you'll press enter, you'll find that now your service is exposed. Let's go ahead and use get services command once again. To do that, we'll write Cubectl, followed by space, followed by get. Again, we'll give a space and we'll write services. After writing the command, we'll press enter. Once you'll press enter, you'll find that now you have a service called deploy1, which is running as cluster IP. Now to find out what port was opened externally, we need to use a command called Cubectl, followed by describe, followed by services, followed by slash and name of the service, which is deploy1. We'll press enter. After writing the command, it will list the detail about the services. You need to locate IP, which specifies the IP address, followed by port, followed by target port, which is 80/TCP, followed by endpoints, that is 10.1.0.7:80. This is how you'll be able to create a service which targets TCP port 80 on any pod and exposes this service onto an external IP address. So in this course, we have examined the key features and components of Kubernetes, how to install all-in-one Kubernetes using containers, use Cubectl to run applications on Kubernetes clusters, create services on pods, and expose them to external IP addresses. We did so by exploring the concept and benefits of container orchestration, the different container orchestration and container orchestration deployment options that we can adopt to manage containerized deployments, the key features and components of Kubernetes, and how to install all-in-one Kubernetes using containers to run Kubernetes components as Docker containers on a single host. The concept of pods in Kubernetes, the approaches used by pods to manage multiple containers, the key objectives of Kubernetes services, and the different approaches of exposing services. How to create and manage deployments that runs applications on Kubernetes clusters using Cube Ctl. In the next course, we will learn how to install and configure Kubernetes tools, work with Cubeadm and Cube Ctl to create and bootstrap Kubernetes clusters, deploy applications and inspect cluster resources, create namespaces, limit range, and pods in namespaces, deployments with labels and modify labels, and filter Kubernetes objects. In this video, we'll describe the concept of container runtime interface and list the container runtimes that are supported by Kubernetes. For orchestration, Kubernetes depends on container runtimes. Now, what is a container runtime? It's typically a software that executes containers and manages containers on nodes. So let's try to list certain features of container runtime. First feature is its capability to manage containers images on a node. But yes, you need to ensure that container runtime is installed on each node in a cluster. Apart from that, we need to also recall that pods run in container runtime. Now, what is the relevance of container runtime interface? Let's try to first describe key components of container runtime interface, which will provide help to interact with containers following specifications of CRI. Container runtime's objective is to facilitate communication. In Kubernetes, it does it by using kubelet. So kubelet becomes the first component whose responsibility is to create communication with container runtime. Apart from container runtime, it can also provide communication to CRI shim for the runtime. As it is indicated in the diagram currently displayed on the screen, we'll be invoking a command on kubelet, that is grpc client, and that will facilitate to invoke communication with CRI shim, which has grpc server installed on it. Now, once that communication is enabled, you will have container runtime, which will manage containers. Now, runtime service contains RPCs to manage entire lifecycle of pods and containers. Apart from that, it also calls to interact with containers. And that's what is reflected in the diagram. Now, let's try to focus on Kubernetes and CRI. And that we will do by using a diagram which is currently displayed on the screen. All the communication starts with kubelet, where kubelet will ask to start up a pod, so it will make call to container runtime interface. Once call is made to container runtime interface, the instance of Kubernetes is configured to use a specific CRI. In our case, it is CRI-O daemon. So it will make call to the specific CRI, which is CRI-O daemon. Now, CRI-O daemon will use container image library and container storage library in order to pull container image and manage them on disk. We are also seeing one call to runc. Runc will start the container using the files contained in the container image, and it will also tell the Linux kernel to start up the processes in appropriate namespace, cgroup, and context. Now we need to also understand what task will be done by CRI-O daemon in order to interact with Kubernetes compatible runtime. And that is done by CRI-O daemon by launching command in order to run the container processes facilitated by runc. This is how you'll be able to build interaction between Kubernetes and CRI in order to load images and storage to the disk. Now let's go and list certain container runtimes which are supported by Kubernetes. And first and most important is Docker, which is a widely known container runtime. But yes, there are other runtimes as well. Docker is one of the popular container runtime that is used in production Kubernetes environment. Second type of container runtime is Containerd. It is available as a daemon for Linux and Windows. Objective of Containerd is to manage complete container lifecycle which are present on host system. Third container runtime supported by Kubernetes is RKT, which is an application container engine, typically created for production cloud native environments. And finally, you have LXD, which is Next Generation System Container Manager. It offers better user experience, which is similar to virtual machines, but using Linux containers. Now, finally, we need to identify how containers will run in Kubernetes engine. And that we will do by using a diagram which is currently displayed on the screen. User will be using Kubernetes API in order to create the request. That request will be intercepted by Kubernetes Master, which in turn will make call to Kubernetes nodes using internal APIs. Then comes role of CRI-O, which invokes gRPC call and executes runc command, which will be executed on Linux kernel. Linux kernel will be hosted on container host, which in turn will be present on physical host. All these activities which are being done on master node and also being invoked using CRI-O and runc will facilitate in managing the containers. So now after going through container runtime, we are clear that how actually container runtimes will be used in Kubernetes and what all are the popular container runtimes which are supported by Kubernetes. In this video, we'll describe the life cycle of a pod and list the possible values of pod phase and container states that runs inside the pods. Understanding pod phases is critical. It helps you to intercept what is the current status of pod and decide next course of action. Let's go ahead and list phases which are supported by pod, and that we will do using a table which is currently displayed on the screen. First phase is pending, which indicates initial phase. Second phase is running, which means that at least one of the pod's containers is up and running. Third is succeeded. It means all the containers have completed successfully. Failed comes into play when one of the pod's containers have terminated unsuccessfully because of various reasons. And finally, you have unknown, which indicates that kubelet has stopped reporting communication with the API server. And this typically happens when you have network issues. Now we'll focus on pod condition, which is used by administrators in order to know current status of pod. There are 4 essential conditions. Let's go through the table which specifies different conditions of pod. First condition is post scheduled, which indicates whether or not the pod has been scheduled to a node. Second is initialized, which indicates that the pod's init containers have all completed successfully. Third is containers ready, which indicates that all containers in the pod indicates that they are ready. It means all the containers are up. And fourth is ready, which means pod is ready to provide services to its clients. Now we need to see how do we have transition of pods conditions while pods lifecycle, which is internally managed by Kubernetes cluster. And that we will do using a diagram which is currently displayed on the screen. Now, each condition that we are going to discuss is either fulfilled or it is not fulfilled. As we can see in the diagram currently displayed on the screen, you will have 4 swim lanes, where each swim lane represents a particular condition. At the top, we have pod scheduled, which indicates false initially, which means the pod is created. And then it moves to true, which means that pod is scheduled to a worker node. But yes, rest of them are neither true nor false, which indicates that all containers are ready, but the pod's readiness gate indicates that pod is not ready. Similarly, when you go to fifth, it indicates that pod is ready to provide service to its clients. And finally, it indicates that at least one of the containers is reporting not being ready. Now, the second swim lane is about initialized, where we see false, which means pod object is created, it is indicating false. Pod is scheduled to a worker node is indicating false. But when it comes to the third column, which is all init containers have completed, is true. It means all the init containers have been completed. The rest of the status is also true, which means that when it is in initialized condition, all containers are ready, but the pod's readiness gate indicates that pod is not. Pod is ready to provide service to its clients, and at least one of the container is reporting not being ready. When it comes to third swim lane, which means containers ready, it indicates false for pod object is created. Pod is scheduled to a worker node. All init containers have completed. So finally, we'll see that in containers ready, except the last condition, that is at least one of the containers is reporting not being ready, it is indicating false. And finally, we have ready state, where we'll directly move to the column where it is true, because rest of them are false, which indicates that pod is ready to provide service to its client. Now, each swim lane indicates the timeline, and as indicated in the diagram, you can map the activity that is internally going on during the transition by using true or false. Now, sometimes your pods need to be specified with restart policy, and that you will do in your configuration file. Now, there are 3 pod restart policies. Let's try to understand it using a diagram which is currently displayed on the screen. At the extreme left, we have the first policy, which is restart policy : always, which means that container is restarted regardless of exit code the process terminates with. So in case if process is terminated, still it will restart. Second policy is restart policy : on failure, which indicates that container is restarted only if the process terminates with a non-zero exit code, which means whenever there will be a failure, you will have restart of the container. And third is restart policy : never, which indicates container is never restarted regardless of the exit code. And that's what is indicated in the diagram. Now let's try to focus on possible states of container and how actually it has transitioned. There are 4 critical states. First is waiting, which means container has yet to start. From waiting, it can have transition to running. And when it has that transition, it means that at least one process is running in the container. From running, it can move to termination state, which means that running processes in the container have been terminated. Now, from terminated, it can move back to waiting state. And it is done when terminated containers are restarted. Finally, you have one exclusive state, which is unknown, which indicates that if the state of the container can't be determined, its state is shown as unknown. So be careful with containers with unknown status. And finally, let's try to summarize by exploring container states, where first is waiting, container is waiting to be started. Running, container is created and processes are already up and running in it. Terminated, which means processes that were running in containers have been terminated. And finally, unknown indicates can't determine the state of the containers. You have to use appropriate commands in order to diagnose your pods and containers, which you will do by understanding pod phases, their states, and container states which are running inside the pods. In this video, we'll recall the concept of workloads from perspective of Kubernetes along with the workload resources that manages pods. Now let's try to classify workload types and Kubernetes primitives. Workload can be of following types. They can be stateless, stateful, you can have batch processing, you can have serverless, and you can have traditional or monolithic services. Primitives that supports these workload types are, for stateless, it can be pod, replication controller, and deployment. Now, what do stateless means? Stateless workloads are those workloads which are packaged and deployed as Replica Set in Kubernetes, where replication controller forms the basis of a replica set and it ensures that a specified number of pod replicas are always running. Then comes stateful, which is implemented using pod with volumes Kubernetes primitives. Now let's first try to understand stateful. Stateful workloads typically are classified into two categories. First is the services and second is persistent storage. A pod needs access to a durable storage backend if you are going to implement stateful, and there will be using pod with volumes Kubernetes primitives. Then comes batch processing. Kubernetes has built-in primitives for batch processing and it can be implemented using stateful sets. Serverless computing, as we all know, refers to concept of building and running applications that do not need any server management. It can be implemented using jobs and cron jobs Kubernetes primitives. Jobs tends to run to completion, whereas cron jobs are scheduled. And finally, you have traditional or monolithic. These are the application deployments which can be managed using microservice architecture. Kubernetes provides headless service in order to implement traditional or monolithic service implementation on Kubernetes. Now we'll talk about scalable layers, which means stateless workload. Stateless workloads are packaged and they are deployed as replica sets in Kubernetes cluster. They typically ensure a specific number of pod replicas are always ready and running. Apart from that, when we talk about scalable layer, which is stateless workload, it is recommended to manage stateless services of cloud-native applications. Then comes the second type, which creates durable layer by using stateful workload. They are implemented when your services requires persistent storage. Apart from that, for services that need to run in highly reliable and available mode, stateful workload is preferred. Now let's go through certain scenarios. First scenario is you want stable and unique network identifier implementation. You want stable and persistent storage. You want ordered, graceful deployment and scaling feature. You want ordered, graceful deletion and termination. And finally, you want ordered and automated rolling updates. To implement all these scenarios, we will prefer stateful workload. Then comes the third one, which is parallelizable layer, which is implemented using batch processing. Kubernetes has built-in primitives for batch processing. They are useful for executing run to completion job or even scheduled job. Now let's try to understand using a diagram which is currently displayed on the screen. We can see level of parallelism at the y-axis and completions at x-axis. You'll find some of the pods are ticked with tick mark, which indicates that these are the pods which are configured for completion, whereas you have one pod with circular arrows that indicates that it is a scheduled job. You can have multiple different pods running simultaneously in order to facilitate parallelizable layer. Now let's talk about one of the frequently used layer, that is event-driven layer, which is implemented using serverless paradigm. It is used for building and running applications with no server management. Now let's try to understand how it is implemented on Kubernetes. And that we will do using a diagram which is currently displayed on the screen. You'll have certain generic pods. You will have pool manager controlled by controller, and you can use CLI command in order to interact to controller. Whenever there is a request which is made, typically it may be an HTTP request, it will go to the router. Router will take responsibility of utilizing specific function pods which will be powered by generic pods. It will be made available to execute the request. As an administrator, you will have privilege of using controllers via router. And finally, let's talk about how to implement legacy layer, and that is done by using headless services. Now, legacy layer exists for interoperability. Now, to expose a set of headless services pointing to a monolithic application, you need to utilize headless service. It also helps to reduce coupling to Kubernetes system by implementing discovery. And finally, no internet protocol address is assigned to headless services. So by deciding type of implementation that you want to do, you need to select the right workload types and corresponding Kubernetes primitive to implement workloads of diversified types. In this video, we'll list the built-in tools provided by Kubernetes that can be used to work with Kubernetes systems efficiently. There are multiple different built-in tools which can be used by administrators in order to manage Kubernetes cluster effectively. Let's go ahead and list some of them. First tool is Cube Ctl, which is one of the prominently used command line tool that helps to submit commands against Kubernetes cluster. You can use Cube Ctl to deploy applications, inspect, manage all cluster resources, inspect logs, and also work with workload types. Second tool is Minikube, which is a tool that helps you to quickly set up Kubernetes cluster locally, typically used for development and testing environments. Third tool is Cubeadm, which is one of the prominently used tool by administrators that helps them to initialize a cluster and join multiple workers to the cluster. Apart from that, you can also use Cubeadm to upgrade from previous versions to recent version of Kubernetes resources. And fourth tool is Dashboard, which is a web-based Kubernetes user interface. It is used in order to simplify the way you can deploy containerized applications to Kubernetes cluster. It also provides you utilities which are in form of user interface to troubleshoot containerized applications as well as manage cluster resources. Then comes one of the popular tool which is used for charting, and it is Helm. These are simple Kubernetes YAML manifests combined into a single package that can be advertised to your Kubernetes cluster. Primary objective of Helm is to simplify the way you manage deployments of containerized applications. And finally, you have Compose, which is a tool that is similar to Docker Compose. It helps to translate your Docker Compose files to Kubernetes resources. Now let's try to understand how do we use kubectl and what happens when we use kubectl commands. Primary objective of kubectl is to control the Kubernetes cluster manager. Now let's try to understand how it does it by using a diagram which is currently displayed on the screen. At the left, you will have utility that need to be there on client. Users will ensure that they have installed kubectl and they have configured it to communicate to a cluster on their machines. Using kubeconfig, which is a configuration file, kubectl will apply or submit request to Kubernetes API server. In turn, Kubernetes API server will invoke services in order to execute the command and change the status of Kubernetes resources. We do have etcd cluster, which works as a repository to your cluster. Then comes how do we use Cubeadm. And in order to ensure that we are able to understand what internally happens when you use Cubeadm, we are using a flowchart. So first, let's try to understand. Cubeadm helps provision a secure Kubernetes cluster, and to do that, it provides us two specific commands. First is Kubeadm space init. Second is Kubeadm space join. Now let's take an example. When you invoke Kubeadm space init, it starts with auto-detecting the IP for API advertise address. Then it starts a kubelet, which is a plugin. After starting kubelet, it will invoke pre-flight checks. Then it will generate a token and it will write it. After token is generated and written to a particular location, it will generate Kubernetes static pod manifests for API server, controller manager and scheduler, and etcd. Then comes the task where it has to generate certificate authority key, generate API server key and certificates, generate service account signing keys, and store it in specific directories. After all the keys and certificates are generated, it will generate kubeconfig files for kubelet and administration. Next, it will ensure that kubelet watches for pods. Next, it taints the master node, and finally, it creates kube discovery deployment, which will wait for it to become ready. Once it is ready, it will go ahead and install add-on components using API server. This is how your Kubeadm init works. Now we need to focus on Minikube and its components. We know that Minikube runs a single node Kubernetes cluster locally. It is used for development and testing. Architecture, as we can see in the diagram currently present on the screen, contains virtual machine. Inside that virtual machine, you will have local kube, which contains one master and one node. Your Minikube will run on container runtime. It means if you are planning to install Minikube, you need to first ensure that you have container runtime installed. Now let's go and discover what is role of dashboard. It's a web-based user interface for Kubernetes, helps to deploy containerized applications, and it also helps to manage clusters and its resources. Now, as an administrator, you can prefer using dashboard, which you need to install. Then comes Helm, which is tool for managing packages specifically for pre-configured Kubernetes resources. Let's go ahead and discuss certain features. First feature is it helps to find and use popular software packages as Kubernetes charts. It also shares applications as Kubernetes charts, which can be used by other team members. It helps in creating reproducible builds of Kubernetes applications. It also facilitates in efficiently managing Kubernetes manifest files. And finally, it helps to manage releases of Helm packages. And final tool that we will discuss is Compose. Objective of Compose is to help Docker Compose users to move to Kubernetes. Apart from that, it facilitates to translate a Docker Compose file into Kubernetes objects. And finally, it will also help you to convert V1 or V2 Docker Compose YAML files. So by selecting the right tools, you'll be able to administrate and manage various Kubernetes objects efficiently. In this video, we'll install and configure Kubernetes tools to provision secure Kubernetes cluster and control the Kubernetes cluster manager. There are three essential tools that need to be used by administrators in order to ensure that they're able to bootstrap and control Kubernetes cluster. Those three tools are Kubeadm, which provides you capability to bootstrap the cluster. Then you have Kubelet. It's a component that runs on all the machines in the cluster and does things like starting the pods as well as the containers. And third tool is the command line utility that talks to the cluster. We need to also understand that when we install Cubeadm, it will not automatically install or manage your kubelet or Cube Ctl. So you need to ensure that while installation, they match the version of Kubernetes control plane you want Cubeadm to install for you. Let's go ahead and see what all are the steps that we have to take in order to install these tools. Our first step is always to prepare the system so that we can install the tools, and it heavily depends on what operating system you are using. We are using Ubuntu, so these steps will work fine with Ubuntu. But if your operating system is CentOS, you need to change the commands that we are going to use. So let's go ahead and start with the first step, that is to update the existing operating system and install certain utilities which you will need in order to install these tools. And to do that, we'll connect to the machine where we want to install the tools. After we connect, we'll go to the command prompt and we'll write the command which starts with sudo, followed by a space, followed by apt-get, followed by a space, followed by update. We'll give a space and we'll use $& in order to ensure that it concatenates the command that we are going to write, followed by a space, followed by sudo, followed by a space, and then again we'll use apt-get. We'll give a space, we'll specify install, followed by a space, followed by a flag that is -y, followed by a space, and then we'll specify the tools. First is apt-transport-https. We'll give a space and we'll specify the second utility, which is curl, C-U-R-L, and we'll press enter. Once you'll press enter, it will start updating your existing system. It will set up apt-transport-https, which is the minimum requirement of installing these tools. We'll clear screen by writing clear. Now we need to use second command, that is curl. We'll write sudo, followed by curl, followed by a space, followed by -s. We'll give a space and we'll use the endpoint in order to get the GPG key so that we can add it. We'll specify the endpoint. After specifying the endpoint, we'll give a space and we'll use a single pipe in order to separate the command with the command that we are going to write, followed by a space. We'll write sudo, space, followed by apt-key, followed by a space. We'll write add, we'll give a space, and we'll specify dash. After writing these commands, we'll press enter. Once you'll press enter, you'll find a message indicating OK. Now let's go ahead and create a file called kubernetes.list. To do that, we'll write sudo, followed by a space, followed by vi, followed by a space, and we'll specify the directory where we want to create the file, along with the file name. Directory where we want to create is sources.list.d. So we'll specify the full path that starts with /etc/apt, followed by directory called sources.list.d/, and here we'll specify name of the file as kubernetes.list. We'll press enter. After pressing enter, we need to specify the package path within the file. We'll move to edit mode by pressing escape on the key and I, and we'll make the entry which starts with deb, followed by a space, followed by https:// followed by apt.kubernetes.io, followed by /. We'll give a space and we'll specify Kubernetes-xenial. Give a space and write main. After making the entry, we'll save the file by pressing escape:/WQ and press enter. So now we have specified the package location of Kubernetes from where we'll get the installers. Now let's go ahead and quickly write sudo, followed by space, followed by apt-get, followed by a space and specify update. After writing the command, we'll press enter. Once you will press enter, it will connect to the repository and get Kubernetes package from where you can install. Now let's go and clear the screen by writing clear and start installing the tools that we want. To do that, we'll write sudo followed by a space followed by apt-get followed by a space followed by install and followed by the list of the tools. We'll give a space after install and we'll write kubelet. We'll give a space, we'll write Cubeadm. We'll give a space and we'll write Cube Ctl. After specifying the list of tools that we want to install, we'll press enter. Once you'll press enter, it will read the package list and it will ask your confirmation. Do you want to continue? You need to press Y and finally press enter. Once you'll press enter, it will start downloading the required tools along with installation. Finally, you get message that indicates that it is setting up Cube Ctl, setting up Cubeadm, and now it is ready to be used. But yes, before using it, you need to configure. This is how you'll be able to install and configure Kubernetes tools to provision secure Kubernetes cluster and control the Kubernetes cluster manager. In this video, we'll create a Bootstrap Kubernetes cluster using Cubeadm and use commands to bootstrap Kubernetes worker nodes and join them to the cluster. The first task that we need to do on all the machines which are going to be part of Kubernetes cluster is to install the dependencies. Let's go ahead and install the dependencies. First dependency that we have to install is apt-transport-https. To do that, we'll first connect to the machine and we'll launch command prompt. At command prompt, we'll write sudo, followed by space, followed by apt-get, followed by space, followed by install, followed by space, followed by the first dependency, which is apt-transport-https. We'll press enter. Once you'll press enter, it will install and set up the first dependency. Our next dependency is Docker, because Kubernetes installation depends on container provider. Let's go and install Docker. To do that, first we'll clear the screen. And at command prompt, we'll write sudo, followed by space, followed by apt, followed by space, we'll specify install, followed by docker.io. After writing the command, we'll press enter. Once you'll press enter, it will ask you to continue. You'll press Y and press enter in order to start installation of Docker. Once Docker is installed, you need to start Docker. And to start Docker, we'll go to the command prompt. We'll write sudo, followed by a space, followed by systemctl, followed by a space, followed by start, followed by space, and the process, which is Docker. We'll press enter. Once you'll press enter, it will start Docker. To confirm that Docker is started, you will write sudo at the command prompt, followed by a space, followed by systemctl, followed by a space, and you'll write status, followed by a space, and Docker. We'll press enter, and you'll find that it shows that your Docker is up and running. We'll press Ctrl C, and we'll enable Docker. To enable Docker, we'll write sudo at the command prompt, followed by a space, followed by systemctl, followed by a space, followed by enable, followed by a space, and we'll specify the process that we want to enable, which is Docker. After writing the command, we'll press enter. Once you'll press enter, you'll find that it creates a symbolic link, and this confirms that you have installed the dependencies. Now, our next objective is to install Kubernetes, and this has to be done on all the machines so that they get all the required tools in order to bootstrap a cluster as well as to join the cluster. We'll clear the screen. After clearing the screen, we'll download and add the key for the Kubernetes install. In order to add the key, depending on the operating system, you need to first move to the root user. To do that, we'll write a command that starts with sudo, give a space, followed by -i. Next, you have to use curl command at the command prompt, followed by a space, followed by -s, followed by the endpoint of the key. You have to specify a pipe symbol, give a space, and use the second command to add the key, that is sudo, followed by a space, followed by apt-key, followed by a space, followed by add, and followed by a dash. Once you'll press enter, you'll find a message indicating OK. It means that you have added the key to initiate installation of Kubernetes. Now we need to create a file. To create a file, in order to add the package, because we are using Ubuntu, we need to use command called vi, followed by a space, followed by /etc, followed by /, followed by app. After specifying app, we'll give a /. We'll use directory called sources.list.d. After specifying sources.list.d, we'll give a / and we'll give name of the file where we want package to be specified. Let's give name as kubernetes.list and press enter. You'll find that a file opens. You need to move to edit mode by pressing escape and I, and you have to add deb followed by a space and the endpoint where that package is. We'll write http://apt.kubernetes.io/ give a space and write Kubernetes -xenial, give a space and write main. After making the entry, save the file by pressing escape key, typing : followed by wq. We'll press enter. So now we have added the repository from where we'll get all the tools that we want to install on all the nodes which are going to be part of Kubernetes cluster. We'll clear the screen and we'll write the command which starts with sudo, followed by a space, followed by apt-get, followed by a space, followed by update, and we'll press enter. Once you'll press enter, it will download all the packages of Kubernetes and it will make it ready so that you can install it. Once packages are read, we'll clear the screen and we'll install Kubernetes tools on all the nodes which we want to be part of Kubernetes cluster. We'll write sudo, followed by a space, followed by apt-get, followed by a space, followed by install. Followed by a space, we'll use the flag called -y, followed by a space, followed by the tools, which is kubelet. Give a space, use Cubeadm. Give a space, use Cube Ctl. Give a space and specify Kubernetes -cni for native interface. After writing the command, we'll press enter. Once you'll press enter, it will start installing all Kubernetes tools. Now, once tools are installed, you need to now configure your system for Kubernetes. To do that, first we'll clear the screen by writing clear at the command prompt and pressing enter. And we'll go and we'll first disable swap. To do that, we'll write command that starts with sudo, followed by space, followed by swap off, followed by space, followed by -a. We'll press enter. To make swap permanent so that you don't need to re-enter every time you reboot, you can edit a file. Let's go ahead and edit the file. To do that, we'll write sudo, followed by a space, followed by vi, followed by a space, followed by /etc/ name of the file, which is fstab. We'll press enter. It opens the file. We'll move to edit mode by pressing escape and I, and we'll put a hash to comment the line. This will ensure that swap is permanently disabled. We'll press escape, followed by :wq to save the file. So now we have disabled the swap. Our next objective is to start initializing the master. Let's use the current machine as master and write a command that will bootstrap and initialize the master. To do that, we'll write sudo. We'll give a space, followed by Cubeadm. We'll give a space followed by INIT. And we'll press enter. Once you'll press enter, it will start initializing the master. We need to wait for the command to complete. Now, once init command executes successfully, you will get message that indicates that to start using your cluster, you need to run following commands, which is creating a directory, copying it to home directory under .cube/config folder, and then changing the ownership. Apart from that, it also provides detail that you can use in order to ensure that worker nodes can join to current master. Let's go ahead and copy the command. After copying the command, you can keep this command ready so that you can use it to join workers to master. Now let's go ahead and complete the prerequisite before we start using the cluster. And first task is to make a directory. We'll be at the prompt and we'll write mkdir followed by space, followed by -p, followed by space, followed by an environmental variable that starts with $home, followed by /, followed by .cube, and we'll press enter. Once you'll press enter, it will come to the prompt again without displaying any error. Our second command that we have to use is sudo, followed by space, followed by cp, followed by space, followed by -i, followed by space, and then we'll specify the path called /etc kubernetes /admin.conf, followed by space, and we'll copy it to a location which has been indicated using environmental variable that is $home, followed by /.cube, followed by /config. After copying admin.conf to the folder which is there in .cube named config, we'll press enter. Once you'll press enter, you need to go ahead and change the ownership. And to do that, you'll be there at the prompt and you'll write sudo, followed by space, followed by CHOWN to change the ownership, followed by space, followed by $, and within bracket, you'll specify ID, followed by a space, followed by -u. After closing bracket, you'll put a colon, followed by another environmental variable that will start with $, and within bracket, you'll specify ID, give a space, -g, followed by a space, and finally you'll specify the path of config folder which starts with $home /.cube/config. After writing the command, you'll press enter. Now your master is ready. Your next objective is to join a worker. In order to join a worker, you need to ensure that all the dependencies are installed and all the tools are also installed. We'll assume that we have already prepared a worker. We'll connect to the worker and we'll write the command that starts with Cubeadm space join space -- token followed by a space, and we have to specify token value followed by a space followed by IP address. Now once we press enter, the worker node will be connected to the master. This is how you'll be able to create and bootstrap Kubernetes clusters using Cubeadm and use commands to bootstrap Kubernetes worker nodes and join them to the cluster. In this video, we'll demonstrate how to configure Cube Ctl to locate and connect to Kubernetes clusters and use Cube Ctl to deploy applications and inspect cluster resources. After installation of Cube Ctl, which we have done in previous video of course 1, video titled Installing and Configuring Kubernetes Tools of the current course, we'll go and we'll first verify whether Cube Ctl is installed or not. And if it is installed, what is the version? To do that, we'll go to the prompt. At prompt, we'll write Cube Ctl followed by a space, followed by version. After version, we'll give a space and we'll use --client and we'll press enter. Once you'll press enter, you'll find that it displays major and minor version. You need to ensure that it is compatible with your cluster's API server. Now we need to configure Ctl so that it can communicate with Kubernetes clusters. It can be multiple clusters to which you can communicate using a single installation of Ctl. Now let's go and verify what is the current configuration of Ctl. And in order to do that, we'll go to the prompt and we'll write Ctl followed by a space. Then we'll specify config. We'll give a space after config and we'll write view. After writing Ctl space config space view, we'll press enter. Once you'll press enter, it will show you the current configuration of Ctl. Your current Ctl is configured to communicate with a cluster which is defined under clusters in line number 1. In line number 2, you are specifying the specific cluster. That specific cluster is specified by using 3 essential properties. First is certificate-authority-data, where when you will configure, you need to specify certificate authority file where that certificate authority data is present. Just below certificate in line number 4, we have specified server, followed by colon, followed by a space, and then endpoint of Kubernetes cluster along with port. Our current Kubernetes cluster is running at 172.31.13.56, followed by port 6443. We need to create the endpoint by writing https://172.31.13.56:6443. Next comes the name of the Kubernetes cluster. Current cluster is named as Kubernetes itself. Next, you have to specify the context, which we have specified in the current file in line number 6. Below context, we are specifying the context and we are giving again certain details about the context. First is the cluster. We are specifying cluster colon followed by Kubernetes, that is the name of the cluster. Second line is about user. We are specifying user colon Kubernetes dash admin. Third is the name, which is Kubernetes dash admin @Kubernetes, and just below name we have current dash context. It means to which Kubernetes your current Ctl is communicating with. It is Kubernetes dash admin @Kubernetes. Kind is config, that specifies the kind of resource, and then preferences followed by users. Current user is specified by using username. We are specifying Kubernetes dash admin, and user specific client certificate and client key, which need to point to the path of the file where you have your client certificate and client key data. These are the entries which are present in configuration file of Ctl. Now let's take a case and see how we can configure Ctl to communicate with multiple clusters. To do that, we have installed Ctl in a different machine. Let's go and see the version. To see the version, we'll go to the prompt of the newly created machine installed with Ctl and we'll write Ctl followed by space, followed by version, followed by space, followed by dash dash client, and we'll press enter. Once you'll press enter, it will indicate again major and minor version. You need to ensure that it is compatible with your Kubernetes server. Our next objective is to create a file. We can create file in whatever directory we want. But yes, we need to specify the directory where our configuration file is by using environmental variable called as kubeconfig. Before we create a file, we'll clear screen. We'll move to the directory where we have already created a sample file. To do that, we'll write cd followed by a space. Kubeconfig demo is the name of the file, and we'll press enter. Now, once we are there in kubeconfig demo directory, we'll open the file that we have created in order to configure Ctl so that it can communicate with multiple clusters. To do that, we'll edit the file. We'll write vi followed by a space. Name of the file is config demo. We'll press enter. Once you'll press enter, you'll find that we have configured a similar kind of file where we are using API version colon v1 in line number 1 kind colon config preferences, and then we are going for clusters. In line number 5, we have specified clusters, and now we are specifying two different clusters. First cluster's name is Kubernetes and second cluster's name is testing. After specifying clusters, we are specifying users, where first user that we are specifying is Kubernetes-admin and second user that we are specifying is tester. And finally, we are specifying context, where we have specified two contexts under context element. First context name is Kubernetes-admin@Kubernetes and second context name is exp-testing. After configuring the file, we'll save it by pressing escape followed by :wq if you are using VI editor, and we'll press enter. We'll clear the screen, and our next objective is to use Cube Ctl command in order to add cluster details to the configuration files. Now we need to go and use commands in order to add cluster details to the configuration file. But for that, you need to ensure that you are there in the right directory. Our current directory where our configuration file is kubeconfig-demo. We need to ensure that our present working directory is kubeconfig-demo. Next, we have to go and we have to add details to the cluster by executing certain command. First set of command is to set the cluster, and we'll do that by using Cube Ctl at the command prompt. We'll give a space config space followed by --kubeconfig equal to name of the file, where we have specified our configuration. Then we are giving a space after specifying name of the configuration file. We are using set-cluster. We'll give a space and we'll specify name of the cluster, that is Kubernetes. Followed by a space, and then we'll specify endpoint of the cluster by using --server equal to https://1.2.3.4, assuming that our Kubernetes cluster to which we want to communicate is running at this endpoint. Then we have to give a space followed by --certificate-authority equal to name of the file where you have your certificate authority. After specifying the details, we'll press enter and it will give you a message indicating that cluster Kubernetes is set. Similarly, you will set the other cluster also to which you want to communicate using the same Cube Ctl client. We have to specify the same command. We'll write Cube Ctl at the command prompt followed by space followed by config followed by space followed by --kubeconfig equal to config-demo, which is the name of the file. We'll give a space and then we'll write set-cluster, give a space followed by testing, which is name of the cluster, followed by a space, and then we'll specify --server equal to https://5.6.7.8. You have to change this to the cluster URL to which you want to communicate. We'll give a space and then we'll specify -insecure-skip-tls-verify. It means we are skipping TLS verification step. We'll press enter. Once you'll press enter, you'll find that now you have two clusters set in your Cube Ctl configuration that will enable you to communicate with two clusters using the same Cube Ctl. Now our next objective is to add the user detail to the configuration file. Before we add the user, we'll clear the screen, and at the prompt we'll write a command using Cube Ctl that will help us to add the users. To add the user, at the prompt we are writing Cube Ctl followed by a space followed by config followed by a space followed by --kubeconfig equal to config-demo, followed by a space, and then we are using set-credentials followed by a space. We are specifying the name of the user, that is Kubernetes-admin, followed by a space, and then we are using --client-certificate equal to ca.cert, followed by a space, and we are also specifying --client-key equal to ca.key. You need to ensure that you have these files available in the host where you are adding the user so that it can authenticate and get authorization from Kubernetes cluster to enable communication for the user. We'll press enter. Once you'll press enter, you'll get a message indicating that Kubernetes-admin is set. Similarly, you will add more users depending on you want to communicate with Kubernetes cluster as how many users. And finally, we need to go and we need to add the context. To add the context at the prompt, we'll write Cube Ctl followed by a space, followed by config, followed by a space, followed by dash dash cube config equal to config demo, which is name of the file, followed by a space, followed by set dash context, followed by a space. You'll specify Kubernetes dash admin at the rate Kubernetes as the context name, followed by a space. You'll specify the cluster by using dash dash cluster equal to Kubernetes, followed by a space. You'll also specify the namespace to which you want to communicate. And that we will do by using dash dash namespace equal to frontend, assuming that frontend namespace is there on your cluster. We'll give a space and then we'll specify the user by using dash dash user equal to Kubernetes dash admin. We'll press enter. Once you'll press enter, you'll find that it creates the context Kubernetes dash admin at the rate Kubernetes. This is how you will be able to configure your Cube Ctl in order to communicate with multiple Kubernetes clusters. We'll clear the screen. We'll write Cube Ctl followed by space, followed by config. We'll give a space and we'll specify dash dash cube config equal to config demo. After specifying config demo, which is the file, followed by a space, and then we'll specify view. After writing view, we'll press enter. Once you'll press enter, you'll find that your cube config file contains all the details that are required by Cube Ctl in order to communicate with cluster of your choice. In order to set a specific context of use, you will be using a command that starts with Cube Ctl followed by space, followed by config, followed by space dash dash cube config, and you'll specify equal to. After specifying equal to, you will specify name of the file that you want to use. We'll specify config demo, which is the name of the file, and finally we'll give a space and we'll use a flag called as use dash context. After writing use dash context, we'll specify the context that we want to use. For example, we'll give a space and we'll specify Kubernetes dash admin at the rate Kubernetes, and we'll press enter. Once we'll press enter, you'll find that your current context is switched to Kubernetes dash admin at the rate Kubernetes. This is how you will be able to set the current context to a particular Kubernetes cluster, so that whenever now you invoke a command for deployment or to manage clusters using Cube Ctl, it will communicate to Kubernetes cluster which is set in the current context. Whenever you want to work with other cluster, you have to switch to that particular context by using the same command. Once you have set your Cube Ctl, you can change the context and you can use Cube Ctl create and various inspect commands in order to inspect your deployment resources. In this video, we'll demonstrate what are the steps that we have to use to configure Kubernetes cluster to run a combination of Linux and Windows nodes in order to facilitate mixed pods running on Linux with pods that runs on Windows. Our first step is to ensure that we have done the right configuration to prepare Kubernetes control plane for Flannel. Flannel is the utility that can be used in order to come up with cluster which has mix of Windows as well as Linux. We need to ensure that we have installed Kubernetes Master, and in order to confirm that Kubernetes Master is installed and all the utilities are up, you need to go and you need to write a command. That command is Cubeadm followed by space followed by version. After writing Cubeadm followed by space version, we'll press enter. Once you'll press enter, it will confirm that Cubeadm is installed. Major and minor versions are also specified in the output. Now let's go and prepare Kubernetes master, or we can say control plane for Flannel. To do that, first we need to modify the probe bridge. To do that, we'll write mod probe followed by space bridge and we'll press enter. Once you'll press enter, it will give you a new prompt indicating that previous command has executed successfully. Now let's go ahead and execute a command to configure sysctl. To do that, we'll write echo followed by space double quotes, and within double quotes we'll write net.bridge.bridge -nf-call -ip tables equal to 1, followed by space, and we'll use double greater than symbol followed by space and specify the file for sysctl. To do that, we'll write /etc/sysctl.conf and we'll press enter. Once you'll press enter, it will give you a new prompt indicating that command has executed successfully. Now let's go ahead and use sysctl command. To do that, we'll write sysctl followed by space -p followed by space /etc/sysctl.conf and we'll press enter. Once you'll press enter, it will show you that configuration that you have applied in last step is completed. Now our objective is to download the most recent Flannel manifest and configure Flannel for Linux. To do that, at command prompt, we'll write wget followed by the endpoint where we have cube-flannel.yml file. We'll press enter. Once you'll press enter, you'll find that it will download and it will save cube-flannel.yml file. Now let's go ahead and write ls at the prompt and press enter. Once you'll press enter, you'll find that you have cube-flannel.yml file present. We'll clear the screen. After clearing the screen, we need to now modify Flannel manifest in order to set VNI and the port. And to do that, we need to edit Flannel manifest file. So we'll write ls, and once we get the name of cube-flannel.yml, we'll edit the file. To edit, we'll write vi followed by space followed by cube-flannel.yml file. Once you will open the file, you will get API version, which is policy/v1 beta 1. We need to directly move to data section in the current file. And in data section, we'll move to net-conf.json, where we need to specify the right network. Apart from network, we need to also specify the backend. In order to specify the network, which is default 10.244.0.0, we need to specify the IP. We'll be specifying IP of our choice along with CIDR. Let's go ahead and specify 172.31.17.67/16. We'll move to backend section of net-conf.json, and in backend section, after type, which is specified as VXLAN, we'll specify another entry. That entry is VNI. We'll specify within double quotes VNI followed by colon followed by space followed by 4096. After writing 4096, we'll ensure that values are separated using comma. This is the reason why after type colon VXLAN we have specified a comma. After specifying VNI and the value, we'll put a comma, we'll press enter, and within double quotes we'll specify port. After writing port within double quotes, we'll give a colon followed by space followed by 4789. Now this is what is the configuration which is needed in Flannel manifest file. After making the changes, we will press escape followed by :WQ in order to save and exit from our VI editor. Now our next objective is to apply the Flannel manifest and validate. To do that, you'll write Cube Ctl followed by space apply followed by space -f followed by space and followed by name of the manifest file, which is cube-flannel.yml. We'll press enter. Once you'll press enter, you'll find that it will create all the assets which are defined in Flannel manifest file. After a few minutes, you will also see that all pods are running if the Flannel pod network was deployed. To confirm that, we'll write Cube Ctl followed by space get followed by space pods followed by space dash n followed by space cube dash system, because these pods will be deployed by default in cube dash system namespace. We'll press enter. Once you'll press enter, you'll find that you have cube dash flannel dash ds up and running. This is how you'll be able to prepare your master so that you can have a mix of pods which are running on Windows as well as Linux. Now we need to go to our Windows machine. We need to ensure that we are using compatible Windows machine. Windows machine that we are using is Windows 2019 server. We'll go and we'll connect to it. Once you have launched your Windows machine, you need to ensure that you have installed all the tools, which includes Cubeadm and Cube Ctl. Let's go ahead and launch PowerShell. To launch PowerShell, we'll go to search icon, which is pinned at the left of your current status bar, and we'll write PowerShell. Once you write PowerShell, you will get an option. You need to select the best match, right click on it, and click on Run as Administrator context menu. It will launch PowerShell. Now you want to confirm whether Cubeadm is installed or not. To do that, you'll write Cubeadm followed by version, and you'll press enter. Once you'll press enter, it will show you Cubeadm version. If it is installed, we can clearly see that major and minor versions are matching to the control plane which we have installed on Linux. Now we have to join Windows to our existing master, that is control plane present on Linux. To do that, first we need to generate the token and the key to join. To do that, we'll go back to our master and we'll clear the screen after connecting to master. We'll be using a command that starts with Cubeadm, followed by space, followed by token, followed by space create, followed by space dash dash print, followed by dash join, followed by dash command, and we'll press enter. Once you'll press enter, it will give you a command that you can use in order to join your existing Windows machine on which you have installed Kubernetes and you want that machine to be part of your existing cluster. We'll copy the command. After copying the command, we'll move back to our Windows machine and we'll paste the command. To paste, we'll right click and select paste from the context menu. After copying the command, we'll press enter, and once you'll press enter, you'll be able to join your Windows machine to Kubernetes cluster. This is how you'll be able to join a Windows machine to Linux-based control plane and utilize mixed pods running on Linux as well as Windows. In this video, we'll demonstrate how to use Cube Ctl in proxy mode to check location and get credentials to authenticate against API server to access REST API using HTTP client. There are multiple different ways in which you can interact with your Kubernetes cluster. One of them is by using Cube Ctl. Using Cube Ctl commands, you can know the location of the cluster and will have credentials to access it by configuring Cube Ctl tool, which is already demonstrated in the video titled Locating and Connecting to Kubernetes using Cube Ctl. Now, what is the other approach? Other approach is to directly access the REST API. Now, we know that Cube Ctl handles locating as well as authenticating to the API server. What if we want to directly access the REST API without using Cube Ctl? We'll be able to do that by using various HTTP clients like wget, curl, browser, or other third-party HTTP clients. Now, there are two ways of doing it. One, you can run Cube Ctl in proxy mode, and second, which is an alternate approach, to provide the location and credentials directly to your HTTP client. And in order to do that, you need to know how to get them. In order to get credentials and other details so that you can communicate directly with REST API, you need to go and explore approach in order to get details of secret using kubectl describe command. Let's go ahead and use kubectl describe command so that we can get the details which can be used directly with REST API. In order to do that, we'll be connecting to the machine where we have installed kubectl. We'll write command that starts with kubectl, followed by space, followed by describe, followed by secret. After writing, we'll press enter. Once you'll press enter, you will get certain details which specifies you the name, the namespace, labels, annotations, type, as well as the credential token. We'll clear the screen and we'll see how we can simplify it. To simplify it, we'll be using Linux command called grep and cut in order to get the token for the default service account. And for that, we need to set certain environmental variables. Let's go ahead and set the first environmental variable. First environmental variable that we will set is API server. To do that, we'll write API server, ensure that all are in caps, followed by equal to, followed by dollar in order to specify Linux commands. We'll use kubectl followed by space, followed by config, followed by space, followed by view. View will be followed by a space and we'll use dash dash minify. And then we'll use a pipe symbol followed by grep. After grep, we'll give a space and we'll specify what we want to grep. We want to grep server, so we'll write server. We'll give a space, we'll use pipe and we'll use cut command followed by a space, followed by dash F, followed by 2 dash. We'll give a space and we'll write dash D, followed by a space. Within double quotes, we'll specify colon. We'll give a space and we'll use again a pipe symbol followed by TR. We'll give a space followed by dash D. And finally, after giving space, we'll use double quotes and we'll close the bracket, press enter. So you have set the API server environmental variable. Our next objective is to set the secret name. So we'll write at the command prompt secret underscore name equal to dollar. Within brackets, we'll write kubectl followed by a space, followed by get, followed by a space, and we'll specify secrets because we want to get detail from secrets. We'll give a space, add a pipe symbol, followed by a space, and we'll use grep followed by a space, followed by caret symbol, followed by default. And then we'll give a space, we'll use a pipe symbol followed by a space, and we'll again use cut, give a space, followed by dash F1, followed by a space, followed by dash D, followed by a space, and single inverted commas, and finally we'll close the bracket and press enter. So now we have API server and secret underscore name environmental variable set. Third objective is to set the token. And we'll do that by moving to the command prompt and writing token equal to dollar symbol, followed by starting of the bracket, followed by kubectl. We'll give a space, we'll use describe, we'll give a space, we'll use secret, and then we'll specify a space followed by dollar secret underscore name. And to get the secret name, we'll give a space followed by a pipe, followed by a space, we'll use grep. After writing grep, we'll give a space, we'll write dash E, followed by a space, and within single quotes, we'll specify caret token. After writing caret token within single quotes, we'll give a space, we'll use a pipe symbol, and we'll use cut, followed by a space, followed by dash F2, followed by a space, followed by dash D, and within inverted commas, we'll specify colon. Next, we'll specify a pipe followed by a space, followed by TR, followed by a space, followed by dash D, and again we'll give a space and empty double quotes before we close the bracket. After closing the bracket, we'll press enter. So now we have these three environmental variables, which are API server, secret underscore name, and token set. We can use HTML clients in order to invoke REST API. Let's go ahead and try. To do that, we'll write curl, followed by a space, followed by dollar API server /API. We'll give a space, and we'll take the header flag by using dash dash header. And what header flag we want? We want authorization, so we'll write authorization. We'll give a colon, followed by a space. We'll write bearer, followed by a space. We'll use dollar token, which is again an environmental variable that we have declared earlier. We'll close by using double quotes. We'll give a space and we'll write dash dash insecure, and we'll press enter. Once you'll press enter, you'll find that it has added the required details which can be used in order to invoke REST APIs. Now let's go ahead and discuss directly accessing the REST API, but now we will run Cube Ctl in proxy mode. Let's clear the screen before we do that. Cube Ctl in proxy mode is recommended approach because it always uses stored API server location. It also takes responsibility of verifying identity of API server, and for that it will be using self-signed certificate. Kubectl in proxy mode also authenticates to API server. Now let's go and see how to use kubectl proxy. To do that, we need to run kubectl in a mode where it acts as a reverse proxy to handle locating the API server and finally authenticating it. To do that, we'll be writing a command that starts with kubectl, followed by space, followed by proxy, followed by space, followed by -- port equal to 8080. Meaning of proxy is to enable creation of proxy server or application level gateway between localhost and the Kubernetes API server. Apart from that, when you use proxy mode, it also allows serving static content over specified HTTP path. Let's go ahead and execute the command by pressing enter. Once you will press enter, it indicates a message that it is starting to serve on 127.0.0.1:8080. So this is how you will be able to use proxy in order to explore the API using HTTP clients, which can be curl, wget, or a browser. You can also replace localhost with ::1, which is specifically used for IPv6. In this video, we'll demonstrate how to create namespaces and configure the default memory requests and limits by creating and configuring limit range and pods in the namespaces. Kubernetes has capability to support multiple virtual clusters, which may be there on the same physical cluster. These virtual clusters, which are present on physical clusters, are called as namespaces. Primary objective of namespace is to enable use of multiple environments for many users which are spread across multiple projects and also teams. Now, why do we use namespace? We use namespace in order to provide scope for all the names that we are using for resources. But we need to ensure that resource names are unique within a namespace, but you can have same name of the resources across namespaces. Our first task is to go and see how many namespaces are there in the current cluster. To do that, we'll be using a command at the command prompt which starts with kubectl, followed by a space, followed by get, followed by namespace. We'll press enter. It will display how many namespaces are currently present in the cluster. Now let's go ahead and configure namespace and specify default memory requests and limits for the namespace. To do that, we'll be writing a command that starts with kubectl, followed by a space. We'll use create. We'll give a space and specify the object, which is namespace, and we'll give a space and we'll specify name of the namespace. After specifying the name of the namespace, we'll press enter. Once we'll press enter, it will display a message indicating that namespace is created. We'll go and we'll confirm by writing kubectl, followed by a space, followed by get, followed by a space, followed by namespace, and we'll press enter to ensure and confirm that our namespace is also created. Now, how do we limit range? That we can do by writing a configuration file. To do that, we'll first clear the screen. We'll move to the directory where we have already created a file. To move to the directory, we'll write cd, followed by a space, followed by examples, and we'll press enter. We'll open the file where we have configured limit range object. To do that, we'll write vi, followed by a space, and we'll specify the name of the file where we have configured. We'll press enter. It's a YAML file where line number 1 specifies API version, followed by : followed by a space and v1. In the second line, we are specifying the kind by writing kind colon followed by space followed by the kind which we are creating, which is limit range. Line number 3, we are specifying metadata followed by a colon. Below metadata, in line number 4, we are specifying name followed by a colon followed by mem dash limit dash range. And in line number 5, we are specifying spec, that is specification of the limits. We are doing that by writing spec colon. Immediately after spec colon, we have specified limits followed by colon, and we have specified the default limits by using dash followed by default colon, and below default colon we have specified memory colon followed by the memory that we want, which is 512 MI. We have also configured default request memory by using default request colon, and below default request colon we have specified memory colon 256 MI. And finally we have specified type colon to be container. After writing the configuration file, we need to now create the limit range in the namespace that we created recently. And to do that, we'll save and we'll exit from the file. To save and exit, we'll press escape followed by colon WQ. Now we have to use Cube Ctl apply command in order to create the limit range in the namespace that we created. To do that, we'll again go and see what all are the namespaces that we created. By writing Cube Ctl, giving a space, get, again we'll give a space followed by namespace and we'll press enter. So we have our namespace which is displayed on the screen. Now we have to use Cube Ctl apply command. To do that, at the prompt we'll write Cube Ctl followed by apply followed by space. After space we'll use a flag called -f followed by a space, and we'll give the name of the file where we have configured. Name of the file is memtune.yaml. After specifying name of the file, we need to specify another flag, and to specify flag, we'll give a space after .yaml. We'll write -- namespace equal to our namespace that we created in previous step. After writing, we'll press enter. In case if you get an error, check the appropriate name and ensure that namespace name that you are taking is proper. After correcting the namespace name, we'll press enter. Once we'll press enter, you will get a message that indicates that now your limit range is created. Name of the limit range that is created is mem-limit-range. Now if container is created in the current namespace, and you are not specifying the memory request and the memory limit to it, it will take the default that you have set in the current configuration file. Now let's go ahead and configure a pod by configuring limit which is specifically applied to pods. To do that, we'll first clear the screen. We have already written the configuration file, so we'll write ls and we'll open mem-pod.yml to understand. To open the file, we'll write vi followed by mem followed by dash followed by pod.yml and we'll press enter. You'll find that configuration is different. We have specified API version :v1 in line number 1. In line number 2, we have specified kind, and now kind is not limit, it is pod. Metadata, we have specified a name for the metadata which is default-mem-demo. And finally, we have specified spec for containers where we are specifying name as default-mem-demo-container, and we are also specifying the image by using image:\nginx. Now we have specified the default. Let's go ahead and create the pod applying the current default. To do that, we need to first save the file and exit from it. To save the file, we'll press escape WQ and we'll exit. Now we need to create the pod using the current configuration that we have seen. And to do that, we'll be using Cube Ctl followed by space followed by apply. We'll give a space and we'll use a flag called -f. After specifying -f, we'll specify name of the file that we want to apply, which is mem-pod.yaml. We'll give a space and we'll specify the namespace where we want. To specify the namespace, we'll write dash dash namespace equal to name of the namespace where we want to create the pod. After specifying namespace, we'll press enter. Once you'll press enter, you'll find that it has created the pod. Now let's go and get detail of the pod. To get detail of the pod, we'll write a command at the prompt called Cube Ctl, followed by space, followed by get, followed by pod, and we'll specify the name. Name is default mem demo. Now it depends. If you want to get output in YML format, you can give a space and use the flag with dash dash output equal to YAML. And finally, you need to specify the namespace as well. To specify the namespace, you'll give a space, you'll write dash dash namespace equal to name of the namespace where this pod is created. After writing the command, we'll press enter. Once you'll press enter, it will give you complete detail of the pod which is created with the required limit. This is how you'll be able to create namespace and configure the default memory requests and limits by creating and configuring limit range and pods in the namespaces. In this video, we'll describe the key features and differences between labels and annotations. Let's start by discussing features of labels. Labels are key value pair which can be attached to Kubernetes objects. Labels are used to specify identifying attributes of objects. But yes, we need to know that it does not directly imply semantics to core systems. Now, how do we create labels? To create label, you can use YML file or even Cube Ctl commands. And finally, you can use labels to attach arbitrary non-identifying metadata to objects. Now, let's take some examples of labels. And that we will do using a diagram which is currently displayed on the screen. First, we need to understand the convention, which is specified using the rectangular box at the left of the diagram. It indicates key/value. You can use environment as a key, which is specified below, environment : and then comes value, that is dev within double quotes, or environment : QA or environment : production. You can also specify release as a key, as it is indicated in the diagram on the left. You can also use app as a key. So you need to decide what you are going to use as key. After understanding key value pair, let's go and try to configure YML file and use the key value. In the current diagram at the right, you will have API version : v1, which indicates the API version of Kubernetes. Then you are using kind : pod, which specifies that you want to create pod object. Then you have metadata. In order to give a name to the pod, you are specifying name : label dash demo, and below name you are giving labels : which will create labels. Labels that we are specifying here are environment : production and app : nginx. And then it follows with specification of the container that will be initialized in pod, where in the current example name is nginx, image is nginx : 1.7.9, and ports binding has been specified as container port : 80. After creating the configuration file, you need to run the command that will read the configuration file and it will ensure that it creates the required labels. Now let's try to go through example of label creation using Cube Ctl, for which we need to write a command that starts with Cube Ctl, followed by space run, followed by space development, followed by space name, followed by space dash dash image equal to image name that you want to run, followed by space dash dash replicas equal to number of replicas, and then comes a space dash dash labels where you have to use equal to, and within double quotes you have to specify key value pairs by writing key equal to value, comma key equal to value. Now, key can be named as per your choice. Similarly, value. You need to decide the name of the key and name of the value before you execute the command. Now, what about annotations in Kubernetes? Annotations are something similar to labels, but it provides a place to store additional metadata for Kubernetes objects. We need to also understand that annotation comes with a different syntax, where annotation has optional prefix and name, which should be separated by a slash. Now let's go and see how to declare annotation. To do that, you need to create a manifest file, specify API version :v1, followed by kind :pod, followed by metadata :name. You have to give a name to your pod. Then you can go and you can specify annotations by using annotations : After specifying annotation : you'll be specifying annotation name, which is the key, value. It should be followed by spec of the containers that need to be created when pods are getting created. For containers in the current configuration, we have used name as nginx, image to be nginx :1.14.2, and final step is the ports binding. We have specified using ports : followed by container port :80. Most important line here is how we are creating annotation, and we can find that it is similar to labels. We have to use key value pairs. So this is how you will be able to provide identifications to your Kubernetes objects using labels and annotations. In this video, we'll demonstrate how to create deployments with labels and use Cube Ctl commands to modify labels and utilize label selectors to filter Kubernetes objects based on set of labels. Now let's try to understand what is role of labels. Labels in Kubernetes are key value pairs that are attached to objects. They are attached to labels in order to specify certain identifiable attributes of objects which are meaningful and are relevant to the users. But yes, we need to understand that they will not have any direct implication on semantics of the core system. In short, labels are attached to the objects at creation time. After attaching, you can modify it anytime using Cube Ctl commands. Let's go ahead and work with labels. To deploy Kubernetes objects with labels, we need to create a YAML file, which is one of the approach of attaching labels to the object. For example, we have created a file which we will open using command called sudo, followed by a space, followed by vi, followed by labels.yml. We'll press enter. Line number 1 is all about API version, which is specified using API version :v1, followed by kind of deployment, which is specified using kind : and we are going to deploy a pod. Line number 3 is metadata, where we are using name : followed by label example. All the labels can be defined under labels element, which is there in line number 5. For now, we have just declared one label where key is env and value is development. Followed by spec, where we are using spec : below spec : we have specified containers : and below containers : we are giving a name to the container, that is nginx, followed by the image, which is specified using image : nginx : 1.14.2. And then we are specifying ports in order to bind the container with a specific port by using container port :9000. After writing the configuration file, we'll save it and we'll exit. Now we need to go and we need to use Cube Ctl apply command in order to create the deployment. And that we will do by writing Cube Ctl, followed by a space, followed by apply, followed by a space, followed by -f, and we'll specify name of the file where we have our deployment configuration. After writing the command, we'll press enter. Once we'll press enter, we'll get notification that pod/label example is created. Now let's go and check out all the labels of the current deployment, which is pod. To do that, we'll write Cube Ctl, followed by space, followed by get, followed by pods, and we'll give a space and we'll specify a flag called show by using --show -labels, and we'll press enter. Once you'll press enter, it will show you certain details of pod, which includes name of the pod, what is the status, whether it is ready or not. If not, what is the status? It is container creating, restarts, 0, age, 33 seconds, and labels is what is given as env equal to development. So in the current pod, by using the command flag --show -labels option, will output the labels which are attached to the current object. Now we need to wait for some time in order to see the status of the pod, which should change to running. Let the container get created in the background. Now we'll see how to manage labels. To manage labels, first we will see how to add a label using Cube Ctl command, for which we'll clear the screen by writing clear at the command prompt. We have to write the command Cube Ctl followed by a space. We'll specify label. We'll write pods because we are going to add label to one of the pod. Name of the pod is label example, and give a space, specify key value. We have added a label called type, which is the key, equal to pre-production, which is the value, and we'll press enter. Once you'll press enter, you'll find that it has created the label. Let's go and check out now how many labels are there for the current pod deployment. And to do that, we will go to the prompt. We'll write Cube Ctl, followed by space, followed by get, followed by space, followed by pods, followed by a space, and then we'll specify --show -labels, and we'll press enter. Once you'll press enter, you'll find that the new label is added. Now let's go ahead and see how do we apply filtering using label. For example, assume that you have deployed multiple different pods, and in order to keep them in a group, you have specified same labels, that is type equal to pre-production. We'll be using type equal to pre-production label in order to filter, and to do that, we'll be using command called Cube Ctl, followed by space, followed by get, followed by pods, followed by space, and we'll use --selector in order to apply filtering. After specifying --selector, we'll give a space and we'll use the key, that is type, equal to pre-production, and we'll press enter. Once you'll press enter, it will show you all the deployments where you are using label combination of type equal to pre-production. Now let's go and change the type from pre-production to pre-deployment and press enter. Once you'll press enter, you'll find that it shows that there is no resource found in the namespace. Now let's go ahead and use a command called Cube Ctl, followed by a space, followed by label, followed by a space, followed by pods, followed by a space, specify name of the pod, which is label example, and now we are writing type equal to pre-deployment, and we'll press enter. Once you'll press enter, it will display you a message that it already exists, but you want to modify it. To modify it, you'll be using the same command, but at the end, you will give a space and you'll specify --override equal to true. Once you will write the command, you'll press enter, you'll find that now your label has been modified. This is how you can create deployment with labels and use Cube Ctl commands to modify labels and utilize label selectors to filter Kubernetes objects which are based on set of label. So in this course, we have examined how to install and configure Kubernetes tools, work with Cubeadm and Cube Ctl to create and bootstrap Kubernetes clusters, deploy applications, create namespaces, limit range and pods in namespaces, deployment with labels and modify labels and filter Kubernetes objects. We did so by exploring the lifecycle of a pod, the concept of workload in Kubernetes, and the built-in tools provided by Kubernetes that we can use to work with the Kubernetes. How to install and configure Kubernetes tools, along with how to create and bootstrap Kubernetes clusters using Cubeadm. How to configure Cube Ctl to locate and connect to Kubernetes clusters, along with how to use Cube Ctl in proxy mode to check locations and access REST API with HTTP client. How to create namespaces and how to configure the default memory requests and limits by creating and configuring limit range and pods in the namespaces. The key features and differences between labels and annotations, how to create deployments with labels, modify labels, and utilize label selectors to filter Kubernetes objects. In the next course, we will learn how to query the API authorization layer, enable the namespace lifecycle and limit ranger admission control plugins, create cluster roles, role bindings, and cluster role bindings from Kubernetes clusters, allow users to perform operations in Kubernetes cluster namespaces, and implement aggregated cluster role. In this video, we'll describe the concept of authorization in Kubernetes along with the authorization modes that are supported by Kubernetes API server. Authentication and authorization is an essential requirement. It helps us to guarantee security and also provide access to resources only to authorized users. Now let's try to understand authorization from perspective of Kubernetes. It is treated as a method that helps to regulate access to computer or network resources. We need to also understand that in Kubernetes, authorization uses rbac.authorization.k8s.io. This is what is used in order to implement authorization in Kubernetes from perspective of API. Apart from that, in Kubernetes, authorization is based on roles of individual users within an organization. And finally, we can say that authorization in Kubernetes works with existing organization-wide or cloud provider-wide access control systems. Now we need to understand what all are the different authorization modes that can be used in Kubernetes, and that we will do using a table which is currently displayed on the screen. First authorization mode is node, which is all about granting permissions to kubelets, which are based on pods they are scheduled to run. Second is ABAC, which defines access control paradigm, whereby access rights are granted to the users. Third is RBAC, which helps to regulate access to computer or network resources which are based on roles. And finally, we have webhook, which is all about injecting authorization details through HTTP callback. Now let's go through and understand node authorization operations and their details. There are three operations which are supported by node authorization mode. First is read, which is applied on resources like services, endpoints, nodes, pods, secrets, all the config maps, your persistence volume claims, as well as persistent volumes. Then comes write, which is applied on nodes and node status, pods and pod status. And third is auth related, which is all about TLS bootstrapping and use delegated authentication or authorization checks. Now what about ABAC authorization? ABAC authorization defines an access control paradigm where access rights are granted to the users using policies. There are certain essential attributes which helps us to define access control using ABAC. Some of them are versioning properties, spec property, non-resource matching properties, and read-only attributes. Then comes the most popular mode, that is RBAC authorization. RBAC is enabled by default and users start with no permissions. It means that permissions must be explicitly granted by an admin to a specific service or resources. Now we need to know that policies are critical for effectively securing cluster. Basically, RBAC model is based on three essential components. First is the roles, second is the cluster roles, and third is subjects. All K8 based Kubernetes clusters will create a default set of cluster roles that represents common division that user can be placed within. Now let's try to understand using a diagram which is currently displayed on the screen. We'll have clients. Clients will send the request as a user. In the diagram, we have user A, user B, user C, and user D. These are the service requests which will be made from the users. It will be intercepted by admin node manager, who will be checking the user permissions against request settings, and finally they will provide access to the requested resource. In case if permissions are not there, they will be denied access. And finally, how webhook authorization works. Webhook authorization causes Kubernetes to generate query outside REST service. Now there are two special admission controllers which will be used, and they are provided by Kubernetes API server. First is mutating admission webhook and second is validating admission webhook. Let's go ahead and see how webhook authorization is implemented. And that we will do using a diagram which is currently displayed on the screen. User will make API request. Once he makes API request, it will be intercepted by API HTTP handler. API HTTP handler will check for authentication and authorization. Then they will pass it on to mutating admission controller to check mutating admission webhooks. Post mutation, it will pass through object schema validator for validation. Once validation is done, it will be processed by validating admission controller. In short, you will have now validating admission webhooks which will be managed by validate admission controller. And finally, your request will be persisted to etcd cluster. So these are special admission controllers which we have specified that sends admission requests to external HTTP callbacks, and in return they receive admission responses. Now we need to know that if these two admission controllers are enabled, Kubernetes administrator can create and can configure an admission webhook in their clusters. So these are different ways in which you can implement authorization in Kubernetes by selecting the right authorization mode supported by API server of Kubernetes. In this video, we'll quickly recall the steps and stages to control access to Kubernetes API server with specific focus on authentication, authorization, admission control, and validation. Now let's try to understand role of Kubernetes API server by using a diagram which is currently displayed on the screen. Now client will be invoking the request. They'll be sending username, ID, and group. Along with that, they will also specify path, resource, verb, and namespace. Path, resource, verb, and namespace will be sent to admission. Username, ID, and group will be sent for authentication and authorization. Where authentication, which is there at the right hand side, will verify the username or service account which is known to the cluster. It will verify through password, token, or certificate that the entity has right credentials. Then comes authorization, where API server will evaluate what request is and it will use permissions to determine whether the request is allowed for the entity which has been already authenticated or it has not been allowed. And final step is admission, which will use the security context and admission controller and then process the authorized request on behalf of the entity that has requested and against the resource that is relevant to that particular request. Now let's go through steps and stages to control access, and that we will do using a diagram which is currently displayed on the screen. As the diagram indicates, Kubernetes authorize API request by using the API server. Now let's go ahead and see the authorization flow in order to intercept steps and stages. The client request is first authenticated. If the client is not authenticated, it will give a status indicating 401. But if he passes the authentication, it will go on to the second module, that is authorization. It's a vector that contains request path, resource, verb, and namespace. Authorization will authorize the user whether that user is having access to the requested resource or not. If not, it will give 403, which indicates forbidden. But if authorization passes, he'll be moving on to the next step, and that next step is admission controller. Now let's try to understand how do we integrate Kubernetes and LDAP. LDAP works as an Active Directory. That Active Directory will store all the credentials along with authorization details. Now, as the diagram currently displayed on the screen indicates that an engineering user or an administrator is placing some request to cluster master. That request will be authenticated. In order to authenticate, credentials will be verified against Active Directory. After verification is done and if it is successful, access to Kubernetes resources is made, where they can access resources like kubelet, containers, and container runtime, which will be present in worker node. Now we need to focus on Kubernetes admission controllers. They are plugins. An objective of these plugins is to enforce how the cluster is used. They work as a gatekeeper that intercepts API request and have control to change the request object or deny the request altogether. Now let's try to understand Kubernetes admission controllers and how they work using a diagram which is currently displayed on the screen. API request will be intercepted by API HTTP handler, then it will be passed on to authentication and authorization module. After authorization is successful, it will come to the first phase of admission, which is called as mutate phase or mutating phase. It will execute, followed by validation phase. These two phases will work using mutating or validating controllers or sometimes combination of both. Post-validation, request will be persisted to etcd and appropriate webhooks will be used in order to complete the admission process. This is how authorization, authentication, and admission works in order to ensure that right user gets access on right Kubernetes resource. In this video, we'll use Cube Ctl subcommands to query the API authorization layer and enable the namespace lifecycle and limit ranger admission control plugins. One of the objectives is to ensure that we are able to quickly query the API authorization layer. When we query the API authorization layer, internally it will use self-subject access review API that will help to determine whether the current user can perform a given action or not. It works regardless of authorization mode that you are using. It can be webhook, it can be RBAC, it can be ABAC, or it can also be node. This particular command has capability of quickly querying the API authorization layer. Now let's go ahead and use subcommand. Subcommand provided by kubectl to query the API authorization layer starts with kubectl. After specifying kubectl, will provide space auth, that is auth, followed by the flag which is space can-i. After specifying can-i, we are giving space and we are asking, do we have create privilege or not? After specifying the operation for which we are asking the privilege, we'll give a space and we'll write deployments. In short, it is asking, do we have create privilege on deployments or not? We'll press enter. Once you'll press enter, it will answer you. And current answer is yes. Now assume that you want to know whether you have authorization to create services in a particular namespace or not. For that, let's go and first see all the namespaces which are currently present in the cluster. And to do that, we'll be using kubectl, followed by space get, followed by space namespaces. We'll press enter. Once you'll press enter, it will show you various namespaces which are currently present in your cluster. Now let's go ahead and ask, do we have create deployments privilege in a namespace, say cube-public or not? To do that, we'll write the command which starts with Cube Ctl, followed by space auth, followed by space can-I, followed by space create, followed by space deployments, and after that we'll give a space and we'll write dash namespace, followed by a space and name of the namespace where you want to find out. We'll press enter. Once you'll press enter, you will get the answer. This is how you'll be able to use kubectl command in order to query authorization layer. Now, next task is to identify how do we turn on admission controller, which is managed by Kubernetes API server. Now let's go ahead and see what all pods are running. To do that, we'll write kubectl followed by space get followed by space pods and we'll press enter. Once you'll press enter, you'll find pods which are running in default namespace. Now where is our Cube API server pod? To do that, we'll clear the screen and we'll see where actually our pods are running, which are provided by Kubernetes cluster. To do that, we'll write kubectl followed by space, followed by get, followed by space pods, followed by space -n, followed by space, and we'll specify the namespace which is cube-system and we'll press enter. Once you'll press enter, you will get list of all the pods which are managing your Kubernetes cluster, and one of them will be Cube-API server followed by DNS of master. This confirms that you are there on the right system where you can configure admission controller. Now, in order to configure admission controller, we need to edit one file. Let's go and get into that file. To do that, we'll first clear the screen and we'll write vi followed by /etc followed by /kubernetes followed by /manifests followed by name of the file. Name of the file will be kubeapi server.yml. We'll press enter. Once you will press enter, you'll find specs. Under spec, you will have containers. Under containers, you will have commands. And you'll find that you have command where you can enable admission plugins. For now, we will locate line where it is specified -- enable -admission -plugins, which will be there under Cube-API server, present in command section. We'll go to that particular line and after equal to, we'll specify name of the plugins that we want to enable. We want to enable 2 plugins. We'll write the name of the plugins, which is namespace, lifecycle, followed by a comma, followed by limit ranger, followed by comma. And by default, it has no restriction plugin already added. After adding, we'll save by pressing escape WQ and we'll exit. Now you have modified your Cube-API server.yml. Let's go and apply the modification that is done. To do that, at command prompt, we'll write kubectl, followed by space apply, followed by space -f, followed by space and the path where you have your Cube-API server.yml file present. After writing the command, we'll press enter. Once you'll press enter, you'll find that it creates the required pod. This is how you will be able to enable the namespace lifecycle and limit ranger admission control plugins. In this video, we'll recall the prominent principles that can help and implement Kubernetes role-based access control. And for that, we will have a quick recap of authorization approach. There are 5 different approaches that can be implemented. And for each approach, you will have a decision source and specific usage. For example, if you have internal use, you can go with approach called node. In short, approach node, decision source is API server and usage is internal use. When you go and adopt ABAC approach, decision source is static files and usage is insecure and deprecated. So it is not preferred to use ABAC. Third is RBAC. Decision source is API objects. Usage is to provide credentials to users and administrators. Fourth approach is webhook. Decision source is external service, which will be RESTful, and usage is when you want external integrations. And finally, you have always deny and always allow. Decision source is API server, and typical use is testing, where always deny flag blocks all the requests and always allow flag allows all the requests. Now, what all are the critical elements of RBAC that we need to consider? First is the subject. It is the set of users and processes that you want to access the Kubernetes API. Second is the resources. These are the set of Kubernetes API objects available in the cluster. Third is the verbs, which indicates set of operations that can be executed to the resources. Now let's try to understand benefits of using principle of least privilege. There are three critical benefits. First is stability. Second is better security because you will have limited code. And third is simplified deployment. Now let's try to understand principle of least privilege using a diagram which is currently displayed on the screen. As we can see, various different circles with color codes. In the outermost ring, we have applications which should have least privileges to the resources. Then we are moving inside further device drivers and further kernel. As you move inside the system, your privileges should increase. Then only you will have access to resources. But when it comes to applications, you will always have the least privilege over infrastructure and architectural resources. Now, how do we implement RBAC in Kubernetes? Let's conclude it by creating a case study using a diagram which is currently displayed on the screen. Let's consider two essential requirements. First, team membership, and second, team duties. Kubernetes RBAC includes a special impersonate verb that can be used to allow subjects to acquire other Kubernetes users or group identity. And that's what is our objective. We have membership where we are using RBAC cluster role and cluster role binding that state that users who are allowed to impersonate their team's virtual user. As the diagram in the left indicates, membership where you have subject and you are using cluster role binding with a verb called can, and inside cluster role you have verbs, resources and resources names. Be careful because your verbs contains impersonate. Now resources will have team duties where RBAC role and role bindings can state which actual Kubernetes resources the team's virtual user can access. And that can be done by creating a relation between your role and role binding. Role binding, as we can see in the right, specifies subject, that is team duties, and it uses the subject name which has been applied as impersonate in cluster role. And finally, it gives access to resources specified in the role, which includes config maps and deployment. Apart from that, for each resource, there is a verb called list, get, watch, and for deployment, you have create and delete. This is how you can plan implementation of RBAC in Kubernetes using special verb called impersonate in order to delegate access to resources on basis of the verb. So these are prominent principles that can help and implement Kubernetes role-based access control. In this video, we'll recognize the features of the role, cluster role, role binding and cluster role binding objects of RBAC API that helps to implement role-based access control in Kubernetes infrastructure. Now let's go ahead and first list RBAC API objects. There are two critical objects. First is roles that will connect API resources and verbs. These can be reused for different subjects. We can also say that these are binded to one namespace, but we can deploy the same role objects in different namespaces. Now let's go ahead and understand what is role binding. Role binding will connect the remaining entity subjects which are not specified in roles. For example, if you have a role which already binds API object and verbs, we will establish which subject can use it. Now let's try to make an important note. For the cluster level, non-namespace equivalents are cluster role bindings. Now, how do we use roles and role bindings? To do that, let's explore two configurations, which are currently displayed on the screen. At the left, we have kind:role, followed by API version, and we are using rbac.authorization.k8s.io/v1beta1. Then we are giving name to the role by using metadata:. Below metadata:, we have name: ns-admin. Then we are specifying the namespace by using namespace:"test" and then some of the rules, which includes API groups, resources, and verbs. Now role is defined. Let's go and work with corresponding role binding. To do that, in the configuration which is there at the right, we are using kind:"role binding. API version is similar to API version of role. Then comes metadata, which will give name to your role binding object. We are specifying name: test-pods. And we are using same namespace by specifying namespace:"test. Then comes the subjects, which is not added in the role. Subjects, we are using kind:"user, name:"coddy, and then we are specifying API groups. After specifying API groups, we are using role ref. We are defining kind:"role and we are specifying name: ns-admin, which is the name of the role object created using the previous configuration that we discussed. And finally, API groups. This is how you will be able to define role and role bindings. Now let's visualize it using a diagram. We'll have user considered as subjects. Then comes role binding, and we are specifying role binding to be test-pods, which we have defined in the previous configuration, where we have specified subjects as kind:users and name as coddy. It will refer to role, which we have defined in the first configuration that we discussed as ns-admin. And this will provide information about API resources, which is pod, as well as operations, which are the verbs specified in configuration of role, which is list, get, and create. And all these will be there in a single namespace called test. Now let's go ahead and identify approach of defining rules in a role. To do that, we'll start with rules: in our YML configuration file. We'll specify API groups: followed by double quotes. Inside double quotes, we can specify a group. Then we have resources on which we want to apply the rule. We have specified pods within square brackets, which indicates the resource on which we want to apply the rule. Then we have verbs, which includes get, list, and watch. After verbs, we'll have API groups. We are specifying batch as well as extensions, which are part of internal Kubernetes API. And then we are specifying resources. We are taking jobs as resources. And then comes verbs, which are applied on jobs. They are get, list, watch, create, update, patch, and delete. So this is how you will be able to specify multiple rules while defining role. Now we need to discuss about cluster role and cluster role binding. Before we start, let's try to understand what is cluster role. A cluster role is typically a set of permissions which are assigned to resources within a given cluster. Cluster role binding grants the permissions that are defined in a role to a user or set of users. Cluster role binding will hold a list of subjects, which includes users, groups, or even service accounts. Apart from that, it will also have reference to role which is being granted. Now let's try to understand it using a diagram. When we say cluster role and cluster role binding, its scope is cluster. Resources are not namespaced. So we'll assume namespace 1, which contains role binding, which refers to role for a subject called user A. In namespace 2, we have role binding, user B, user C, and they refer to role which is defined in cluster role. And cluster role is referenced by cluster role binding. So typically when you want cluster scope, you will be defining cluster role and cluster role bindings. So finally, let's try to understand when to use cluster roles and cluster role bindings. There are three typical cases. First, when you want to give permissions for non-namespaced resources like nodes, or you want to give permissions for resources in all the namespaces of a cluster. And third case is when you want to give permissions for non-resource endpoints. So these are three critical cases when you will use cluster roles and cluster role bindings. So after discussing features of role, cluster role, role binding, and cluster role binding objects of RBAC APIs, will be able to decide what kind of objects will be used in order to facilitate implementation of authorization using RBAC API. In this video, we'll create a manifest file and use it to create a role in the default namespace and grant get, watch, and list access to pods. In order to create a role in the default namespace, we have to write a file which contains following details. In line number 1, we have to specify API version, followed by rbac.authorization.k8s.io/v1. We need to ensure that we are following YAML format while writing the configuration file. Second line is kind. We have specified it using kind:role. Third line is the name that we want to associate to role, and that we are doing by using metadata: namespace: since we want it in default namespace, we are specifying default, followed by name: we are giving a name to the role, and name that we have specified is pods role. Then comes the rules, where we have to ensure that we are able to grant access on pods, and that we will do by moving to resources, and within square brackets and double quotes we'll write pods. This indicates that we are going to apply this role on pods. And then finally comes what access we want to give. Before we go ahead and describe access types, we need to understand what is API groups. API groups indicates the core API group. After API groups, we have specified resources where we added pods within square brackets and double quotes. And now we will specify the verbs that provides access to pods. We want get access, we want watch access, and we want list access. And that's what we'll specify within square brackets, keeping each and every verb in double quotes, separating it with other verb using comma. So we have specified verbs within square bracket, get within double quotes, followed by a comma, followed by double quotes, within double quotes watch, followed by comma, followed by double quotes, and within double quotes list. You should not forget to close the square brackets. After writing the file, we'll save and we'll exit. To do that, we'll press escape, followed by :WQ, and we'll press enter. Now we are out of the file. Our objective is to create the role that we have specified. To do that, at the prompt, we'll write Cube Ctl, followed by space apply, followed by space -f, followed by space and name of the file that we created where we have defined the role and authorization on pods. We'll press enter. Once we'll press enter, we'll find that role is created. Let's go ahead and confirm by listing the role. To do that, we'll write Cube Ctl, followed by space get, followed by space roles, and we'll press enter. Once you'll press enter, it will list you what all roles are there currently present in your cluster. This is the first role that we created. This is the reason why it is listing only one role along with create date and time. This is how you will be able to write manifest file and use that file to create role in default namespace in order to grant, get, watch, and list access to pods. In this video, we'll create a file and use it to create a role binding in the default namespace in order to facilitate pod role to the users. Now let's try to understand primary objective of role binding. Role binding's objective is to grant permissions defined in a role to a user or a set of users. Typically, it holds subject. Now let's first go and see what roles we have created in our current cluster. To do that, we'll start writing Cube Ctl, followed by space get, followed by space roles, and we'll press enter. So now we have role called as pods role. Let's go and describe the role. To describe the role, we'll write Cube Ctl, followed by space describe, followed by space role, followed by space pods role, and we'll press enter. Once you'll press enter, you will get details of the role. And current role is applied on resource called pods, and verbs that are being used in order to assign privileges are get, watch, and list. Now we need to use this role in order to create role bindings, which will grant pods role to subjects or a group of users. To do that, let's clear the screen first. After clearing the screen, we'll open the file where we want to specify role bindings configuration. To do that, we'll write vi followed by space role bindings underscore c3 underscore va.yml. This is the file which we have created to bind role binding to a specific role, where role binding will contain details of the users who need to be granted access as per the role that we have seen in the previous step. Let's press enter and open it. First two line is all about API version. API version will be rbac.authorization.k8s.io/v1, and kind that we are going to use as role binding because we want to create a role binding object. Then comes metadata. Metadata name that we have specified as read-pods. We want this role binding to be present in default namespace. This is the reason why we have specified namespace : default. Then comes the main part, which is subjects. We have specified subjects kind to be user by specifying kind : user. Followed by name of the user, we have specified name : Coddy. Then we have specified API group, which we are specifying to rbac.authorization.k8s.io. And finally, we have to provide reference of role to role binding, and that we are doing by using role ref segment in our current YAML file. We are writing role ref : followed by kind : role, followed by name : pods role. You need to ensure that this name is the name of the role which you want to assign to current subjects, which are users or group of users. And finally, we are specifying API group, which is similar to API group of subjects, which is rbac.authorization.k8s.io. After writing the configuration file, we'll save and we'll exit. To do that, we'll press escape, followed by :wq, we'll press enter. So now we have configured role binding, which contains details of the subject and the role to which those users will be binded. Now let's go ahead and create role binding object. To do that, we'll write Cube Ctl, followed by space apply, followed by space -f, followed by space name of the file, which is role binding underscore c3 underscore v8.yml. We'll press enter. Once we'll press enter, we'll get a message that indicates that your role binding is now created. Let's go and describe role binding to see the details. To do that, we'll write Cube Ctl, followed by space describe, followed by space name of the role binding, which is read-pods, and we'll press enter. Once you'll press enter, it will show you the detail, which includes name, labels, annotations, followed by which role it has to follow. We have specified kind : role and name : pods role. Subjects, you have only one, that is user, and name is Coddy. This is how you will be able to create a file and use it to create a role binding in the default namespace in order to facilitate a specific role that you have created to the users that you have defined in role binding. In this video, we'll create a file and use it to create a cluster role in order to grant, get, watch, and list access to secrets object in any particular namespace and across all namespaces. Now let's go ahead and create a manifest file which creates a cluster role that can be used to grant read access to secrets object in any particular namespace or across all namespaces. Now we need to understand that cluster roles are not namespaced. They are applied at cluster scope. And this is the reason why we'll not be specifying namespace while creating cluster role object. Let's create a file and make entries in order to create cluster role first. And to do that, we'll write sudo followed by space vi followed by space cluster role c3_v9.yml. You can specify whatever name you wish to. After writing the command, we'll press enter. And we'll write certain lines in order to ensure that we are able to create cluster role in order to manage access to secrets object. Line number 1 and 2 of current YAML specifies API version and kind. We need to be careful when we are specifying API version. It should be rbac.authorization.k8s.io/v1. It should be followed by kind : and the object type that we want to create. We want to create cluster role, so we have specified cluster role. Next, third line is metadata, which has a property called name. We'll specify secret manager as name, and this name is name of the object which will get created of type cluster role. Then comes the rules, where we have to specify API groups. We haven't specified anything. We have kept double quotes. Then comes resources, and since we want to grant read access to secrets object, in resources within square brackets and double quotes, we have specified secrets. And then comes verbs, which will help us to bind operations to the resource. Operations that we are binding to resource called secrets is get, watch, and list. And that we have done by writing it in square brackets by specifying get, watch, and list within double quotes in square brackets separated by comma. Now, our cluster role configuration file is ready. Let's go and use it to create cluster role. To do that, we'll press escape followed by :wq. This will save and exit from the current editor. We'll press enter. In order to create, we'll be using Cube Ctl followed by space apply followed by space -f followed by space name of the file, which is cluster role c3_v9.yml in our case. We'll press enter. Once you'll press enter, you'll find that it has created cluster role whose name is secret manager. This is how you'll be able to define a file and write configuration to create cluster role that can manage operations on secrets objects. In this video, we'll create a manifest file to use it to create a cluster role binding in order to allow any user in the group manager to read secrets in any namespace. Scope of cluster role is cluster. It is not specific to a particular namespace. Now, in order to create subjects, we need to ensure that we are creating cluster role binding object and we are giving reference of cluster role. Let's go ahead and create a file in order to do that. We'll open a file by writing vi space cluster role bind c3_v10.yml. We'll press enter. Now let's start from line number 1 and understand what cluster role we are defining that we will use in cluster role binding. We are using API version and kind in first two lines in order to specify the version and kind of object, which is cluster role. Then we are giving name to our cluster role without namespace by just specifying name, and name is secret manager 1. Post that, we are specifying the rules in order to provide authorizations on resources. We are talking about secrets. So resources that we have specified is secrets. On secrets, get, watch, list operations need to be enabled, and that's what we have specified in verbs. After creating the required cluster role, we'll create cluster binding, for which we'll specify API version We need to ensure that API version of cluster role and cluster role bindings are similar. Then we are specifying kind to be cluster role binding. We are giving a name to cluster role binding, and that we are doing by specifying metadata. Under metadata, name that we are giving to cluster role binding is secrets bindings. Then we are specifying subjects, where we are specifying kind not to be a particular user but a group. And name of that particular group is manager. After specifying name, we'll specify API group, which should map to rbac.authorization.k8s.io. And finally, we need to specify the cluster role, which will tell cluster role binding that what subject will have what operational privileges over secrets object. And that we are doing by using role ref, specifying kind to be cluster role, name to be the name of the cluster role that we have defined in the first section of the current file. And finally, we are specifying API group to be rbac.authorization.k8s.io. This is what need to be specified in configuration file. Now you need to understand that after you create binding, you cannot change the role or cluster role that the current binding refers to. Whenever you will try to change it, you will get a validation error. So be careful, never change after you have created binding object using a particular role or cluster role. After specifying the configuration file, we'll come out of the file by pressing escape followed by :WQ, and we'll press enter in order to save and exit. And final step is to create cluster role binding object. To do that, we'll use Cube Ctl at command prompt followed by space apply followed by space -f followed by space name of the file which contains your cluster role binding details. After specifying name, we'll press enter, and you will get a message that indicates that your cluster role is created. Name of the cluster role is secret manager 1. Apart from that, it has also created secret bindings using cluster role that is created in first step. This is how you'll be able to create a file and use it to create cluster role binding in order to allow any user in the group manager to read secrets in any namespace. In this video, we'll work with Cube Ctl commands to get a list of existing roles, cluster roles, role bindings, and cluster role bindings from Kubernetes cluster. We need to first connect to master, and once we are connected, at command prompt we'll write Cube Ctl followed by space get followed by space followed by roles, and we'll press enter. This will give us what all roles are there in the current default namespace. We'll use the same command that starts with Cube Ctl space get space roles followed by space -- namespace. And we'll specify name of the namespace that is equal to C3 objects. And we'll press enter. Once you'll press enter, it will show you what roles are currently present in C3 objects namespace. This is how you'll be able to get roles in a specific namespace. Now, if you want to get all the roles from all the namespaces, you'll be using the command that starts with Cube Ctl followed by space followed by get followed by space followed by roles followed by space -- all namespaces. After writing the command, you'll press enter. Once you'll press enter, you'll get all the roles currently present in all namespaces in your current cluster. We'll clear the screen. Now, if you want to get cluster roles, you'll be using the same command with one difference. And that difference is you'll be using Cube Ctl followed by space get followed by space cluster roles. After writing the command, you'll press enter, and you will get all the cluster roles. Now, since scope of cluster role is not namespace, it is cluster, you will get all the cluster roles which are defined in the current cluster. You'll be using similar commands in order to get details of role binding. For example, assume that we want to get all the role bindings in a particular namespace. For that, we'll clear the screen. After clearing the screen, we'll write Cube Ctl, followed by space, followed by get, followed by space, followed by role bindings, followed by space dash dash namespace equal to C3 objects, which is one of the namespaces currently present in our cluster. We'll press enter. And you will get role bindings, which is present within a specific namespace. Now, after getting what all roles, role bindings, cluster roles, and cluster role bindings, you will like to get details. To get details, you'll write kubectl, followed by space describe, followed by space, followed by role binding, space, followed by role binding name, that is read dash pods. After writing the command, we'll press enter. Once you'll press enter, it will show you detail of a particular object. So you can use kubectl get followed by roles, cluster roles, role bindings, or cluster role bindings in order to get what all objects are present of specific type. If you want to know about a specific object, you can use kubectl followed by space, followed by describe, followed by space, followed by the object type, followed by the object name. This is how you will be able to use kubectl commands to get list of existing roles, cluster roles, role bindings, and cluster role bindings from Kubernetes cluster. And you can also use kubectl command with describe clause in order to get details of each. In this video, we'll create kubeconfig file to allow particular users to perform operations in a particular namespace of Kubernetes cluster. Let's try to take up a case study where we want to allow particular users to perform operations, and that too limited to a particular namespace. To do that, we'll be writing one configuration file, though you can split and you can write it in two configuration files as well. Let's go and edit the file. To do that, we'll write vi space followed by case underscore study c3 underscore v12.yml file. We'll press enter. Now we need to carefully visualize the file. When we write the file, first two lines will be API version and role. First, we need to create the role so that we can provide operations that a user can perform on a particular resource. To do that, we'll write API version followed by kind, which is role. Metadata will help us to specify namespace and name. Namespace that we are using is C3 objects, and name that we are giving to the role is pods role underscore n. Then we are specifying rules, which is all about what operations can be performed on what resources. To do that, we are starting with API groups, which is empty within square bracket and double quotes. Then we are going for resources. We are just taking one resource, that is pods. We are specifying pods within square bracket and double quotes. And finally, we are specifying operations using verbs. We have specified get, watch, and list within square bracket, and all these verbs must be present in double quotes separated with each other using comma. Using the role so that we can bind it to a particular user, and that user now will be able to perform operations on resources and verbs that are specified in the current role. To do that, we are using triple dash to separate first configuration with second configuration. And we are again starting with API version, kind. Kind now is role binding. We need to be careful when we are specifying metadata. We'll give a name to role binding and we'll specify the namespace. We are using the same namespace, that is C3 objects, followed by subjects whose kind is now user and name of the user is Cody. You can specify as many users as you want. And final line is API group, followed by rbac.authorization.k8s.io. Now we have created the required configuration file, which can be split into two files as well. After creating the file, we'll save and we'll exit. To save and exit, we'll press escape in VI editor followed by :wq and we'll press enter. So now we have configuration file ready. Let's first go and create a namespace. To create a namespace, we will write the command that starts with Cube Ctl, followed by space create, followed by space namespace, followed by space, and we'll specify the name, that is C3 objects. After writing the command, we'll press enter. Once you'll press enter, you will have the namespace called C3 objects created. After creating the object, you can create multiple different pods using deployments and replica sets. And then you can apply role and role bindings to have write operation privileges to user on those pods. To create role and role binding that is applied on namespace called C3 objects, we will write the command that starts with Cube Ctl, followed by space apply, followed by space -f, followed by space, and we'll specify name of the file, which is case_study c3_v12.yml. We'll press enter. Once you'll press enter, you'll find that required role and role bindings are created. And now these users will have access to conduct operations which are permitted in role in a particular namespace. This is how you can create kubeconfig file to allow particular users to perform operations in particular namespace of Kubernetes cluster. In this video, we'll create a configuration file to implement aggregated cluster role and use aggregation rule to define label selectors that the controller can use to match other cluster role objects. There will be several scenarios where you would like to aggregate various cluster roles into one combined cluster role. Internally, you will have a controller that will run as part of cluster master, that will watch for cluster role object using an aggregate rule set. Let's go ahead and configure a file to define a cluster role and then use aggregated cluster roles to show how actually rules can be shared. To do that, we'll write a manifest file, and to write a manifest file, we'll use vi editor on our terminal, followed by space, and we'll specify name of the file, which in our case is aggregate_role c3_v13.yml. We'll press enter. Now, first task is to define cluster role, which we have already discussed in video titled Creating Cluster Role. We are using same elements here to create a new cluster role, and we are giving a specific label that will be used in order to map. And that we are specifying under metadata colon. After specifying name to the cluster role, we are using labels. Label that we are using is aggregate:_true. Then comes rule of the current cluster role, which we are specifying using API groups, resources, and verbs. Resources contains collection of resources on which we want this cluster role to operate. They are pods and services. And finally, operations on these resources will be applied using get, list, and watch. Now our next task is to show how label selector matches and picks up the rule from one of the existing cluster role and aggregates it to the other cluster role. To do that, in the current file, we are creating one more cluster role by using -- to separate first cluster role configuration with the second. We are writing API version, kind, which is again cluster role, metadata, name, cluster role 2. Most important element in the current file is aggregation rule, which we are specifying along with cluster role selectors, where we are using match labels. We are specifying the same label that we have specified in the previous cluster, that is aggregate:_true. In short, it will use the previous rule and make it available in the current cluster role. Now let's go ahead and create. To do that, first we will save the file by pressing escape:\w, and we'll exit from the file by writing Q and pressing enter. Now let's go ahead and create aggregate cluster role. To do that, we'll write Cube Ctl, followed by space apply, followed by space -f, followed by space and name of the file, that is aggregate_role c3_v13.yml. We'll press enter. Once you'll press enter, you'll find that it creates cluster role 1 and cluster role 2. Let's go ahead and describe cluster role 2. To do that, we'll write Cube Ctl, followed by space describe, followed by space, followed by cluster role, and space name of the cluster, we'll specify cluster role 2 and we'll press enter. Once you'll press enter, you'll find that cluster role 2 now has the same verbs and same resources which are defined for cluster role 1. This is how you can utilize aggregated cluster roles in order to combine rules of cluster roles into a single cluster. So in this course, we have examined how to query the API authorization layer, enable the namespace lifecycle and limit ranger admission control plugins, create cluster roles, role bindings and cluster role bindings from Kubernetes clusters, allow users to perform operations in Kubernetes cluster namespaces and implement aggregated cluster role. We did so by exploring the concept of authorization in Kubernetes, the prominent principles and key components of RBAC API that we can utilize to plan and implement Kubernetes role-based access control, how to create files and use them to create a role binding, cluster role and cluster role binding in the default namespaces, how to work with Cube Ctl commands to get a list of existing roles, role bindings and cluster role bindings from Kubernetes clusters, how to allow users to perform operations in a particular namespaces of Kubernetes clusters using kubeconfig files, how to implement aggregated cluster role and use aggregation rule to define label selectors and match other cluster role objects. In the next course, we will learn to create load balancers for Cube API server and add control plane nodes, set up high available clusters with external etcd nodes, add additional control planes to clusters, install workers, and take snapshot with etcd ctl commands to restore clusters. In this video, we'll list the Cubeadm command and critical flags that can be used to manage Kubernetes cluster, Bootstrap clusters, join existing clusters, and manage tokens on running clusters. There are multiple different tasks that Kubernetes administrator has to take. In order to facilitate and simplify the way Kubernetes clusters can be managed, Kubernetes comes with a tool, and that tool is Cubeadm. Now let's try to understand some of the features of Cubeadm. First feature is it's a tool that is used for provisioning or creating the cluster. It also helps to define how Kubernetes cluster will bootstrap. In short, it is used for bootstrapping. Apart from that, Cubeadm also supports administrators to perform actions that are required to get minimum viable clusters. And finally, it's one of the tools that helps administrators to simplify creation of clusters. Now let's go and list certain Cubeadm commands. There are multiple different commands that helps to bootstrap, create, and manage clusters. We'll list certain commands using a table which is currently displayed on the screen. After preparing your systems and meeting all the prerequisites, you can use Cubeadm init command to bootstrap Kubernetes control plane node. Once you will bootstrap, your control plane node, which is the master, will facilitate you with the required assets that helps workers to join that cluster. And that's where comes role of Cubeadm join command, which helps bootstrap Kubernetes worker node and facilitates it to join the cluster. Many times you will be working on older versions of Kubernetes. Cubeadm provides a command that starts with Cubeadm upgrade that facilitates to upgrade Kubernetes cluster to newer version. Now what about configuration? Cubeadm provides a command called Cubeadm config that helps to configure cluster for Cubeadm upgrade. It means before you upgrade, you need to configure it. Then comes managing tokens, which will be used by workers in order to join control plane or master. For that, you have a command called Cubeadm token. Sometimes you would like to revert all the changes that are made on host. To do that, you can use Cubeadm reset command. Before you start working with Cubeadm, in order to know its capability, you would like to display version of Cubeadm. That you can do by using Cubeadm version. that prints Cubeadm version. And finally, you will have an interesting command that helps you to preview set of features that are made available for gathering feedback from community. And that command is Cubeadm space alpha. Now let's go and discuss essential phases of Cubeadm space init command. Now when you use Cubeadm space init command, internally it executes multiple phases. Let's go and try to understand what phases are there and what is relevance of those phases. And that we will do using a table that is currently displayed on the screen. Now when you use Cubeadm space init, internally it fires a command called preflight that runs all the pre-flight checks. Then comes kubelet-start, which writes kubelet settings and restarts kubelet, which takes responsibility of establishing communication. Third command that internally get executed as a phase is certs, which generates certificates that will be used by Kubernetes cluster. Then comes kubeconfig, where it will use this command in order to generate all kubeconfig files that will be used by control plane and admin kubeconfig file as well. Next is control-plane, which generates all the static pod manifest files which are required to establish control plane. Now for storage, it uses etcd command to generate static pod manifest file for local etcd. After etcd is configured and pods are generated, it calls upload-config command, which uploads all the currently used configuration for Cubeadm to config map for persistence. Now after uploading all the config in config map, it calls mark-control-plane, which marks nodes, identifying them as control plane. After mark-control-plane has executed, it calls bootstrap-token, which manages Cubeadm specific bootstrap token functions. And finally, in order to facilitate features of add-on, it calls add-on that installs required add-ons for passing conformance tests. Now let's go and see using a flowchart how Cubeadm init works, and that we will do using a diagram which displays working mechanism of Cubeadm init. As the diagram shows, when administrator uses Cubeadm-init command, first task is it auto detects the IP for API advertise address. Once it is done, it starts the kubelets, goes to pre-flight checks phase, generates a token and writes that token. After writing the token, it generates Kubernetes static pod manifest used by API server, controller manager, scheduler, and etcd. Now we need to know that it places them in /etc/Kubernetes in form of manifest files. Now all the static pod manifests are generated, post which it will go to next phase where it will generate certificate authority key. It will generate API server key and certificate, and it will also generate service account signing in keys. And all the generated assets will be stored in a directory that is present in /etc/Kubernetes/pki. Now all the assets related to certificate, key, and account signing keys are ready. It moves to next phase where it generates kubeconfig files for kubelet and administration, and it stores it in kubelet.conf and admin.conf file. Now you have admin.conf and kubelet.conf ready. It goes to next phase where kubelet watches the directory for pods to create on startup. Next phase after startup is completed, it goes to a phase where it taints the master node, and as it taints the master node, it might have created kube discovery deployment, which is waiting for it to become ready. And finally, it installs add-on components, which includes kube proxy, daemon set, kube DNS, and all this is done using API server. Once it installs all the add-on components, it indicates that now your cluster is initialized, and this particular phase of Cubeadm init ends. Now you have initialized your Kubernetes server. What need to be done on worker? As you initialize, the last statement which will be present on your console will be command that will help you to formulate joining mechanism for worker node. Now let's go ahead and see how Cubeadm-join command works. And that we will do using a diagram which is currently displayed on the screen. Now Cubeadm joins objective is to create kubelet.conf so that kubelet can establish a connection with API server. And in order to do that, it passes through various different phases, where first phase is obviously pre-flight checks. In short, it runs a series of pre-flight checks to validate the state of the system. Now, once validation passes, it starts the kubelet, downloads the root CA information from the API server. It uses the token to verify authenticity using the tokens. And once authenticity is positive, it creates cluster info discovery client, which it will request using IP address, port, and token of the master. Now, we have created cluster info that will help worker to discover the cluster. In next phase, it verifies signature. And it does it once it receives cluster info object. After verification of signature is done, it moves to next phase where it tries to establish connection with API endpoint. And once that connection is established, it creates a local key pair. It prepares a certificate signing request, which is called as CSR, and it sends that off to the API server for signing. And as soon as it is signed, it generates kubelet configuration. After kubelet configuration is generated, it moves to final step where it writes kubelet configuration to a specific file that is present in /etc/Kubernetes, and that facilitates to connect to API server. This is how your Cubeadm join works. Now, after going through various commands, as an administrator, we need to decide what Cubeadm command with the right flag can be used in order to complete the task. In this video, we'll recall the architecture of highly available Kubernetes along with the benefits afforded by multi-master high availability architecture. Let's try to understand what all are the different type of high-level architectures that we can build for Kubernetes clusters. There are two different ways in which we can derive architectures. First is single master configuration. In single master configuration, you'll find that your Kubernetes cluster consists of one master and multiple workers, where workers will directly connect to and communicate with the master's Kube API server. Second architecture that we can derive is multi-master configuration, where Kubernetes cluster will contain multiple masters and multiple workers. We need to understand one classic difference here, and that is workers will connect and communicate with any master's Kube API server using high availability load balancer. Now let's try to understand single master configuration using a diagram which is currently displayed on the screen. The master will be composed of K8s specification. They will have kube scheduler, etcd, and kube controller. These are three essential components to which Kube API server present in master will communicate in order to manage orchestration. Then comes worker. Worker will host kubelet, which will initiate communication with master. Other components which will be there in worker will be all the images which are used in order to build containers that will be managed by container runtime. So whenever there is request to manage containers, it will come from master through Kube API server. It will use kubelet in order to communicate it to workers. But yes, single master configuration have a serious disadvantage, and that is what happens if master is not available. It means if master is not available, it creates single point of failure in your architecture. And this is the reason why we don't consider single master configuration to be highly available. Now we'll also discuss about multi-master configuration, where you will have multiple masters. And communication between master and workers will be established using load balancer. Now, as we can see in the diagram, master has Cube scheduler, etcd, Cube controller. All the communication will be managed by Cube API server. Workers will contain images, container runtime, and containers. Now, in multi-master configuration, it is load balancer which will play essential role in order to establish communication between master and worker. Now, in the current case, if one master is not ready, other master will take over. Now, since single point of failure is absent from multi-master configuration, it is considered to be highly available. Now, what all are the benefits that we can realize if we are using multi-master? First benefit is it enables scalable and reliable container orchestration engine. It also ensures reliability by utilizing multiple masters as well as multiple workers. And finally, it operates according to a leader/follower pattern in order to identify the right master who will process the requests. Now, how do masters select the right leader? It does it by following a process called as master component leader election process. Now, let's try to understand diagram from right to left. Now, you'll find that both masters are in a state where they try to acquire lease. As a result of attempt to acquire lease, they will be executing main, which will initiate restart process. Now, at any point of time, you'll find that masters will have lease which they will acquire. And once they acquire the lease, they will initiate the process to renew the lease. So logic of leader election is masters will try to acquire lease and they will be successful only if the leader lease exists and the lease is not timed out and the leader lease holds identity to the self. And that's what is being explained using the diagram. So in order to acquire lease, master components must have the right state. And then they will process activities in order to acquire lease, renew lease, and once lease is acquired, they will be the new leader. This is how you'll be able to manage master, and internally Kubernetes multi-master configuration manages lead election process. In this video, we'll recognize the advantages and disadvantages of different approaches that can be adopted to set up high available Kubernetes cluster. There are two different approaches that we can adopt in order to set up Kubernetes HA clusters. First is with stacked control plane nodes and second is with external etcd cluster. In approach 1, which is with stacked control plane nodes, we get benefited because it requires less infrastructure. And you'll find that etcd members and control plane nodes are co-located in the same system. Whereas when you go with external etcd cluster, you will require more infrastructure and you will have control plane nodes and etcd members are separated and they are decoupled. So impact of failure on control plane nodes may not have impact over etcd cluster. Now let's try to understand what do we need to set up HA cluster. Most of the requirements are common whether you are going with stacked control plane nodes or you are going with external etcd cluster. For example, both of them needs 3 machines that fulfills Cubeadm's prerequisites or minimum requirements for master. You need 3 machines that fulfills Cubeadm's minimum requirement for workers in both the cases. You do need full network connectivity between all cluster machines in both type of clusters. You also need sudo privileges on all machines in both cases. You need SSH access from one device to all nodes in both cases. You need Cubeadm and kubelet installed on all machines. There is one extra requirement with external etcd cluster, and that is you need 3 additional machines for etcd members. Now let's go ahead and compare the approach. In order to compare the approach, first let's consider that when we use stacked control plane nodes, we'll be able to simplify the way we do setup It will have simple replication management, but it may run risk of failed coupling and it will affect the cluster's redundancy. But when you go with external etcd cluster, your setup becomes more complex because now you need to manage 3 extra nodes for etcd. You'll have complex replication management, but it facilitates better when it comes to managing risk of failed coupling, and you will also get benefit because it does not affect clusters redundancy. So depending on your need and evaluating advantage and disadvantages of these two approach, you can adopt the right fit that helps you to set up high available Kubernetes cluster. In this video, let's recall the topologies of stacked etcd and external etcd that are used to set up highly available Kubernetes clusters. Kubernetes can be set up using 3 different topologies. First, basic non-HA topology, which begins to spread out the roles by separating the worker node components from master nodes. Second is stacked etcd topology. In this topology, you will have distributed data storage cluster, which is provided by etcd, and that is stacked on top of cluster formed by node which are managed by Cubeadm that runs control plane components. And third is external etcd topology, where you can initialize an HA cluster with external etcd, where distributed data storage cluster will be provided by etcd as an external provider. It will not be on top of nodes that runs control plane components, rather they will be decoupled. Now we'll try to understand basic non-HA topology using a diagram which is currently displayed on the screen. Now in this topology, we'll have spread out roles by separating worker node components from the master components as it is displayed in the diagram. Now all master components like API server, Cube scheduler, and controller manager will run on a single master. However, you can have one or more dedicated nodes that will run the worker components as we can see in the diagram. This topology seems to be more fault tolerant than a single node cluster, but yes, it is still not recommended for production. Though it can handle greater workloads, but it is still not fault tolerant when it comes to Cube API server or etcd, without which clusters can't function. So as we see in the diagram, workers will communicate to API server and metadata will be provided to API server, which will be stored in etcd. Scheduler and controller manager will plan orchestration that will be completed by API server. Now let's go with the second topology, which is stacked etcd topology, where you will find multiple different control plane nodes. And each control plane node will run an instance of API server, controller manager, scheduler, and they will also have etcd on top of them. We will need a load balancer in order to facilitate implementation of multi-master, and load balancer will take responsibility of selecting the right master who can process the request invoked by worker nodes. Now let's try to understand third topology, where we will have external etcd topology. It is entirely similar to the previous topology as the diagram indicates, but yes, there is one small difference, and that difference is you will have etcd nodes externalized from control plane nodes, and this will facilitate in better high availability. So depending on fault tolerance levels that you expect from your architecture, you can select the right topology. In this video, we'll list the essential components of control plane along with their associated features. Let's go ahead and list control plane components and specify essential features afforded by them. First component is Cube-API server, and this component is used to expose Kubernetes cluster. Role of Cube-API server is to make your cluster available outside the cluster. Second component is etcd, which is distributed, highly available storage that follows key value mechanism. Kubernetes will use etcd to store cluster configuration. Third component is the manager, that is kube-controller-manager, which manages applications through various controllers provided by Kubernetes that operates on the general model of comparing the current status against a known specification. Fourth component is Cube Scheduler. We all know that primary objective of using Kubernetes is to implement orchestration feature. Kube-Scheduler has built-in logic for managing the scheduling of pods. And finally, we have Cloud-Controller-Manager, whose responsibility is to manage the controllers which are associated with built-in cloud providers. After going through various different components of control plane, let's go and try to derive features of each components. And we'll start with Cube API Server. First feature is it serves as the interface for all cluster communication. Second feature is it always uses a secure port. Third feature is it is responsible for API validation for all resource creation requests that are made using Cube Ctl or other interfaces that helps to interact with master. And finally, it can be communicated using two primary interfaces. First is Cube Ctl and second is REST API. Now, what about etcd? etcd is distributed, highly available key value data store that stores metadata of Kubernetes. It is used by Kubernetes to store cluster configuration that holds metadata and the desired and current state of all the resources, which includes deployments, services, roles, role bindings, and others. And etcd is one of the components that communicates directly with Cube API Server. Third component whose features we would like to discuss is Kube Controller Manager, whose responsibility is to manage applications through various controllers that operates on a particular model of comparing the current status against a known status. Second feature is it watches current cluster state, which is stored in etcd. There are multiple different controllers that helps Kubernetes to manage applications. Let's go ahead and list some of them. First is Node Lifecycle Controller. Second is Daemon Set Controller. Third is Deployment Controller. And fourth is Namespace Controller. These specific controller will manage node lifecycle, daemon sets, deployment, and namespaces. Now we'll talk about that component which facilitates in orchestration, and that component is Kube-Scheduler, which is considered as orchestration framework. It has built-in logic for managing the schedules of pod. There are various different factors that we need to consider because they will have impact over Kube-Scheduler. And first factor is app resource requirements. Second, resource availability across nodes. Third, identifying affinity labels. In short, you need to identify whether the pod spec has affinity labels requesting scheduling on particular nodes. And fourth is taints and toleration. You need to identify whether the nodes have certain taints, tolerations that are preventing them from being included as part of scheduling process. And finally, we'll discuss about Cloud Controller Manager, whose responsibility is to manage the controllers which are associated with cloud providers. They also take responsibility of abstracting resources which are offered by individual cloud providers like GCP and AWS. And finally, they provide a standard approach to map Kubernetes to different cloud providers in order to ensure that you have common experience of Kubernetes across multiple cloud providers. So after identifying components of control plane, we'll be able to write configurations in order to utilize cluster and its high availability features effectively. In this video, we'll create a load balancer for Cube API server and add control plane nodes to the load balancer. There are many different configurations that can be done for load balancers. In our case, we are using AWS in order to host our Kubernetes cluster. We need to ensure that in cloud environment, we should place all our control plane nodes behind TCP forwarding load balancers. This particular load balancer will take responsibility of distributing traffic to all healthy control plane nodes in its target list. Let's go ahead and create a load balancer and add all the control plane nodes in load balancer. To do that, we will launch AWS Management Console. Once landing page of AWS Management Console is launched, we'll go to EC2, which will be there under All Services, below Compute. Once you'll click on EC2, it will list you details of EC2 resources which are currently running. We have one load balancer here and number of instances are 9. We'll click on instances in order to explore how many instances of control plane node we are going to add to load balancer. We'll click on instances. Once you'll click on instances, you will get all the instances that are created keeping in mind Kubernetes cluster, which will be highly available. We have 3 HA workers. We have also 1 HA master and 1 HAS master and 3 etcd nodes. Now let's go ahead and create a load balancer. To create a load balancer, from the left navigation panel, we'll go to option called as load balancing. We'll have load balancer as one of the items. We'll click on it. Once you'll click on it, it will launch load balancer page where you have one of the load balancer which is created. Let's go and delete it and create a new load balancer. To do that, we'll select the load balancer that we want to delete. We'll click on actions and we'll click on delete. Ensure that you are deleting load balancer which you are not using. If your load balancer is being used by other nodes, ignore delete. We'll delete it to clean our existing VPC. Once you have deleted, you will be creating a new load balancer. To do that, you'll go to the top left of your content pane and click on Create Load Balancer. Once you'll click on Create Load Balancer, it will facilitate you 3 different types of load balancers that you can create. First is HTTP and HTTPS. It's typically used for application load balancing. Then you have Network Load Balancer, which has capability of TCP, TLS, and UDP. It is capable of handling millions of requests per second. And third is Gateway Load Balancer. Let's go and select Network Load Balancer. To do that, we'll click on Create button, which is there in Network Load Balancer card. Once you'll click on it, it will ask you name of the load balancer. Let's go and specify name as Kubernetes Load Balance. And you have to specify the port, which is typically listener port for load balancing. And we'll retain the default port, that is 80. Our next objective is to select availability zone. We'll select default VPC and 2 availability zones. After selecting at least 2 availability zones, we'll click on Next Configure Security Settings, which is a button present at the bottom right of your current page. Next comes Configuration of Security Group. We'll click on Next Configure Routing, which is a button at the bottom right of the current page. Now you have to go and you have to specify targets. We'll retain default. We'll just specify name to the target group. We have specified control planes. We'll click on Next Register Targets. Once you'll click on Next Register Target, it will show you all the instances which you want to be managed by the current load balancer that you have selected. We'll select all the instances that we want to be part of our Kubernetes cluster. In short, we will be selecting all the nodes that we want to be balanced by the current load balancer that we have selected. Next, we'll click on the button which is there at the bottom right, captioned Next Review. And finally, we'll click on Create button, which is there at the bottom right of your current page. It will create the load balancer successfully. Once it has created, we'll click on close. Once you'll click on close, you'll find that load balancer is created. You can go ahead and confirm the description of the load balancer, and most important description is the DNS name. This is the name which will be used when you'll configure your multi-master Kubernetes cluster. This is how you'll be able to create a load balancer which will be used by Cube API server and add control plane nodes to the load balancer. In this video, we'll initialize a stack control plane by applying CNI plugin and watch the pods of the control plane components. In order to initialize a stack control plane, we need to first ensure that our current control plane node is meeting all the prerequisites. First, it should be added to the load balancer target groups. Let's go and verify it. To verify, we'll go and we'll log into our AWS Management Console where we have created the load balancer and we have assigned the IP of current control plane node to it. To do that, we'll click on EC2, which will be present on AWS Management Console landing page. Under Compute, once you'll click on EC2, it will show you details of what all instances are there. You need to use left navigation pane and go to Load Balancing. Click on Target Groups. Once you'll click on Target Groups in left navigation pane, it will show you target groups that you have created earlier, which is already demonstrated in video titled Creating Load Balancer for API Server. We will click on Control Planes 1. Once we have clicked on it, it will show configuration page of your current load balancer. You need to click on Targets and confirm that your IP address on which you are going to install control plane is present. After confirming, our next objective would be to get the DNS of load balancer. To do that, from the left navigation panel, we'll click on Load Balancers, which is present under Load Balancing. Once you'll click on it, it will show you load balancers. Select your load balancer that you have configured for current Kubernetes cluster with multiple control planes. Copy DNS. Connect to the machine where you want to install control plane. After connecting, you need to verify whether load balancer is listening or not. To ensure that you are able to find out that load balancer is able to communicate with your control plane nodes, you need to use NC followed by space -v followed by space followed by the DNS name of the load balancer followed by space port, which is 80. We'll press enter. You'll find that connection is established. This confirms that your current node, which is going to be first node in your stacked control plane, is able to communicate to load balancer. We'll press Ctrl C and we'll write clear to clear the screen. Next, you have to verify whether Cubeadm and Cube Ctl tools are installed or not. To do that, you'll write Cubeadm followed by space version at the prompt. You'll press enter. Once you'll press enter, it will show you the current version of Cubeadm. Similarly, you will write Cube Ctl followed by space version and you'll press enter. You'll find that Cube Ctl is also installed. Now let's go ahead and clear the screen for now. After clearing the screen, we have to initialize the control plane. To do that, we'll be writing a command that starts with Cubeadm followed by space init, and you can specify space -- control -plane -endpoint followed by space, and you have to specify within double quotes DNS and port of your load balancer. To do that, we'll paste the load balancer DNS followed by colon followed by port, which is 80. After writing the command, we'll press enter. Once you'll press enter, it will start installing the components. Now this may take some time, but as the process ends, you'll find that you have your control plane added to your cluster. Now let's go ahead and connect to one of the nodes where we have installed control plane. Now once your control plane is installed, you would like to apply the CNI plugin of your choice. To do that, you need to ensure that you are aware about capabilities of CNI provider. Let's go ahead and install a CNI, which is Weave. To do that, we'll write Cube Ctl followed by space followed by apply followed by space dash F, followed by space, followed by the URL provided by the provider. After specifying the endpoint or the URL, you will press enter. Once you'll press enter, you'll find that it has created all the required services, which includes service account, cluster role bindings, role bindings, and one daemon set. Now let's go ahead and watch the pods of the control plane components. In order to do that, we'll write Cube Ctl, followed by space get, followed by space pod, followed by space dash n, followed by space cube dash system, where you'll have all the pods, followed by space dash w. We'll press enter. Once you'll press enter, you'll find weave dash net set of pods which are already installed. This is how you'll be able to initialize a stacked control plane by applying CNI plugins and watch the pods of the control plane components. In this video, we'll initialize a stack control plane by applying CNI plugin and watch the pods of the control plane components. In order to initialize a stack control plane, we need to first ensure that our current control plane node is meeting all the prerequisites. First, it should be added to the load balancer target groups. Let's go and verify it. To verify, we'll go and we'll log into our AWS Management Console, where we have created the load balancer and we have assigned IP of current control plane node to it. To do that, we'll click on EC2, which will be present on AWS Management Console landing page under Compute. Once you click on EC2, it will show you details of what all instances are there. You need to use left navigation pane and go to load balancing. Click on target groups. Once you'll click on target groups in left navigation pane, it will show you target groups that you have created earlier, which is already demonstrated in video titled Creating Load Balancer for API Server. We'll click on it. Once we'll click on it, it will show configuration page of your current load balancer. You need to click on targets and confirm that your IP address on which you are going to install control plane is present. After confirming, our next objective would be to get the DNS of load balancer. To do that, from the left navigation panel, we'll click on load balancers, which is present under load balancing. Once you'll click on it, it will show you load balancers. Select your load balancer that you have configured for current Kubernetes cluster with multiple control planes. Connect to the machine where you want to install control plane. After connecting, you need to verify whether load balancer is listening or not. To ensure that you are able to find out that load balancer is able to communicate with your control plane nodes, you need to use NC, followed by space dash V, followed by the DNS name of the load balancer, followed by space port, which is 80. We'll press enter. You'll find that connection is established. This confirms that your current node, which is going to be first node in your stacked control plane, is able to communicate to load balancer. We'll press Ctrl C and we'll write clear to clear the screen. Next, you have to verify whether Cube Ctl tools are installed or not. To do that, you'll write Cubeadm followed by space version at the prompt. You'll press enter. Once you'll press enter, it will show you the current version of Cubeadm. Similarly, you will write Cube Ctl followed by space version and you'll press enter. You'll find that Cube Ctl is also installed. Now let's go ahead and clear the screen for now. After clearing the screen, we have to initialize the control plane. To do that, we'll be writing a command that starts with Cubeadm followed by space init, and you can specify space dash dash control dash plane dash endpoint, and you have to specify within double quotes DNS and port of your load balancer. To do that, we'll paste the load balancer DNS followed by colon followed by port, which is 80. After writing the command, we'll press enter. Once you'll press enter, it will start installing the components. Now this may take some time, but as the process ends, you'll find that you have your control plane added to your cluster. Now let's go ahead and connect to one of the nodes where we have installed control plane. Now once your control plane is installed, you would like to apply the CNI plugin of your choice. To do that, you need to ensure that you are aware about capabilities of CNI provider. Let's go ahead and install a CNI, which is Weave. To do that, we'll write Cube Ctl followed by space apply followed by space -f followed by the URL provided by the provider. After specifying the endpoint or the URL, you'll press enter. Once you'll press enter, you'll find that it has created all the required services, which includes service account, cluster role bindings, role bindings, and one daemon set. Now let's go ahead and watch the pods of the control plane components. In order to do that, we'll write Cube Ctl followed by space get followed by space pod followed by space -n followed by space cube-system, where you'll have all the pods, followed by space -w. We'll press enter. Once you'll press enter, you'll find weave-net set of pods which are already installed. This is how you'll be able to initialize a stacked control plane by applying CNI plugins and watch the pods of the control plane components. In this video, we'll set up highly available cluster with external etcd nodes and add additional control planes to the clusters. Let's try to understand how do we set up highly available cluster with external etcd nodes. To do that, first we need to see configuration of our etcd cluster, get the etcd members URL, and then create a configuration file which will be used by Cubeadm in order to create highly available cluster, and finally using that cluster and the same mechanism that we have used to join multiple control plane nodes in the video titled Joining Multiple Control Plane of this course. Let's go ahead and first look at the configuration of our etcd cluster. To do that, we need to first connect to our etcd cluster and open the configuration file. To open the configuration file, we'll write vi followed by /etc followed by /systemd followed by /system followed by /etcd3.service. We'll press enter. Once you'll press enter, you will get a configuration file. We'll directly move to service block, and in service block, we will locate exec start. Once we are able to locate exec start, we will locate an element that starts with -- initial cluster, which has etcd1, etcd2, and etcd3. And for each etcd, we have an endpoint. Apart from that, we have -- listen -client URLs where certain URLs are specified. We'll capture these details and we'll save it. After capturing these details, we'll come out of the file by pressing escape followed by :q exclamatory mark. Now we are aware about IP and ports. We'll connect to the system where we want to install highly available cluster using etcd cluster. First, we'll create a file and we'll name the file as config.yml. We'll write vi followed by space config.yml. We'll press enter. Once you'll press enter, it will open a file where you will start with API version, which will be kubeadm.k8s.io/v1alpha3, followed by kind, which is now cluster configuration, followed by Kubernetes version will take stable, which will be the most recent stable version, followed by API server cert sans, which will have an IP that we are using is 10.10.40.93, and then we'll specify control plane endpoint. Our current control plane endpoint is specified with 172.31.61.128:6443. Then comes the etcd configuration, where we are specifying external to tell that we'll be using external etcd cluster. And then we are providing endpoints on each etcd cluster machine, you might have specified the port at which it listens. We are specifying https://172.31.78.37:2379 followed by two other endpoints of our cluster. These are the IP addresses that we have captured in step 1. Then comes the CA file. We are using CA file which is located at /etc/etcd/ca.pem followed by cert file and key file. You need to specify appropriate location of them. And then comes networking configuration where we are specifying pod subnet. We are taking 10.30.0.0/24 where 24 is CIDR. And finally, we are specifying API server extra ARGS where we are setting API server -count to be 3. This is how you will be able to create a configuration that uses external etcd cluster. We'll save and we'll exit. To do that, we'll press escape followed by :WQ. After doing this, you need to run Cubeadm. To run Cubeadm, you'll write Cubeadm followed by space init followed by space --config equal to name of the configuration file that you have created. Name is config.yaml. Once you'll press enter, and if all entries are fine and ports are open, you'll find that it creates a cluster where instead of using internal etcd, it will use external etcd. Once your cluster is created, you can generate or create token and use that token to join other control plane nodes using Cubeadm join command. This is how you can set up highly available clusters with external etcd nodes and add additional control planes to the cluster. In this video, we'll demonstrate how to install workers after bootstrapping a control plane and demonstrate the steps involved in manual certificate distribution. In order to ensure that we are able to join a worker to control plane, we need to first go to our control plane and find out how many nodes are there. To do that, we'll connect to control plane and we'll write Cube Ctl followed by space followed by get followed by space followed by nodes. We'll press enter. Once you'll press enter, it will show you how many nodes are there currently present, and one of them is master. Now let's go ahead and spin a new machine and prepare the machine so that it can join to existing control plane. To do that, we'll move to our worker node, and first task that we will do is to update the new system. We'll do that by writing app-get space update and we'll press enter. Once your system is updated, you need to install certain dependencies. We'll do that by writing app-get space install space -y followed by space followed by apt-transport-https. And if you feel that you don't have curl utility, you can also give a space and write curl. Press enter. Once you'll press enter, it will show you what all is already installed and what is installed with the current command. After installing all the dependencies, we'll write clear to clear the screen. Next, we have to go and we have to add the Kubernetes signing key on the new worker nodes. To do that, we'll write curl followed by space -s followed by space followed by https://URL of the signing key. After specifying the URL, we need to add a different command, and that we will do by adding a pipe symbol followed by space followed by apt-key followed by space followed by add followed by space followed by dash. We'll press enter. Once you'll press enter, you will get a message that indicates that everything is fine. In order to add the repository, we'll be using app-add-repository followed by the entry for the current Ubuntu version which you want to make as worker. After specifying Kubernetes URL for the repository, we'll press enter. Once you'll press enter, it will get added to Ubuntu repository. Now we need to go and install tools. To install tools which are required for worker, we'll be using apt-get followed by space followed by update, and we'll press enter. Once you'll press enter, it will download all the repository in the local system, and next we will be using apt-get install command to install all the dependencies. Let's clear the screen. After clearing the screen, we'll write apt-get space install space -y space kubelet space Cubeadm. We'll specify again a space and we'll write Cube Ctl followed by a space and docker.io, because docker.io will take care of containerization. We'll press enter. Once you'll press enter, it will start installing all the tools. Now we have all the tools installed. Let's go and enable Docker. But before that, we will see status of Docker. To do that, we'll clear the screen. After clearing the screen, we'll write systemctl followed by space followed by status followed by space followed by Docker. We'll press enter. You'll find that it is active and it is running. We'll press Ctrl C to exit. We'll clear the screen and we'll enable Docker service on the current worker node. And to do that, we'll write systemctl followed by space followed by enable followed by space Docker. We'll press enter. You'll find that it synchronizes and now Docker is enabled. We'll clear the screen. After clearing the screen, we'll test Cubeadm version. To do that, we'll write Cubeadm followed by space followed by version. We'll press enter. You'll find that it displays version. Ensure that version of Cubeadm on the worker is similar to version of Cubeadm on control plane node. Now let's move back to our control plane node. Now on control plane node, we will generate new join token using Cubeadm command. And to do that, at the prompt, we'll write Cubeadm followed by space followed by token followed by space followed by create followed by space followed by print join command, so that you get join command that you have to use on your worker. We'll press enter. Once you will press enter, it will show you Cubeadm join command. You need to copy it from the master. After copying it on the master, we need to go to worker node and paste it there. After pasting, we'll press enter. Once you'll press enter, it will start the joining process. In case if ports are not open, be careful, open the ports. Finally, you will get a message that indicates that node has joined the cluster. You'll go back to master and you will now write Cube Ctl followed by space followed by get followed by space followed by nodes. You'll press enter. Once you'll press enter, you'll find that the new node is added. To do that, we'll be on our control plane. We'll move to a folder which is present in etc Kubernetes directory. Let's clear the screen by writing clear. We'll move to the directory where all the certificates are stored. And to do that, we'll write cd space /etc/ Kubernetes /pki. We'll press enter. Once you'll press enter, it will take you to pki, which becomes now the current working directory. We'll write a command called ls and press enter. Once you'll press enter, you'll find all the certificate and keys are present in pki folder. Now there are various different mechanisms that you can use in order to distribute these keys. One of the approaches is to write a script. Let's go ahead and see a sample script that can be written in order to manually distribute all the keys to other control planes. To do that, we'll move back to home directory by writing cd space tilde and we'll press enter. We'll clear the screen by writing clear. We'll press enter. And now we'll write a file. Let's name the file as transfer certs. We'll press enter. After pressing enter, we'll write a small script where we'll specify user equal to. Assume that you want to transfer files to users called master user. After writing the name, you'll specify control underscore plane underscore IPs. And then you'll specify all the IP addresses. For example, we are taking dummy. You need to separate IPs of all control plane using a space. After writing IPs, you will be writing a small loop. For example, we'll write for followed by space host followed by space in space. We'll use the loop to iterate in control plane, which we have declared in line number 2. We'll specify $. We need to ensure that your looping variable is within curly braces. We'll put semicolon and we'll start the loop by writing do. So assume that we want to transfer ca.crt file. In order to do that, we'll be using scp followed by space followed by /etc/ followed by Kubernetes / followed by pki / followed by name of the file. After specifying name of the file, as specification of scp command says, you have to specify user@host. For now, we'll go ahead and we'll double quotes. Within double quotes, we'll specify $, followed by curly braces, and within curly braces, we'll specify user. After specifying user, we'll have another double quotes that will be for host. We'll specify $host. We can write as many as file transfers as we want. Separator of two scp would be colon. And finally, after writing all your scp commands, you will write done. You will save the file by pressing escape :wq and you will run the file. Once you will run the file with appropriate values of control plane IPs, host, you'll find that it has transferred the files to desired location. This is how you will be able to manually distribute certificates across multiple different control planes. In this video, we'll recognize the properties and roles of etcd in Kubernetes, along with concepts of leader election and the terms used by etcd-based cluster for leader selection. There are 4 essential roles which we expect etcd to play in cluster. And first is to safely store critical data for distributed systems. Second, to enable multiple functionalities for Kubernetes. Third, to ensure that it acts as a primary data store for configuration data, state and metadata. And finally, it should facilitate Cube Ctl commands to retrieve data and trigger value changes in etcd. Now, what all are the critical features of etcd? First, it's fully replicated. It means the entire store is available on every node in the cluster depending on the topology that you select. It assists high availability because etcd is designed to avoid single point of failure in case of hardware or any network issues. And third, it is reliably consistent because every read returns the most recent write across multiple hosts. And finally, it's fast and secure because it is benchmarked at 10,000 writes per second. Apart from that, it also implements automatic TLS with optional client certificate authentication. Now we'll try to understand leader election process, and that we will do using a diagram which is currently displayed on the screen. Now assume that a new etcd member joins the cluster with no initial data, and that's what is being initiated by using the first circle called member add, and he's considered as a follower. Now they will request all historical updates from the leader until it catches up to the leader's log. So follower, when he is added, he'll follow up the leader and he will try to get all the data which is present in leader's log so that he can be promoted as a leader. Now we'll take a scenario which is there at the extreme right of the diagram. We are assuming that leader fails. Now in case if leader fails, we need to have leader election process. As per that process, you'll find that a follower may experience election timeout and start a new leader election process as well. Finally, cluster with a new member is high risk because it may take some time for new member to get all the logs present, and this is the reason why one of the follower will be promoted as a leader depending on what is the sync between leader logs and follower logs. Once it is done, you'll find that the new follower who is added will be in sync with leader. Second scenario is leader isolation. Now, in a critical 3-node cluster, the leader nodes gets isolated. And let's try to understand it using a diagram which is currently displayed on the screen. At any given point of time, leader requires at least one active follower. It means you need to have 2 nodes which are active, including leader. But if we see the diagram, in the second diagram, we have leader that have no active follower within the partition. This scenario may occur because of lost quorum. And if that happens, then leader election will happen to elect a new leader itself. This is how you'll be able to identify role which is played by etcd in Kubernetes and identify leader election and leader isolation scenarios. In this video, we'll demonstrate steps to create a 3-node etcd cluster using the static bootstrapping mechanism. Now, there are different ways in which you can install etcd cluster. Let's try to adopt static bootstrapping approach of installing etcd cluster. Our first step should be to create 3 different instances which are going to be part of the same cluster. For example, we have created 3 instances and we have entered details of those 3 instances in every instance in a file called as hosts file. Let's go and edit the hosts file to see who all are going to be member of the current cluster. To do that, we'll write sudo at the command prompt, followed by space, followed by vi. Again, we'll give a space, followed by /etc/hosts. We'll press enter. Once you'll press enter, you'll find entries where we have specified IP addresses, followed by DNS names, followed by etcd1. Similarly, for rest of the 2 members, we have specified same details. You need to ensure that you are entering these details in etc/hosts file of every node where you want to install etcd to participate in etcd cluster. Let's exit from the current file by pressing escape followed by :wq enter. Now our next step is to download and install the etcd binaries on all nodes. So we need to log into each node and download the etcd binary archive. To do that, we need to write a command that starts with curl followed by space -s followed by space endpoint of etcd release. After specifying endpoint, we'll give a space and we'll use a pipe symbol in order to specify other commands. After pipe symbol, again we'll give a space followed by grep followed by space browser _download _URL. We'll give a space followed by a pipe followed by a space grep followed by space Linux-AMD64 followed by space pipe symbol followed by space followed by cut followed by space -d followed by space, and we'll use single quotes. Within that, we'll specify a single double quote followed by space -f followed by space 4, and finally we'll give a space followed by pipe and specify space wget space -qi space dash. After entering the command that will be used in order to download the right etcd binary, we'll press enter. Once you'll press enter, it will download. Let's go and confirm. We can confirm by writing ls. Once you'll write ls, you'll find that it has downloaded etcd version 3. We have downloaded it twice, so you have 2 copies here. Now we need to unarchive the file and move binaries to /usr/local/bin directory. To do that, we'll write tar followed by space xvf. Again, we'll give a space followed by etcd-v3.4.14 -linux-amd64.tar.zz, and we'll press enter.
Once you'll press enter, it will unarchive it. Once it unarchives it, you will move to etcd directory. To do that, you will write cd followed by space followed by etcd dash version details. You'll press enter. Once you are there in the directory, we'll clear the screen and we'll move etcd resources to /usr/local/bin. Let's go and write ls to see what all files are there. You will have etcd, you will have etcd ctl, which is the client, and certain MD files with documentation. Now let's move. To move, we will write sudo followed by space mv followed by space etcd star in order to ensure that all the files that starts with etcd are moved to /usr/local/bin. We'll specify a slash at the end and we'll press enter. Now we'll move out of the directory. To do that, we'll write cd followed by space followed by tilde in order to move to home directory. Now we are there at home directory. We can delete the ZZ file that we have downloaded. For now, we are not deleting it. Let's go and check etcd and etcd-ctl versions. To do that, we'll write etcd followed by space -- version and enter. It will show you the current version of etcd. We can also confirm that etcd-ctl is installed by writing etcd-ctl and we'll just press enter. Once you'll press enter, it will show you all the options that can be used with etcd-ctl. This confirms that you have installed etcd-ctl. You have to do this task on all the nodes. After completing this task on all the nodes, you'll come to next step, where you have to create etc directories as well as users. Before we do that, let's clear the screen. We'll write clear and press enter. Now we need to create etcd system user group. Now we need to create etcd system user as well as group. To do that, we'll write sudo followed by space followed by group add followed by space -- system followed by space etcd and you'll press enter. You'll come to next line without any errors, which confirms that your group is created. Similarly, we'll create user by writing sudo space user add followed by space -s followed by space /sbin /no login followed by space -- system followed by space -g followed by space etcd is the group followed by space etcd is the user. So now you have created the required group and user. You need to ensure that you are creating the same on rest of the nodes. Now it's time to create data and configuration directories that will be used by etcd. To do that, we'll write sudo followed by space mkdir followed by space -p followed by space /var /lib /etcd. We'll press enter. We'll create another directory by writing sudo followed by space mkdir followed by space /etc followed by /etcd. We'll press enter. After creating these two directories, we'll clear the screen. Now we have cleared the screen. We have to do this on all nodes. Now let's configure the etcd, and you have to do similar configuration on each nodes, for which on each server you have to save certain variables. First variable that you will save is int_name equal to within double quotes eth0. This is the name of your network interface that will be used for cluster traffic. After writing, we'll press enter. Now once we have set int_name, we need to set another important variable, and that variable is etc_host_ip. We'll write at the prompt etc_host_ip and we'll set it to internal IP address of specified network interface, and that we will do by using $ followed by opening bracket and within bracket we'll specify IP followed by space addr, followed by space show, followed by space $int underscore name. This is the variable that we have set earlier, followed by space pipe, followed by space grep, and followed by space within double quotes inet \b, followed by space pipe, followed by space awk, and will give a space. After space, will specify within single quotes and curly braces print, followed by space $2. After writing, we'll give a space, we'll use a pipe. Post pipe will give a space and will write cut space -d slash, followed by space -f1, and will close the bracket. After writing the command, we'll press enter. And third variable that we have to set is etcd underscore name, which is equal to dollar within brackets will specify host name, give a space -s. After writing, we'll press enter. And this activity again has to be done on all different nodes. Now, after we have set the required environmental variables, we need to go and we need to create etcd3.service system unit file. To do that, we'll write sudo followed by space vi followed by space /etc/systemd/system, and we'll name the file as etcd3.service. We'll press enter. Now, there are a couple of units that we need to specify in this. We'll specify unit which will contain 4 essential entries. First is description, second is documentation, and rest of the 2 are conflicts in order to avoid conflicts with etcd.service and etcd2.service. Next is the most important element where we are configuring service. Type is notify, restart always, restart seconds we are specifying as 25 seconds, limit no file we are specifying as 40,000, timeout start second we are specifying as 20 seconds, followed by environment file which we have specified to be available in /etc/etcd.conf. Then comes exec start, which is equal to certain directories which need to be started, and most important entries start from --listen-client-URLs, where you are specifying various different URLs that you want to be part of listen client URLs. Next is --advertise-client-URLs, where you are specifying the etcd host IP along with port and also the local host. Port that you are specifying here in all cases is 2379. Then comes --listen-peer-URLs, where you are setting up the first, that is http:// pointing to etcd_host_IP, which we have set in the previous step, followed by :2380 port. Next, we are again using --initial-advertise-peer-URLs, and we are specifying http:// with $, we are specifying the variable that we have set along with :2380. And then comes the cluster part, where you are specifying --initial-cluster and URL of etcd1, etcd2 as well as etcd3, followed by --initial-cluster-token, followed by space, followed by my-etcd-token, followed by space --initial-cluster-state with a space new. And finally, you are specifying install component, where you are specifying wanted by attribute to have multi-user.target. After creating the file, we'll save and exit. To do that, we'll press escape followed by :WQ. We'll clear the screen. Now, our next objective is to ensure that we are opening the firewall. To do that, we'll write sudo followed by space ufw, followed by space allow, followed by space proto, followed by space TCP, which is the protocol, followed by space from, space any, space to, space any, space port, space the ports 2379, 2380, or you can say 2379, 2380. We'll press enter. Now these ports are open. and rules are changed. You need to ensure that you are using the right command depending on your operating system to open these ports on firewall. Now we need to reload daemon. To do that, we'll write sudo followed by space system ctl followed by space daemon dash reload. You'll press enter. Once you'll press enter, you'll get a new prompt where now you have to write sudo followed by space system ctl followed by space enable followed by space etcd3. After writing the service name, we'll press enter and you'll find that you get a new prompt. You may get symbolic link created message also, and you will get a new prompt. Ensure that you are not getting error. This activity has to be done on all the nodes that you have configured to be part of etcd cluster. Our final step is to write sudo followed by space system ctl followed by space start followed by space etcd3. Once you'll press enter, you'll find that etcd3 cluster has started. You need to follow same steps on rest of the nodes as well. This is how you can create a 3-node etcd cluster using the static bootstrapping mechanism.
In this video, we'll recall the approaches of backing up etcd cluster that can be used to recover Kubernetes cluster under critical disasters like losing all master nodes. Now let's try to understand data protection ecosystem for Kubernetes. And to understand data protection ecosystem, we'll be using a diagram which is currently displayed on the screen. Let's go from bottom to top in order to understand level of data protection. Kubernetes Platform Data Protection provides you capability to implement local high availability within cluster and across fault domains. This is the first level, where you can add backup for offsite cluster protection. Then comes second level, which is backup and restore. You can have local HA with backup and restore offsite, where you can add disaster recovery for 0 or near 0 RPO and low RTO. And finally, you have disaster recovery, which is turned from RPO and RTO to secondary site. This is how you'll be able to derive the right ecosystem that need to be implemented for data protection in case of Kubernetes. Now we'll take up a scenario of backup and recovery that can be implemented for Kubernetes. Let's try to understand it using a diagram which is currently displayed on the screen. We'll have Kubernetes with 2 containers, Nginx and MySQL. MySQL is database and Nginx is web server. You will have various different Kubernetes objects that will facilitate in managing orchestration of your application along with database. So we'll have Kubernetes objects plus all the configurations which are specific to application. Application specific configurations will be binded to a volume. And finally, in order to implement backup, you can consider Kubernetes backup that must understand the semantics of what makes up Kubernetes application and create a copy in offsite storage. This is how you can plan building architecture for backup and recovery for Kubernetes. Now, what is disaster recovery? Similar to backup, you will have disaster recovery that also need to be considered. And for that, you need to come up with active and standby disaster recovery site. Let's try to understand it using a diagram which is currently displayed on the screen. We have active site, which is the primary site, where you have all the containers, pods, and Kubernetes resources running. You need to ensure that you are able to persist state to standby DR site so that whenever there is failure, it have transition from primary site to DR site. Now we need to understand that DR site must have capability to handle varying level of RPO and RTO. And it heavily depends on the cost and the business requirements. So depending on the cost and risk analysis, you'll be able to decide what should be the configuration of standby disaster recovery site. And finally, let's try to understand etcd backup mechanism, which can be used in order to implement backup in Kubernetes. There are 2 types. First, internal etcd cluster, It means you are running your etcd cluster in form of containers inside Kubernetes cluster, and it is the responsibility of Kubernetes to manage those pods. Second is external etcd cluster, which means your etcd cluster is running outside Kubernetes cluster. You need to provide its endpoint to Kubernetes cluster so that it can write the data. External etcd cluster is considered more highly available as compared to internal etcd cluster. So depending on your need, you can decide the right data protection level and identify the right mechanism to implement it in your Kubernetes cluster. In this video, we'll work with etcd Ctl commands to take snapshots from live members and use them to restore clusters. First task should be to get the cluster members. In order to demonstrate snapshot and recovery, we have created a cluster which is a single node etcd cluster. Let's go and see how to get list of all the members. To do that, at the prompt, we'll write etcd Ctl followed by space member followed by space list. We'll press enter. Once you'll press enter, you'll find the member, and this member is the default member running at a particular location. Now let's go ahead and clear the screen. If you are into multi-node etcd cluster, you will get multiple different members who are part of the cluster. Now we need to create a snapshot. Now, recovering a cluster first needs a snapshot of the key space from a particular etcd member. A snapshot may be taken from a live member using etcdl direct snapshot save command, or by copying member/snap/db file from an external data directory. Let's take an example. In order to create a snapshot, we'll write etcd Ctl followed by space followed by -- endpoints followed by space, and we'll specify the endpoint, which is 172.31.41.175. You have to assume that this is endpoint of a particular member. You need to give a space and write snapshot. After writing snapshot, give a space and write save, followed by space name of the snapshot. Let's keep it as snapshot.db. We'll press enter. Once you'll press enter, you'll find that it starts creating the snapshot. It will take some time for snapshot to get created. We'll press Ctrl C in order to end the process. We'll write ls and press enter. You'll find that it has created snapshot.db.part because it was still creating. It takes some time in order to create. Now we'll show what command we can use in order to restore. To restore, we'll write etcd Ctl followed by space followed by snapshot followed by space restore followed by space name of the snapshot. Once your complete snapshot is created, your name of the file would be snapshot.db. You need to write snapshot.db and press enter. Once you'll press enter, you'll find that restore initializes a new member of a new cluster with a fresh cluster configuration using etcd cluster configuration flags. This is how you'll be able to work with etcd Ctl commands to take snapshots from live members and use them to restore clusters. So in this course, we have examined how to create load balancers for Cube API server and add control plane nodes, set up highly available clusters with external etcd nodes, add additional control planes to clusters, install workers and take snapshots with etcd Ctl commands to restore clusters. We did so by exploring the architecture of highly available Kubernetes, the different approaches for setting up highly available Kubernetes clusters and topologies of stacked etcd and external etcd used to set up highly available Kubernetes clusters, how to initialize a stacked control plane, watch the pods of control plane components and join multiple control plane nodes in parallel using stacked control plane approach. The properties and role of etcd in Kubernetes along with the concept of leaders, elections and the terms used by etcd-based clusters for leader selection. How to create a load balancer for Cube API server and set up highly available cluster with external etcd nodes. How to create a 3-node etcd cluster, work with etcd Ctl commands to take snapshots and use them to restore clusters. In the next course, we will learn how to use Cube Ctl and Cubeadm commands to view a node status, set quotas for total amount of memory CPU that can run in a namespace, and upgrade Kubelet, Cube Ctl, and Cubeadm on the control plane and worker nodes. In this video, let's recall the key considerations for Kubernetes deployment and review the pros and cons of some of the best-known approaches to deploy Kubernetes. Let's try to understand certain essential considerations for Kubernetes deployment. First consideration is Linux is foundation to containers. In short, containers were first created in Linux, and the technology exists because it uses the key Linux subsystems. So when you deploy apps into containers, those apps are running on Linux. Second consideration is deployment maintains containers as the foundation for Kubernetes deployments. Third consideration is it builds portable and scalable critical workloads. Fourth is it ensures overall experience is the same across platforms. And this is the reason why we need to focus on having consistent Kubernetes implementation to ensure that overall experience is same, no matter which cloud environment your containers and Kubernetes are configured to. And finally, use Kubernetes API for orchestration, scheduling, and resource management capabilities. So these are primary considerations that we need to keep in mind before we go ahead and deploy. Apart from that, we do need to consider 3 essential considerations which indicates that deployment involves infrastructure, operations, applications, and enterprise architecture. So before you decide a Kubernetes implementation, you must identify and finalize infrastructure, operations, application, enterprise, its architecture, and the line of business group. You need to also ensure that you make Kubernetes easy for development team to use. And finally, always consider selecting the right partner to accelerate container adoption. After going through essential deployment considerations, let's go and try to understand various different approaches which can be used in Kubernetes for deployment. We can classify those approaches into 5 different types. Let's try to discuss it using a table which is currently displayed on the screen. First deployment approach is recreate, where we'll terminate the old version and release a new one. Second is ramped, where we release a new version on a rolling update fashion. Third is blue/green, which means we'll be releasing new version alongside the old version and then slowly switch the traffic. Then comes canary deployment approach, where we release new version to a subset of users and then do a full rollout. And finally, we have A/B testing, where we release a new version to a subset of users in a precise way. Now, finally, let's try to understand pros and cons of Kubernetes deployment approach in order to facilitate administrator to take the decision. And we'll discuss that using a table which is currently displayed on the screen. First approach is recreate. Process application state is entirely renewed, but you have a severe con, that is downtime dependent on shutdown and boot duration of the application. Then comes ramped. Process version is slowly released across instances. It is one of the convenient ways for stateful applications that provides capability to handle data rebalancing. This rollout, rollback can take considerable amount of time, difficult to support multiple different APIs, and you will have no control over traffic. Now comes blue/green. Process instant rollout or rollback. It avoids versioning issues and changes entire cluster state in one go. But you have cons from perspective of resource. You need double the resources Apart from that, you must do proper test of entire platform before you release to production, which takes time. And third, not efficient to manage stateful applications. In short, difficult to handle stateful applications if you have adopted blue/green deployment approach. Next is canary, process version release for a subset of users. One of the convenient ways for managing error rate and performance monitoring. And fast rollback. Cons is slow rollout, expensive to fine-tune traffic distribution if you have adopted canary. And finally, A/B testing. Process several versions will run in parallel. You will have full control over traffic distribution. But when it comes to cons, and if you are using A/B testing, it is hard to troubleshoot errors for a given session. Distributed testing also becomes mandatory. And finally, you will face con in case of A/B testing because it is not straightforward and you still need to set up additional tools. So after going through various different deployment strategies, you need to identify the right deployment approach, evaluating pros and cons of each. In this video, we'll demonstrate how to deploy Kubernetes cluster in the cloud and demonstrate how to connect and manage clusters. One of the ways in which you can utilize Kubernetes cluster is hosted environment. Various cloud providers will facilitate you to set up your Kubernetes cluster in simplified way. Let's go ahead and see how we can deploy Kubernetes cluster in cloud, and cloud that we are selecting is Google Cloud Platform. You need to log into your Google Cloud Platform by writing console.cloud.google.com in address bar of your browser. Once you will write, it will ask you credentials. You need to specify credentials, and once you have specified credentials, it will take you to landing page of Google Cloud Platform, where first task is to select the project where you want that cluster to be created. We have selected my project, which is visible on the top panel just beside Google Cloud Platform. After selecting the project, we'll go to search text field and we'll write Kubernetes. Once you will write Kubernetes, it will show you various different options. One of them will be Kubernetes clusters. So from drop down of your search, we'll click on Kubernetes cluster. Once you will click, it will take you to Kubernetes engine configuration dashboard, where if clusters are already there, it will show you the list, else it will give you a card with an option called Create Cluster. We'll click on Create Cluster button, which is there present on the card. Once you'll click on Create Cluster, it will launch configuration page where you have to specify configuration for your cluster. You need to specify name to the cluster. We'll keep the default. You need to select the location. We'll select zonal and keep the default zone. Next, you have to decide what version you want. You have two different type of releases, static version and release channel. Let's go and click on release channel. Once you click on release channel, it will provide you release channel where there are two different channels. One is regular channel, which is default. Second is stable channel. Let's keep the default. Next, you have to decide the version. Let's keep the default. After selecting all the options, you will go to the bottom panel where you will have a button called as Create. We'll click on Create. Once you'll click on Create, it will submit the request and it will internally start creating the cluster. We'll wait for some time for cluster to get created and initialized. Once it is created, you will get a green tick along with the details, which includes cluster size, total cores, and total memory. To connect, we'll click on Connect button. It will give us two different options in order to connect to the cluster. First, command line access, where we can configure Cube Ctl command line access by just running the command which is given below. That is gcloud followed by space container followed by space cluster followed by space get dash credentials followed by space cluster dash 1 followed by space dash dash zone followed by space us dash central 1 dash c followed by space followed by dash dash project and name of the project. Second option is Cloud Console Dashboard. Let's go and click on Open Workloads Dashboard.
Once you'll click on Open Workloads dashboard, you'll find various different type of workloads. In order to manage your cluster, you can use the left navigation panel where you can deploy a new workload by clicking on Deploy button, which is present at the top of your content pane just beside Refresh. We'll click on Deploy. Once you'll click on Deploy, it will ask you details of the container that you want to deploy. You can specify the containers. For example, we are selecting Nginx itself, which is default. You can add environmental variables. You can further add more containers and click on Continue button, which is there at the bottom of your current deployment. Once you click on it, it shows you details where you can manage labels. You can also go and view YAML, which is created by Google, and you can finally click on the button called Deploy, which is there present at the bottom of your current content pane. Once you'll click on Deploy, it will deploy your container depending on what image you have selected. Now, once it has deployed, it will show you the details of the container which you recently deployed. Similarly, you can go ahead and you can use left navigation panel in order to manage cluster and its objects, which includes services and ingress, applications, configurations, storage, as well as it helps you to migrate to containers. This is how you will be able to deploy Kubernetes clusters in the cloud and use appropriate option to connect and manage clusters. In this video, we will list the prominent infrastructure components that need to be provisioned to deploy Kubernetes cluster and their components. Now, what all components need to be provisioned? Let's try to understand so that we are able to build the infrastructure and provision various components of Kubernetes. First component is master, that receives all the input from CLI or user interface, passes it to API in order to complete the task. You can define pods, replica sets, and services that you want Kubernetes to maintain, and all that request will be made to master. Then comes worker. These nodes will listen to API server for any new work assignment. Once they receive it, they will execute the work assignment and then they will report back to Kubernetes master. Now let's quickly describe components of master. You can interact with master, as the diagram indicates currently present on the screen, using interfaces which can be GUI based or CLI command line. Those requests will be made using API. Those APIs will be intercepted using API server, which is the front end of master and only component in master to which we can directly interact. You'll have internal system components as well as external user components. And all communication that you will make to internal or external user component will be using APIs. You'll have other components as well as part of master, where key value store is facilitated by etcd cluster, which is a database used by Kubernetes to back up all cluster data. Then you'll have scheduler. Scheduler typically will watch for any new request that comes from API server and then it will assign them to healthy worker nodes. And finally, you have controller. The role of controller is to obtain the desired state again from API server, check the current state of the nodes and determine if there are any differences. If differences are there, it will resolve them as well. Now, after going through master components, let's focus on worker components as well, and that we will do using a diagram which is currently displayed on the screen. You'll be interacting with worker using Kubernetes master. Worker node will contain multiple different components, out of which most important components are kubelet, container runtime, and network proxy. Kubelet runs on every node in the cluster. It is considered as the main Kubernetes agent. When you install kubelet, you'll assign node CPU, RAM, and storage, and they become part of cluster. Container runtime objective is to pull images from container image registry and start and stop containers. And then you have kube proxy that makes sure that each node gets its IP address
And it does it by implementing local IP tables and rules to handle routing and traffic load balancing. We do have optional add-ons like DNS, which will facilitate in DNS resolution. All pods, which are currently displayed in the diagram, are considered as smallest element of scheduling that is managed by Kubernetes. Without pod, container cannot be part of a cluster. So if you want to scale your app, you can do that only by adding more pods to it. Finally, let's go and try to focus on architecture of runtime component. And we'll consider three essential elements. You'll have deployments, which helps us to manage scaling, updates, and rollbacks. Within deployments, you'll be defining pods, which are considered as smallest unit of deployment in Kubernetes. And pods will wrap up container, which contains application code and its dependencies. So whenever we are creating a deployment, it creates pod, and pod internally will hold containers which will have actual application code along with all its dependencies. So after going through various different components, we'll be able to decide our provisioning environment, which includes infrastructure as well as operating systems. In this video, our objective is to describe the features of nodes along with the recommended approach to provision and add nodes to Kubernetes clusters. Now, what are nodes? Nodes can be considered as worker machines in Kubernetes. They can have multiple pods. They are managed by the master, and they run kubelet and container runtimes. In short, we can consider node to be a worker machine in Kubernetes. They can be virtual, physical, depending on the cluster. Each node is managed by master. Node can have multiple pods, and Kubernetes master automatically handles scheduling the pods across nodes in the cluster. Now let's try to understand the architecture of node. Every Kubernetes node will run at least two essential processes. First is kubelet, whose responsibility is to enable communication between Kubernetes master and node. It manages pods and the containers runtime on a machine. Second process that need to be present is Docker or any other container runtime, whose responsibility is to pull the container images from registry, unpack the container, and run the application. Now let's talk about pod. Pod will contain containerized application as well as volume. Volume will store data, and containerized app will be application deployed along with dependencies, binded to a particular port in order to provide access to it. Now we need to understand available hardwares for nodes. You can have multiple flavors and isolation levels that are available for your nodes. Let's try to understand it using a diagram which is currently displayed on the screen. At the top, we have nodes which are built using physical machines. If you are using physical machines, it means you have to work on bare metal, and bare metal will be used in order to configure worker node, where every worker node will have pod. Inside pod you will have container, and inside container you will have app. In short, every worker node will be an independent physical machine. Now let's go through second hardware combination where we are using virtual machine. Now there are two different mechanisms as it is displayed in the diagram. First, you are using virtual machines on shared hardware. On top of shared hardware, you have hypervisor, and using hypervisor, you are creating multiple virtual machines where each virtual machine is being treated as a worker node, and worker node will facilitate to create deployments that will build pods, containers, and apps. So as the diagram indicates, we have three virtual machines which is there on shared hardware, and each virtual machine is being treated as worker node. As we can see in the diagram, we have worker node 1 and worker node 2. These worker nodes can be distributed to various customers. Now worker node 1 and worker node 2, which is there at the top, besides shared hardware, will be used by customer 1. It means one customer can have multiple worker nodes present on multiple virtual machines present on shared hardware where virtualization is managed by hypervisor. Customer 2 in the middle we can see is using only one virtual machine and he has only one worker node. Second approach of using virtual machine is to go with dedicated hardware. As we can see at the bottom of the diagram, dedicated hardware which is there on the right at the bottom will be powered by hypervisor. Using that hypervisor, you can create multiple virtual machines and each virtual machine can host worker node. These are different hardware combinations that can be used for node configuration. Finally, let's try to understand what if you want to manage nodes on cloud, and that's the reason it is called as cloud hosted nodes. Let's try to understand cloud hosted nodes using a diagram which is currently displayed on the screen. When we talk about cloud, we will be using certain extra components. As the diagram indicates, user will make request using Cube Ctl. That request will be received by API server. API server will take responsibility of communicating with scheduler, resource controller, and storage in order to complete the task. In cloud hosted, you will have zonal control plane, which will be using computing resources of cloud hosted in a particular zone. You'll be using cloud in order to create nodes where every node can have multiple user pods powered by containers. Benefit of using cloud hosted nodes is you'll be facilitated with ready to use cloud services provided by cloud provider. For example, at the extreme right of the diagram, we are able to see connected Google Cloud services. Now, these services are readily available to be used by cloud hosted nodes. They are VPC networking, persistent disk, load balancer, and stack driver monitoring. So depending on your need and availability and definitely considering cost, you'll be able to decide what combination of hardware fits for your node. In this video, we'll use Cube Ctl to view a node status and elaborate the fields of addresses, conditions, capacity, and allocations. Once you have set up your Kubernetes cluster and you have joined certain nodes to it, you would like to see what is the current status of those nodes. In order to do that, we can use kubectl commands. First kubectl command that I'll be using here will provide us information about status that is from perspective of Kubernetes environment. Let's go ahead and see how many nodes are there currently in our current cluster. To do that, we'll connect to master and at command prompt we'll write kubectl followed by a space followed by get followed by space followed by nodes and we'll press enter. Once you'll press enter, it will show you details of node where first information will be name, second will be status, third will be the role, fourth is the age, and finally you will have version. Our both nodes, out of which one is the master and other is the worker, are using the same Kubernetes version. Now let's go ahead and see the status that informs about current nodes. To do that, we'll be using kubectl command, and to do that we'll be writing kubectl followed by a space followed by describe and we'll write nodes. After writing kubectl space describe again a space and then nodes, will press enter. Once we'll press enter, it will show us the detail about the nodes. Now let's try to understand the details of information that we get when we use kubectl describe nodes command. Now most of the information that we will see here will be related to system resources, which are CPU, memory, as well as version information. The first line is the name. The second line is the roles. We can see none, which indicates that it's a worker. Third is labels which are associated with the current node. Fourth is annotations that are specified for the node. Fifth information is important, that is creation timestamp, which displays the time as well as the date when that particular node was created. Unscheduled, false, unattained. One of the important information that we can retrieve from the command is conditions. Conditions indicate whether there are system resource issues that will affect the running of the application. For example, we can see conditions, and under conditions we can see type, where we have memory pressure. Current value of memory pressure is false, which also indicates that your kubelet have sufficient memory. Next is the disk pressure, which is again false, which indicates that kubelet has no disk pressure. In other words, you have sufficient disk. Then you have the third element, which specifies condition of the process, which is indicated by PID pressure, which is again false, which means that kubelet has sufficient PIDs available. Then comes what is the current state of the node, which is indicated by ready. Value is true. It means that your node is ready and kubelet is posting ready state. Next information that you get is about address of the node, which includes internal IP as well as host name. And then comes the capacity section, where it shows what is the current capacity of your nodes, which starts with CPU, ephemeral dash storage, huge pages dash 1 GI, huge pages dash 2 MI, memory, and pods. You'll be able to understand what is the current capacity of your node. Then comes allocated resources, which indicates what amount of resource has been allocated, where the total limit may be over 100% as well, which indicates that it's overcommitted. Resources which are allocated include CPU. We can see it's in the current node, it is 100 M, which means 5%, and it also indicates the limit. Memory is 562 MI, 14%, and limit is also specified for that. Then you have ephemeral dash storage, huge pages dash 1 GI, and huge pages dash 2 MI. So by going through all these details, you'll be able to know what is the current allocated resource and what is the current status of the nodes. So by using these two commands, you'll be able to understand status of the node, as well as by going through various different fields, you'll be able to identify what is the address, what is the condition, what is the capacity, and what is the current allocations. In this video, we'll demonstrate how to use Cube Ctl commands to configure the default CPU requests and limit for namespaces. Now, before we start, we need to ensure that we have Kubernetes cluster up as well as Cube Ctl command line tool installed and configured. In order to confirm, we'll write Cube Ctl followed by a space and dash dash version. After writing version, we'll press enter. Once you'll press enter, you'll be able to see client version as well as server version along with their major and minor version details. We'll clear the screen. After clearing the screen, we'll first create a namespace. Objective of namespace is to ensure that you are able to divide a Kubernetes cluster into various namespaces. And it also provides you capability to configure namespace with the default CPU request and limits for a particular namespace. So let's go ahead and create a namespace first. To create a namespace, we'll be using kubectl command. Let's go ahead and write kubectl at the prompt, followed by a space, followed by create. After create, we'll give a space and we'll specify namespace because we are going to create namespace object. After writing namespace, we'll give a space and we'll write sample namespace. After writing sample namespace, we'll press enter. Once you'll press enter, it will show you a message indicating that your namespace has been created. Now, after creating namespace, before you go and create other objects within the namespace, you would like to create a limit range. To do that, we'll be creating a configuration file. To create a configuration file, at the command prompt, we'll write vi followed by a space and we'll give a name to the file called limitsdemo.yaml. We'll press enter. Once you'll press enter, it will launch your VI editor. You need to move to insert mode, and that you will do by pressing escape and I. Once you are there in insert mode, you will make some entries to your configuration file. But before that, you need to decide your limits. In the configuration file, line number 1 will specify API version v1 kind limit range. Then we'll specify metadata followed by a colon. Below metadata, we'll specify name followed by CPU limit range. You can give whatever name you want. After specifying name, you will start with specification by writing spec colon. Below spec colon, you will use limits followed by a colon. And then you will specify default. Followed by default colon, you'll specify CPU, which is the resource, (1), which ensures that you are able to provide default CPU limit of 1. Then comes the second limit, that is default request. Below default request colon, we'll be specifying CPU followed by 0.5, which is the default CPU request. And finally, you will specify type as container. After writing the configuration file, we'll save it. To save it, we'll press escape (WQ). After writing (WQ), we'll press enter and you'll find that your file is created and it is saved. Now let's go and apply the limit range that we created in limitsdemo.yml file to our namespace. To do that, we'll write Cube Ctl followed by space, followed by apply, followed by a space, and we'll specify -f. After specifying -f, we'll give a space and we'll give name of the file where we have configured limit for CPU as well as default requests. Finally, we'll give a space and we'll specify the name of the namespace on which we want to apply the current limits that we have set in limitsdemo.yml, for which we'll write --namespace equal to name of the namespace, and name of our namespace that we have created is sample namespace. We'll press enter. Once you'll press enter, you'll find a message that indicates that now your limit range, which is CPU-limit-range, is created. Now, if a container is created in sample namespace and you haven't specified any values to the container, specifically CPU request and CPU limit, the container will be allocated the default CPU request and default CPU limit that you have set in limitsdemo.yml file. This is how you'll be able to use Cube Ctl commands to configure the default CPU requests and limits for a specific namespace. In this video, we'll use Cube Ctl commands to set quotas for the total amount of memory and CPU that can be used by all the containers that are running in a particular namespace. In order to ensure that we are able to specify quotas, we need to use a Kubernetes object called as resource quota. Prerequisite of this particular video is you have a running Kubernetes cluster along with Cube Ctl installed. Let's go ahead and create a new namespace. To do that, we will connect to the master and we'll write Cube Ctl command followed by a space, followed by create, followed by namespace, and we'll give sample2 as the namespace name. We'll press enter. Once you'll press enter, you'll find that it creates a namespace. Now let's go ahead and configure resource quota object. And to do that, we need to create a manifest or configuration file. To create a manifest or configuration file, we'll be using VI editor, and to do that, we'll write VI followed by a space and we'll specify a name to it. We have specified name as quota-config.yml. We'll press enter. Once you'll press enter, you need to move to insert mode by pressing escape I. Once you are there in insert mode in your current VI editor, you need to write configuration. In line number 1, you will specify API version v1. In line number 2, you'll specify kind and kind of object that we are creating is resource quota. Line number 3 will specify metadata followed by a colon. Line number 4 will give a name to our resource quota object. And that we will do by writing name followed by memcpu. You can use whatever name you want. Line number 5 is all about specification, where we are using spec followed by hard and below hard we'll specify all our quota limits. First is requests.cpu:1. request.memory:1 GI, which indicates GB bytes, followed by limit on the CPU that we have specified by writing limits.cpu: followed by 2. And finally, we are specifying limits.memory: 2 GB bytes. Now our configuration is ready to create resource quota object. We'll press escape followed by :WQ to save and exit. After we exit, we need to create resource quota object using Cube Ctl command, specifying the configuration file that we have written in previous step. And that we will do by writing Cube Ctl followed by space, followed by apply, followed by space and -f. After -f, we'll give a space and we'll specify name of the file, which is quota-config.yml, where our configuration of resource quota object is written. And finally, we'll specify the namespace on which we want to apply this resource quota. To do that, we'll give a space after writing name of the file, followed by --namespace equal to name of the namespace, which is sample2. We'll press enter. Once you press enter, you'll find a message that indicates that your resource quota named memcpu is created. Now let's go and see the details of the resource quota object which we created. And to do that, we'll be using kubectl, followed by a space, followed by get, followed by a space, and we'll specify the object which we want to describe. After specifying the object, we'll give a space and we'll specify name of the object, which is memcpu. After specifying name, we need to also specify the namespace. To specify namespace, we'll give a space and we'll write --namespace equal to sample2. We'll press enter. Once you'll press enter, it will show you details of your resource quota, which indicates in the current case that every container must have a memory request, memory limit, CPU request, and CPU limit. For the current configuration, memory request total for all containers must not exceed 1 GB. Similarly, the memory limit total for all the containers must not exceed 2 GB. The CPU request total for all the containers must not exceed 1 CPU, and the CPU limit total for all containers must not go beyond 2 CPUs. This is how you'll be able to use kubectl commands to set quotas for total amount of memory and CPU that can be used by all the containers running in a particular namespace. In this video, we'll demonstrate how to use kubectl commands to set quotas for the total number of pods that can run in a particular namespace. To start with, we'll connect to the machine where we have kubectl installed. Once kubectl is installed, your first objective should be to create a namespace for the current lab. To do that, we'll go to the command prompt, and at command prompt, we'll write kubectl followed by a space, followed by create, followed by a space, followed by namespace, followed by a space, followed by a name that you want to give to current namespace. We have specified namespace as pod namespace. We'll press enter. Once you'll press enter, you'll find that you have created a namespace with the name pod namespace. Now let's go ahead and create the configuration file so that we are able to create resource quota object where we'll specify the total number of pods that can be created in the current namespace. To do that, we'll open a file by writing vi followed by a space and a name to the file. We'll give a name as podlimits.yml and we'll press enter. Once you'll press enter, it will launch the editor. You need to move to insert mode by pressing escape and I. We'll create the file where line number 1 is API version :v1, followed by kind : we'll specify resource quota. Next element in line number 3 is metadata, followed by :. Line number 4 is the name that we want to specify to the current resource quota object, which is pod limit range. After specifying the range, we'll use spec : and in the current resource quota, we are just setting up number of pods, for which we'll specify hard : and finally, in the last line, we'll specify pods : followed by the number of pods that we want. Current number is 2. We'll save the file by pressing escape key, followed by WQ. After specifying :WQ, we'll press enter and you'll find that you are out of the file. Let's clear the screen. Now our next objective is to use Cube Ctl apply command to create the resource quota object. And to do that, we'll write Cube Ctl at the prompt, followed by a space, followed by apply, space, followed by -f, followed by a space, and we'll use podlimits.yml file that we configured in the previous step. We'll give a space and we'll specify namespace. To specify namespace, we'll write --namespace equal to namespace that we created. After specifying the namespace, we'll press enter and we'll get a message that pod limit range is already created. Once creation is done, we would like to see the details of the resource quota. To see that, we'll write kubectl followed by a space, followed by get, followed by a space, followed by resource quota. We'll give a space, followed by name of the resource quota object, which is pod limit range. After specifying pod limit range, we'll give a space, we'll specify the namespace, and that we will do by writing --namespace equal to pod namespace. Because pod namespace is the current namespace on which we have applied the quota. And finally, in order to get output in form of YML, we'll give a space and we'll write --output equal to YAML. After writing the command, we'll press enter. Once you'll press enter, it will show you the current status. We'll directly go to the last 4 lines where we will see status as hard, pods:2, which indicates that this is what is the limit, and currently used pods are 0. Now let's go ahead and create a deployment. To do that, we'll clear the screen and we'll write ls in order to locate the file where configuration is written for a simple deployment. And name of the file is sampledeploy.yml, which is currently present in our examples folder. We'll open the file to see what is the current deployment settings. To do that, we'll write vi. We'll give a space followed by sampledeploy.yml. We'll press enter. Once you'll press enter, you'll find details where first line is API version, second line is kind. Now we are specifying kind to be pod. Apart from that, other details which are required for deployment. After specifying the deployment type to be pod, we'll save the file and we'll exit by pressing escape followed by : followed by WQ. Now we have seen our file which contains deployment of a pod. Now let's go ahead and create the deployment. To do that, we'll be using kubectl followed by a space, followed by apply, followed by a space, and we'll use -f. We'll give a space followed by name of the file, which is sampledeploy.yml in our case. Now this is the file which contains our deployment. Now let's go ahead and specify the namespace on which we have applied the pod limit in previous steps. To do that, we'll write --namespace equal to pod namespace. And after specifying the namespace, we'll press enter. Once you'll press enter, you'll find that it gives you a message indicating that pod test is created. Now let's go and view the details of the resource quota. To do that, we'll write kubectl followed by a space, followed by get, followed by a space, followed by resource quota, followed by space, followed by pod limit range, which is name of our resource quota object where we have specified limit on number of pods. We give a space followed by --namespace equal to pod namespace. We give a space and we'll specify --output equal to YAML. We'll press enter. Once we'll press enter, we'll directly go to the last 4 lines where now we can see that status is hard pods:2, which is the limit, and used number of pods is 1. Kubernetes will take care when you will create more pods to indicate whenever you will cross the range of the limits that you have set. This is how you will be able to use kubectl commands to set quota for total number of pods which can run in a particular namespace. In this video, we'll demonstrate how to use Cube Ctl commands to set minimum and maximum values for the CPU resources that are used by containers and pods in a namespace. In order to set minimum and maximum values for the CPU resources that you want to be used by containers and pods in a particular namespace, you have to create an object of type limit range. While creating object of type limit range, you have to specify minimum and maximum CPU values in its specification. Let's go ahead and create a manifest file where we can specify minimum and maximum values for CPU resources. And in order to do that, at the command prompt, we'll write vi followed by space followed by min max CPU dot YAML. We'll press enter. Once it launches VI editor, you need to move to edit mode by pressing escape I. And you need to write the configuration which starts with API version :v1 in line number 1. In line number 2, for kind, we'll specify limit range, and that we will do by writing kind : followed by limit range. Third line is metadata : fourth is the name that you want to specify to your current limit range object. We are giving it a name called min-max config. And then comes the specification which is specified in the current YAML file using spec:. Specification is all about limits, so we are specifying limits : followed by max : CPU : followed by 800M within double quotes. Min will specify by using min : followed by CPU : followed by 200M within double quotes, and then we'll specify type : container. After writing the specification, we'll save and we'll exit. To do that, we'll press escape key followed by : WQ and enter. So we have created the manifest file which will create the limit object. Now let's go ahead and create a namespace on which we will apply the current limit range. To do that, we'll be writing Cube Ctl followed by space followed by create followed by space followed by namespace followed by a space, and we'll write CPU sample as the namespace name. After writing namespace name, we'll press enter. So now we have namespace created, we have configuration file created. Let's go ahead and create the limit range, applying it on the namespace that we recently created. To do that, at the prompt, we'll write Cube Ctl followed by a space followed by apply followed by a space and -f. We'll give a space and then we'll specify name of the file, which is min-max CPU.yml. We'll give a space and we'll specify namespace. To specify namespace, we'll write --namespace equal to namespace that we created, and name of the namespace that we created for the current lab is CPU sample. After writing the command, we'll press enter. Once you'll press enter, you'll find that it has created limit range and it has specified name of the object as min-max config. Now let's go ahead and view the detail of the limit range that you have created. To do that, we'll write Cube Ctl followed by space, and we'll specify get after space, and then we'll give a space. We'll specify the object that we want to query, and object is limit range. After specifying the object type, we'll give a space and we'll specify name of the object, which is min-max config. And after specifying the name of the object, we'll give a space. We'll specify the namespace by writing --namespace equal to CPU sample. In order to get output in form of YAML, we'll give a space and we'll write --output equal to YAML. After writing the command, we'll press enter. Once you'll press enter, you'll find configuration of max, which is 800M, and min, which is 200M for CPU. This is how you'll be able to set the range of minimum and maximum CPU resource that can be utilized by pods and containers in the current namespace. In this video, let's describe the process of upgrading Kubernetes clusters that are created using Cubeadm. In order to upgrade cluster master, which are initialized and bootstrapped using Cubeadm, we need to follow certain process, which starts with logging into the first node and invoking Cubeadm upgrade command to it. Post that, you need to apply upgrade plan, followed by applying the upgrade plan to other master nodes in case if you have created multi-master architecture. Post which you have to verify upgrade plan. After verification is done, you need to update kubelet and restart the service. Once you have restarted the service, you need to upgrade Cube Ctl on all master nodes. So this is how you'll be able to upgrade Kubernetes cluster master. Once it is done, you need to focus on Kubernetes cluster worker. You need to upgrade that too. And you'll start by upgrading Cubeadm on the first worker node, then logging to master node and drain the first worker node. After draining, you need to upgrade kubelet config on worker node. After you have upgraded kubelet config, you need to upgrade kubelet on worker node and restart the service. Once service has restarted, you need to restore the worker node. You have to follow the same process for all workers. Now we need to focus on how to update the master node, for which first you need to discover what is the update type. There are two different update types, accordingly two different paths. First is major or minor. You need to discover what changed. If you are able to know what changed, you need to update your master in a test cluster, update all your configuration files, deploy it to a test cluster. Check if it is working fine. If yes, you need to update production master and deploy to production. Post that, again you will go ahead and update worker nodes. Finally, all the updates are applied. But if it is not working fine, you need to keep on updating your configuration files with the right configuration details. Now, in case if you are not aware about what changed, you need to write release note and keep discovering the change. Now, let's try to understand the second path, which is patch. If patch, no action needed because patches will update automatically and they will update all the worker nodes. Finally, we need to discuss how to migrate cluster resources because you will have now source cluster and then you will have destination cluster. In order to migrate your source cluster, which contains various applications and is on Gen 1 VPC infrastructure, it has various different open source projects to back up your VPC Gen 1 resources. And those open source projects are Velero plus Restic, which is being displayed in the diagram in source cluster. Now you will adopt app and persistent data migration approach, where you will migrate everything to destination cluster, which will have Gen 2 VPC infrastructure. It will again have open source projects called Velero and Restic to back up your VPC Gen resources, which is Gen 2 in destination cluster, and you will migrate all the apps from source cluster to destination cluster by restoring the resources from VPC Gen 1 cluster to VPC Gen 2 cluster. So depending on your need, identify your upgrade path and specify appropriate mechanism to upgrade your cluster from existing cluster configuration. In this video, we'll use Cubeadm and Cube Ctl commands to upgrade the first control plane node and the additional control plane nodes of Kubernetes cluster from version 1.18.x to version 1.19.x. We need to first ensure that we have Cubeadm Kubernetes cluster which is running version 1.18.x, where x can be 0, 1, 2, 3, 4. Now let's go ahead and check the version. To do that, at the prompt after connecting to master, we'll write kubectl followed by space cluster -info and we'll press enter. Once you'll press enter, you'll find that you have Kubernetes cluster running. Now let's go ahead and see what all are the versions of worker and the master node which are part of current cluster. In short, we will see what are the versions of control plane and the workers. To do that, we'll be using a command that starts with Cube Ctl, followed by space get, followed by space nodes, and we'll press enter. Once you'll press enter, you'll find that your current master is using v1.18.12 and worker is also running the same version. Now this confirms that your current Kubernetes cluster is using older version, that is version 1.18.12. Now our first objective is to ensure that we are able to control plane nodes. Process of upgrading control plane node is going to be similar. In order to start with upgrade, our first objective is to check what is the recent stable version which is currently present in apt-get repository. To do that, we'll be using a command that starts with apt-cache, followed by space medicine, followed by space Cubeadm, and we'll press enter. Once you'll press enter, it will show you all the different packages and its versions which are supported by the current build. And we'll move to the top and you'll find that your current version is 1.19.4. It means that your current apt repository has the desired version of Kubernetes as well, to which you will like to upgrade. Now let's go ahead and clear the screen. To clear the screen, we'll write clear. Now let's go ahead and get the nodes once again, because after ensuring that we have the right build, we need to drain the control plane node. And to do that, we'll write Cube Ctl, followed by space get, followed by space nodes, and we'll press enter. This will show us the name of the node. Our control plane node is IP-172-31-78-141. Let's go ahead and drain the current control plane node. To do that, we'll write kubectl, followed by space, followed by drain, followed by space, followed by the name of the control plane node. After specifying the name, we'll give a space and we'll specify --ignore -daemonsets. After writing the command, we'll press enter. Once we'll press enter, it will start evicting the pods. And finally, you will get a message that indicates that your control plane has been evicted. Now let's go ahead and run a command on control plane. An objective of that command is to derive the expected upgrade plan. To do that, at the prompt, after clearing the screen with clear command, we'll write Cubeadm, followed by space, upgrade, followed by space, plan, and we'll press enter. Once you'll press enter, it will run cluster health checks and it will fetch all the available versions to which you can upgrade. Once you get this message, we will do some installation in order to ensure that we have the latest version. To do that, we'll write apt-mark, followed by space, followed by unhold, followed by space, Cubeadm. Now we'll concatenate some commands in order to ensure that we are able to immediately update and install the desired version to which we want to upgrade. And to do that, we'll give a space, add && in order to add two commands, followed by space apt-get, followed by space update, followed by space, and again we'll use && in order to ensure that we are able to install the version to which we want to upgrade. Followed by space, we are writing apt-get, followed by space install, followed by space -y, followed by space Cubeadm equal to 1.19.4-00. And finally, we'll add && after giving space, followed by space, and we'll write apt-mark, space hold, space Cubeadm. After writing this command, we'll press enter. Once we'll press enter, now it will start installing the recent version of Cubeadm to which you want to upgrade. Final message that you will get is Cubeadm is set on hold. Now let's go ahead and verify Cubeadm's version. To do that, we'll write Cubeadm, followed by space version, and we'll press enter. Once you'll press enter, you'll find that now your version has changed to version 1.19.4. We can also confirm it by looking at major, which is 1, minor as 19. Now, once you are sure that you have the version to which you want to upgrade, we'll again go ahead and generate the upgrade plan. To do that, we'll write Cubeadm, followed by space, followed by upgrade, followed by space plan, and we'll press enter. Once you'll press enter again, it will run the cluster health check. Now you have to scroll bit up in order to see what is the current version of components. You will find that current version is v1.18.12 and available is v1.19.4. You can compare version of all the components which are currently installed and what is the available to which you want to upgrade. Now comes the command which will check your cluster and it will derive whether it can be upgraded or not, fetch the version you want to upgrade to, and it will finally show a table with the component config version states, and that's what we are able to see on the current screen. Now let's go ahead and use the command to upgrade, which is Cubeadm followed by space, followed by upgrade, followed by space apply, followed by space v1.19.4. We'll copy the command at the prompt and we'll press enter. Once we'll press enter, it will start upgrading the control plane. We need to wait for some time in order to complete the upgrade. Now it will ask you a message indicating are you sure you want to proceed with the upgrade. We'll press Y and press enter. Once it is upgraded, it will give you a message indicating success, your cluster was upgraded. This is how you will be able to use Cubeadm and Cube Ctl commands to upgrade the first control plane node, and you'll be using the similar process in order to upgrade additional control plane nodes with one difference. And that difference is instead of using sudo followed by space Cubeadm followed by space upgrade followed by space apply, which we have used for the first control plane, you need to replace apply to node. By using node instead of apply, you'll be able to upgrade all the control planes in your existing cluster. In this video, we'll demonstrate how to upgrade the kubelet and Cube Ctl on all control plane nodes of Kubernetes cluster from version 1.18.x to version 1.19.x. Now let's go ahead and upgrade kubelet and Cube Ctl on control plane. Similar steps will be applied on all control planes. To do that, we have to specify a command that starts with apt-mark followed by space unhold followed by space kubelet followed by space Cube Ctl followed by space $& followed by space app-get followed by space update, and then we will install the version to which we want to upgrade. To do that, we will write $& followed by space followed by app-get followed by space install followed by space -y followed by space kubelet equal to 1.19.4 followed by -00. Then we'll give a space and we'll specify version to our Cube Ctl as well, which is equal to 1.19.4-00. And finally, we'll specify $& in order to concatenate apt-mark followed by space hold followed by space kubelet followed by space Cube Ctl command. After writing the command, we'll press enter. Once we'll press enter, it will start executing the command, which will first unhold, then update and install the version of kubelet and Cube Ctl to which you want to upgrade. And final step after executing the command is to first clear the screen. After clearing the screen, we'll write systemctl followed by space daemon-reload. After writing the command, we'll press enter. Once we'll press enter, you will get the new command prompt. Once you get new command prompt, we have to restart kubelet. To do that, we'll write systemctl followed by space followed by restart followed by space kubelet. After writing the command, we'll press enter. Once you'll press enter, you will get the new prompt. Now let's go ahead and check the version of Cube Ctl. To do that, we'll write Cube Ctl followed by space version and we'll press enter. Once you'll press enter, you'll find that now new version is 1.19.4. You can confirm it by looking at major, and minor entries, which is 1 and 19. This confirms that your Cube Ctl is upgraded. Similarly, you can write kubelet followed by space version and you'll press enter. Once you'll press enter, you'll find that everywhere it is showing that all the components are upgraded to version 1.19.4. This confirms that your kubelet and kubectl are upgraded from previous version, that was 1.18.4, to new version, which is 1.19.4. In this video, we'll demonstrate how to upgrade the Cubeadm, kubelet and kubectl on all the worker nodes of Kubernetes cluster from version 1.18.x to version 1.19.x. This is continuation of the previous video where we have upgraded kubelet, kubectl and Cubeadm of control plane using video titled Upgrading Cubeadm and Upgrading Kubelet and kubectl on control plane nodes. Once it is upgraded, we'll go and we'll check the current status of the cluster. And to do that, we'll write kubectl followed by space get followed by space nodes and we'll press enter. Once you'll press enter, you'll find that your master's version is 1.19.4 and your worker, which is named as IP-172-31-79-90, is ready, but version is 1.18.12. Now we have to upgrade Cubeadm, kubelet and kubectl on all worker nodes of Kubernetes cluster. To do that, we need to connect to our worker node. Once we are connected to our worker node, we need to execute certain commands in order to ensure that we have the version to which we want to upgrade. To do that, first we need to patch Cubeadm on all worker nodes. Patching means upgrade. And to upgrade Cubeadm on worker node, we'll be using a command that starts with app-mark, followed by space unhold, followed by space Cubeadm, followed by space ampersand, followed by space app-get, followed by space update, followed by space $ampersand, followed by space app-get, followed by space install, followed by space -y, followed by space Cubeadm equal to the version to which you want to upgrade. We want to upgrade to 1.19.4-00. And finally, we are adding the last command by giving a space, followed by $ampersand, followed by space app-mark, followed by space hold, followed by space Cubeadm. After writing the command, we'll press enter. Once we'll press enter, it will call unhold Cubeadm, followed by update, followed by install of the new version and holding the Cubeadm. Once you get a message that Cubeadm is set on hold, your next task is to execute a command that uses a flag called allow changed held packages. To do that, first we'll clear the screen. After clearing the screen, we'll write another command, which is again app-get, followed by space update, followed by space ampersand, followed by space app-get, followed by space install, followed by space -y, followed by space allow change held packages, followed by a space Cubeadm equal to the version to which you want to upgrade, and that is 1.19.4-00. This will ensure that it marks the node as unschedulable as well as it starts evicting the workload. We'll press enter in order to execute the command. Now we can see that it gives clear message that Cubeadm is already the newest version. Our next objective is to go and drain the node. To drain the node, first we'll clear the screen. After clearing the screen, in order to ensure that we are able to make the current worker node unschedulable and evict all the workload as discussed earlier, we'll be using a command that starts with kubectl, followed by space drain, followed by space node name, and this name should be of your worker, followed by space --ignore daemon sets. We'll press enter after writing the command. Now let's go ahead and upgrade the kubelet and kubectl. Command that we need to write in order to upgrade kubectl and kubelet is app-mark, followed by space unhold, followed by space kubelet, followed by space kubectl, followed by space ampersand, followed by space app-get, followed by space, followed by update, followed by space ampersand, and then we are using app-get followed by space install followed by space -y followed by space kubelet equal to version to which we want to upgrade. In our case, it is 1.19.4-00 followed by space, and we'll specify Cube Ctl equal to 1.19.4-00. And finally, we will use app-mark after specifying ampersand followed by a space hold followed by a space kubelet followed by a space Cube Ctl. After writing the command, we'll press enter. Once you'll press enter, it will start the upgrade. And finally, you will get a message that indicates that kubelet is set on hold and Cube Ctl is also set on hold. Now let's go ahead and restart the kubelet. To do that, we'll write a command that starts with systemctl followed by space followed by daemon -reload. After writing the command, we'll press enter and we'll write final command. But before we write, we'll clear the screen by writing clear at the prompt. And we'll write the final command, that is systemctl followed by space followed by restart space kubelet. Once you'll press enter, it will restart the kubelet and you'll find that your worker has been upgraded to the version of your choice. You have to use similar commands in order to upgrade all the workers. Once they are upgraded, you have to bring node back online by marking it schedulable, and that you will do by using kubectl uncordon command. This is how you will be able to upgrade the Cubeadm, kubelet and kubectl on all worker nodes of Kubernetes cluster from version 1.18.x to version 1.19.x. So in this course, we have examined how to use kubectl and kubeadm commands to view a node status, set quotas for total amount of memory CPU that can run in a namespace, and upgrade kubelet, kubectl and kubeadm on the control plane and worker nodes. We did so by exploring the key features and recommended approach for provisioning and adding nodes to Kubernetes clusters, how to use kubectl to view a node status and evaluate the fields of addresses, conditions, capacity, and allocations, how to use kubectl commands to set quotas for total amount of memory, CPU, and pods that can be used by all the containers running in a namespace. The process of upgrading Kubernetes clusters along with how to use kubeadm and kubectl commands to upgrade the first and additional control plane nodes of Kubernetes clusters. How to upgrade the kubelet and kubectl on all control plane nodes of Kubernetes clusters. How to upgrade the kubeadm, kubelet and kubectl on all worker nodes of Kubernetes clusters. In the next course, we will learn to perform key Kubernetes deployment tasks, which includes implementing and updating deployments, diagnosing and managing pods, rolling back updates and deployments, scale stateful set, and set up autoscaler for deployments. In this video, we'll describe the key Kubernetes deployment strategy and specify the elements of the manifest file for each deployment strategy. Let's first try to understand what is Kubernetes deployment object. We need to manage Kubernetes objects, and that we can do by specifying deployment. Deployment can be used in order to deploy a replica set or a pod, where you can specify number of pods which must be available. Apart from that, you can also update pods and replica sets. Not only that, it also facilitates you to roll back to previous deployment versions because it maintains all the versions of previous deployments. And that is done in form of replica set resource. You can apply process of scaling up deployment as well as scaling down. And as an administrator, you will have full control to pause or continue deployment depending on your need. Now, what all are the different deployment strategies that we can adopt when we are working with deployment objects? There are three critical strategies. First strategy is rolling update strategy, which provides a controlled phased replacements of application pods. It also ensures that there are always minimum number of pods available. Second is recreate strategy, Recreate strategy typically removes all the existing pods before new ones are created. And in order to do that, Kubernetes will first terminate all containers from the current version, and then it will start all new containers simultaneously when old containers are deleted. Third strategy is ramped strategy, which involves rolling out version of an application in slow manner by replacing one instance at a time. Now let's try to focus on specific features which are provided by different deployment strategies. First feature of rolling update is its capability of controlled and phased replacement of application pods. It also makes sure that only 25% of pods are unavailable at given time. Apart from that, when you are adopting rolling update strategy, it will not kill old pods until enough are available. And finally, rolling update also allows you to control range of available and access pods. Now let's try to focus on manifest file, which is currently displayed on the screen, to understand how do we create it. While configuring your manifest file for deployment, you need to specify replicas. In the current case, replicas are specified to be 3. Then you will use a property called a strategy, which will have certain attributes. Now, when we go and specify type : rolling update, it means we are going to adopt rolling update strategy, where we have 2 essential properties of rolling update that we have to specify. First is max surge, which is equal to 1 in the current case, and then max unavailable, which is set to 0. Now, what all are the features of recreate strategy? First, recreate strategy helps you to adopt a strategy that removes all existing pods before it creates new ones. You will experience downtime, and recreate strategy will ensure that 2 versions are not running at the same time. Now, how do we specify it in manifest file? We do that by editing our existing deployment manifest file and specifying strategy type to be recreate instead of going for rolling update. Now, third strategy is implemented using rolling update. It is considered as a variation of rolling update. Critical feature of ramped is you'll find that secondary replica set is created with the new version of applications, and the number of replicas of old version is slowly decreased. When replica of old version is decreased in ramped, you'll find that replicas of new version is increased until the correct number of replica is reached. Now, how do we specify? We specify it by editing deployment manifest file, where we'll specify strategy type to be rolling update. And now if we see, we are updating max surge to be 2 and max unavailable to be 0. By making value of max surge to be 2 and max unavailable to be 0, we are setting up deployment strategy of Kubernetes objects to be ramped. Now you need to identify that in your scenario, which strategy works best. And it depends on scaling factor, how you want to manage rollback, and also availability of pods. The objective of this video is to recognize the workload resources that are used by Kubernetes to manage deployments and set of pods. Managing workload is one of the critical responsibility of Kubernetes, and that's the reason why it comes with orchestration capability, and it has an internal orchestrator to orchestrate workload. We can classify workloads of Kubernetes into 4 types. First is the deployment. These are typically used for stateless applications. Pods will be managed by deployment workload, and they are treated as independent and disposable. Second workload type is daemon sets, which ensures that every node in the cluster runs a copy of pod, typically used for collecting logs, monitoring nodes, checking the performance, and any work where background task is needed. Third workload type is stateful sets. It is similar to deployment with one difference, and the difference is deployments are stateless, but when you want to support stateful applications where you need to maintain identity and store data, you have to go with stateful sets type of workload. And fourth workload type is jobs. Primary objective of jobs is to launch one or multiple pods and ensure that the specified number of those pods are successfully terminated. So whenever you have need of finite task, jobs is considered as better option. Now, how do we configure workload types? We do that by creating manifest file. Let's go and try to understand how do we create Kubernetes deployment manifest file and what all are the critical entries. We'll start with selecting YAML format because that is preferred one. In the file, first line would be API version that should specify apps/v1. You need to specify kind to be deployment. Then you need to decide metadata, where you'll be giving a name to your deployment and also specify labels. We are specifying labels under metadata. First label is apps:mysampleapp. Second property under metadata, similar to labels, is name. Name is used in order to identify the deployment and do operations on deployment, whereas label is used in order to provide it an identity so that it can be used in order to get the object with a specific matching label. Then comes most important part, that is spec, where we specify replicas. In the current configuration, we have specified 3. We specify selector and use match labels to match one of the labels that you have defined. We are using app:mysampleapp. Apart from that, Kubernetes deployment will also have template where you are specifying metadata, picking up the labels, specifying app:mysampleapp, and then you are specifying specification of the container, which start with image, which tells which image need to be pulled, name, you are giving a name to your container, and container port to bind the existing container to a particular port. How do we define stateful set? We do that by creating a manifest file. And some of the essential entries in stateful set manifest file would be API version app/v1.0 followed by kind. Now, instead of giving deployment, we are giving kind to be stateful set. We are specifying metadata in order to give name to stateful set, and under spec, we are specifying service name. In the current case, service name is kstreams-count-service. Now, how do we create daemon set? For that, we need to create a manifest file where now API version will not be app/v1. It will be extensions/v1 beta 1 because it is part of extension API. Kind that you need to specify as daemon set followed by metadata in order to give it a name. Name we have specified as daemon set 1 test followed by spec, which contains selector. Selector internally will have match labels followed by name of the selector, that is daemon set 1. Next, you have to specify template where you'll have metadata, labels. To use the label, we are using name:daemon set 1 test followed by spec, which is the most important part of daemon set that specifies what is the image pull policy. Currently, it is set to always. The name of the container that you are specifying, which is Tomcat IMG, followed by ports. We are giving the port at which that container will listen. Container port is 80, protocol is TCP. What all resources you want. For now, we have kept resources to be empty. Then you are specifying termination message path, where message will be written when this current daemon set terminates. Finally, you are specifying the service account which will be binded with the current daemon set, which is default as of now. And last entry in the manifest file is termination grace period seconds, which is set to 10 for expiry. Containers contains image, which specifies Tomcat, which need to be pulled. This particular container has been set for an image called Tomcat. This is how you'll be able to create workload types which will be managed by Kubernetes. In this video, we'll demonstrate how to create a deployment that creates and brings 3 replicated pods and defines selection rules that help deployment find which pods to manage. Once you have your Kubernetes cluster up, you can deploy all your containerized applications on top of it. Assume that your developers have created a containerized application and now you are planning to deploy your containerized application on Kubernetes cluster. In Kubernetes, primary objective of deployment is to provide capability to configure updates for pods and replica sets. Let's go ahead and see how we can configure a deployment which uses replicas in order to create a replica set to bring up 3 pods of your desired application. In order to do that, we need to open a file for which we'll connect to our cluster, and at the prompt we'll write vi followed by a space followed by name of the configuration file where we will be writing configuration details for deployment. Now in the configuration file, you will start specifying API version followed by kind, which specifies type of resource that you are going to create. And this is the reason why in line number 2, kind : is specified as deployment. And that we have done by writing deployment just beside kind. Next, we have to define metadata which binds your deployment with a particular name. And this is the reason why in line number 3, we have specified metadata followed by name, where we are giving it a name called as web-deployment. Just below name, we have also specified labels. And labels that we are adding here is app : followed by nginx server. Next, we have to specify replication in order to create replicated pods. And that we are specifying in spec. Just below spec, which is there in line number 7, we are using replicas : and we are specifying number of replicas that we want. We want 3, so we have specified 3. Spec also has another element called as selector, which defines how the deployment finds which pod it has to manage. And below selector, we have specified match labels. Below match labels, we have specified property of match label, that is app : nginx server. And then we are specifying template, where we are giving pod a label, and that we have specified below template element in the current YAML file along with metadata : and just below metadata : we have specified a property called as labels : we are using as of now only one label, and that label is app : nginx server. And finally, we are creating a spec for specifying what is the type of resource that it has to create. And that we are specifying by writing containers, giving it a name, which is nginx container. We have specified that by using name : followed by name of the container, that is nginx container. Every container will be of a particular image, and that we are specifying with image : providing image name of nginx server, which will be pulled. And final element of the last spec have to bind ports to the container. As of now, we are using only one port, which we have specified using container port :80. Once you have created your configuration file and you have specified replicas, you need to save and exit from current file, for which you will press escape followed by :wq. We'll press enter. You'll find that file is saved and you are now on the new prompt where you have to create the deployment, and you will do that by running Cube Ctl command. Let's go ahead and write Cube Ctl followed by a space followed by apply followed by space followed by -f followed by a space followed by name of the file, which is deployment-config.yaml. Now let's go and press enter in order to create the deployment object. You'll get a message that indicates that your deployment object is created. Now let's go and check if the deployment was created, and if it was created, what is the current state. To do that, we'll write
Cube Ctl, followed by a space, followed by get, followed by a space, followed by deployments, and will press enter. Once you'll press enter, you'll find that it has created a deployment. Name of the deployment is web-deployment. Current ready state is 0 out of 3. Up to date is displaying the number of replicas that has been updated to achieve the desired state. And available displays how many replicas of applications are available for the users. And finally, age displays the amount of time the application has been running. This is how you'll be able to create a deployment which creates and brings 3 replicated pods and also defines selection rule that helps deployment find which pods to manage. In this video, we'll demonstrate how to update an existing deployment and use Cube Ctl command to view the deployments, its rollout status, and deployment update information. You need to first find out what updates you are going to make to your existing deployment. So let's go ahead and first describe one of the existing deployment that we have done in the previous lab titled Create a Deployment and Replica Set. And to do that, we'll connect to our cluster. At the prompt, we'll be using Cube Ctl, followed by a space. We'll use describe, followed by a space. We'll specify deployment, followed by a space and name of the deployment object that we created earlier. After specifying the name, we'll press enter. Once you'll press enter, you'll be able to see detail about the deployment that you have done in the previous lab of video titled Create a Deployment and Replica Set. Assume that we want to upgrade our NGINX image. To do that, we'll first clear the screen. After clearing the screen, we'll specify command kubectl followed by a space, followed by set, followed by a space, and then we'll specify what we want to update. We want to update image, so we are writing image, followed by a space, followed by deployment / web-deployment, where deployment is the object type, web-deployment is the name of deployment. We'll give a space and then we'll specify name of the container, that is NGINX container, equal to the new version to which we want to update it. And that is NGINX :1.16.1. We'll specify this value after giving equal to immediately after NGINX container. And finally, we'll give a space and we'll specify -- record. After writing the command, we'll press enter. Once we'll press enter, we'll get a message that indicates that web deployment image is updated. Now let's go and check out the existing deployment. And to do that, we'll be using a command called kubectl, followed by a space, followed by describe, followed by a space, followed by deployment, space, followed by name of the deployment, that is web-deployment. We'll press enter. Once we'll press enter, we'll find that now new image is updated and it is 1.16.1. This is how you'll be able to update the deployment using kubectl command. Now let's go ahead and view deployments and its rollout status. To view deployment, we'll first clear the screen and we'll write a command that starts with kubectl, followed by a space, followed by get, followed by a space, and we'll write deployments. After writing deployment, we'll press enter. Once you'll press enter, you will get what all deployments are there with 5 important properties. First is the name, second is the state, 3 out of 3 pods are ready, up to date 1, available 3, age is 25M, which indicates minutes. Now let's go and check out the rollout status. To check rollout status, we'll be using a command called kubectl, followed by a space, followed by rollout, followed by space, and then we'll specify status, followed by a space. We'll also specify deployment .v1.apps/web-deployment, where web-deployment is the name of the deployment. After writing the command, we'll press enter. Once you'll press enter, it will show you that it is waiting for rollout to finish, and it will also show you how many are finished. So in the current message, we are seeing that 1 out of 3 new replicas has been updated. You have to execute this command multiple times and wait for certain time until and unless you don't get message indicating 3 out of 3 new replicas has been updated. This is how you'll be able to view deployments, rollout status, as well as deployment update information. In this video, we'll describe how to use Cube Ctl rollout commands to inspect rollouts as they occur, pause and resume rollouts, to roll back updates, and to view an object's rollout history. Sometimes you may want to roll back a deployment, specifically in the case when your deployment is not stable and it is showing you status as crash looping. By default, you'll find that all the deployments rollback history is kept in the system so that it facilitates you to roll back any time you want. Now let's take up a case. Assume that you have made a mistake while updating the deployment and that you did by making a small typo in the image. Let's go ahead and first see what all deployments are there, and then we'll try to update with a typo. To see the deployment, we'll connect to the master, we'll go to command prompt and we'll write a command that starts with Cube Ctl, followed by a space, followed by get, followed by space, followed by deployments. After writing the command, you'll press enter. Once you'll press enter, you'll find your deployment. Now let's go ahead and update the deployment with a typo in the image. To do that, at the command prompt, again we'll write Kubectl, followed by a space, followed by set, followed by a space, followed by image, followed by a space, and we'll specify deployment.v1.apps/ name of the deployment, which is web-deployment. After writing name of the deployment that you want to update, you need to specify the property that you want to update. We'll write nginx container equal to nginx:1.171. Now this is a typo that we have created knowingly. Finally, we'll give a space. We'll write --record equal to true and we'll press enter. Once you'll press enter, you'll find the output which is similar to what we can see on the screen. That is deployment.apps/web-deployment followed by a space image followed by a space updated. Now let's go ahead and verify what is the status of rollout. To do that, we'll be writing Kubectl followed by a space followed by rollout followed by a space. We'll specify status followed by a space and we'll specify deployment.v1.apps/web-deployment, which is name of our deployment. We'll press enter. Once you'll press enter, you'll find that it shows it is waiting for rollout to finish. And it clearly indicates that 1 out of 3 new replicas have been updated. Now, we'll stop the command by pressing Ctrl+C. Now let's go ahead and see the number of old replicas and the new replicas. To do that, we'll write Kubectl followed by space, followed by get, followed by space and rs. After writing the command, we'll press enter. Once you'll press enter, you'll find that pods are created and you can see that one pod created by the new replica set is stuck and it is stuck in an image pool loop. We are able to see 3 because we have updated the deployments thrice. Let's focus on the second one, which is showing 98 seconds, which is the recent update that we have made. Now we'll go ahead and see the status of pods. You need to remember the name of the resource, which is web-deployment- followed by alphanumeric identifier. We need to focus on the entry which shows desired one and current one. This is what is the recent one, which can also be confirmed using the timestamp which is being shown below age, that is 98 seconds. Now let's go ahead and see the status of pods. To do that, we'll write Kubectl followed by space, followed by get, followed by a space, and then we'll write pods and we'll press enter. Once you'll press enter, you'll find pods status is image pull back off. It means that your new replica set for the current deployment is stuck in an image pool loop. Now what we need to do? In order to get the description of the deployment, we'll write
Cube Ctl, followed by space, followed by describe, followed by a space, and we'll write deployment. After writing, we'll press enter. Once you'll press enter, you'll be able to see the complete status of your deployment. Let's ignore this command and focus on checking the rolling history of a deployment. And to do that, first we'll clear the screen. After clearing the screen, we'll write a command called kubectl followed by a space, followed by rollout, followed by a space, followed by history, followed by space, followed by deployment dot v1 dot apps slash name of your deployment, which is web dash deployment. After writing the command, we'll press enter. Once you'll press enter, you'll find the status where you need to see change cause, which is copied from the deployment annotation internally managed in form of kubernetes.io/change cause to its revision, and it is specifically done upon creation. Now let's go and see detail of each and every revision. To see detail of each and every revision, we need to use a command which starts with kubectl. We'll write kubectl followed by space, followed by rollout, followed by space, followed by history, followed by a space. We'll write deployment.v1.apps slash name of the deployment, which is web dash deployment. After specifying the name of the deployment, we'll give a space and we'll write dash dash revision equal to 2 and we'll press enter. Once you'll press enter, it will show you the revision which is there, which specifies image to be nginx:1.16.1. This shows the revision which is specified correct. We'll go and we'll specify the same command with dash dash revision equal to 3 and we'll press enter. Once you'll press enter, it will show you the wrong one which you have actually specified in the last update. It means that all revisions are maintained. Let's go and check out revision 1 by using the same command by just changing dash dash revision equal to 1 and press enter. Once you'll press enter, you'll find that it is the oldest revision. Now our objective is to roll back to a previous revision. And as per our history query, we found that revision 2 is appropriate one. So let's go ahead and roll out to the previous revision, which is version 2. And in order to do that, we'll first clear the screen. After clearing screen, at the prompt, we'll write kubectl followed by a space, followed by rollout, followed by a space, and we'll use undo. Followed by a space, we'll specify deployment.v1.apps slash name of the deployment, which is web deployment. After writing the command, we'll press enter. Once you'll press enter, you'll find a message that deployment.apps slash web dash deployment rolled back. This is how you will be able to use kubectl rollout commands to inspect all your rollouts as they occur. You can pause and resume rollouts to roll back updates and also view the object of rollout history. In this video, we'll demonstrate how to use kubectl command to check the revisions of deployments and roll back deployments from current version to previous version. Sometimes as an administrator, our objective would be to review all the revisions of the current deployment. In short, we have to check the rollout history of a particular deployment. In order to do that, we'll first connect to Kubernetes Master. We'll go to the command prompt. And at prompt, we'll write a command called kubectl, followed by a space, followed by get, followed by space, followed by deployments. We'll press enter. Now this will show you the current deployment. Now assume that we want to check the rollout history of the current deployment, which is web dash deployment in our case. To do that, we'll be using a command that starts with kubectl, followed by space, followed by rollout, followed by a space. After space, we'll specify history. We'll give a space and we'll write deployment.v1.apps, followed by slash, followed by name of the deployment, which is web deployment. We'll press enter. Once you'll press enter, you will get the details of revision. We can see the revision and the change cause, which shows the command that was used in order to change the revision. Now our objective is to demonstrate how to roll back deployment from the current version to the previous version. Our previous version is indicated in the output of previous command is 1, 3 and 4. Now let's assume that we want to roll back to the previous revision that is indicated by 1 in the output of previous command. In order to do that, we'll write a command called Cube Ctl followed by a space, followed by rollout, followed by a space, and we'll use undo. After specifying undo, we'll give a space and we'll write deployment dot v1 dot apps slash name of the deployment, that is web deployment. After writing the name of the deployment, we'll give a space and we'll use dash dash 2 dash revision. Now using this, we can specify the revision number to which we want to roll back. We are writing equal to followed by 1. After writing the revision to which we want to roll back, we'll press enter. Once you'll press enter, you'll find that now your deployment is rolling back to the previous version. Now, in order to check if the rollback was successful and the deployment is running as expected, you need to give some time. And after you give some time so that task can be completed in the background, you'll write a command that starts with kubectl followed by a space, followed by get, followed by a space, and you'll specify deployment, followed by a space, followed by name of the deployment, which is web deployment in our case. We'll press enter. Once you'll press enter, you will find a message that indicates that your deployment is ready, 3 of 3, up to date 3, available is 3, as well as age, which indicates that now you have rolled back to the version of your choice. This is how you'll be able to use kubectl command to check the revisions of deployments and roll back deployments from current version to previous version or to any version of your choice. In this video, we'll recall the different states of deployment lifecycle along with the characteristics of each state. Let's try to understand various different lifecycle states of deployment. First state is pending, which indicates that pod is accepted by Kubernetes system, but its containers are yet to be created. Second is running, which means pod is scheduled on a particular node and all its containers are created and at least one container is in running state. Then comes the third state, which is succeeded, which indicates that all containers in the pod have exited with status 0 and further they cannot be restarted. When it comes to failed indicates that all containers of pod have exited and at least one container has returned a non-zero status. And finally, crash loop back off. We need to be careful with this particular state because it indicates that container fails to start and it tried again and again. Now, what about deployment lifecycle and participants who are going to participate in deployment lifecycle? To do that, we'll be using a diagram, which is a state chart diagram currently displayed on the screen. At the top, we have the participants. They are API server, etcd, scheduler, kubelet, and Docker. User will invoke a request to create pod. API server will intercept it and it will write it to etcd. Once it is written, task of scheduler starts, which will watch new pod, bind the pod, and once it is binded, it will write the status to etcd. Once status is written, it goes to kubelet, where kubelet will watch for the bound pod and talks to the Docker daemon using the API over the Docker socket to create the container and update the pod status back to the API server. And finally, API server will update the status to etcd using write. And this is how deployment lifecycle works with participation of various different objects. Now we'll discuss on state transition. How actually we have transition from one state to other state. container construction starts by pulling the image from container runtime. As it is indicated in the diagram currently displayed on the screen, it will first download using Docker pull. Once image is downloaded from registry, it will invoke Docker create, where it will keep the state to be blocked. Once create has executed successfully and all the dependencies are satisfied, state moves to pending. Now from pending, it has to go to start state, which is done by invoking Docker start command on Docker container runtime with appropriate throttling policy. Now once it is created, it indicates that live probe has reported it OK and it is in ready state, means it is ready to be served. Else, if Docker start fails, state will be failed, and one of the reasons why it moves from starting to failed is times out. And finally, let's try to understand pod lifecycle event generator, whose responsibility is to adjust the container runtime state with each matched pod level event and keeps the pod cache up to date by applying all the changes. Let's try to understand the process using a diagram which is currently displayed on the screen. Activities start with API server request, which can be request for a resource using file or HTTP. And now those changes will apply changes to pod spec, which will be committed to kubelet, and kubelet will send it to all the workers. In response to workers notifying container runtime either to create or to kill, container will take responsibility of completing the task of creation or killing the container. All the workers will update pod cache, and that particular cache will be managed by pod lifecycle event generator, who will continuously probe pod events to kubelet. We do have upstream container state event generator, which can also facilitate in creation of state and updating that state in pod lifecycle event generator. This is how pod lifecycle event generator facilitates in managing container runtime and pod lifecycle. In this video, we'll demonstrate how to use Cube Ctl commands to manage pods, scale out deployments, and customize the resource definition of the deployments. Let's go ahead and first see how do we manage pods. To manage pods, first you need to get information about existing pods. First, assume that you want to list the pods. To do that, you'll connect to master, you will launch command prompt, and at command prompt, you will write command that starts with kubectl followed by space, followed by get, followed by a space, and you'll specify pods. After writing the command, you'll press enter. Once you'll press enter, you'll find all the pods which are running in your current system. Now let's select one of the pods that we want to manage. To manage, you need to be aware about logs. To do that, we'll use kubectl followed by a space, followed by logs, followed by a space, and name of the pod. We are selecting nginx to view the log of the current pod. We'll press enter. Once you'll press enter, you will get details of the current pod that you have specified after logs. You need to look at the last entry, which indicates that it is ready for startup. Now let's go and try to attach the pod to a running container. In order to do that, we'll clear the screen, and at the prompt, we'll write the command kubectl followed by a space, followed by attach, followed by a space, followed by name of the pod, and we are using nginx pod, followed by a space and -i. After writing -i, we'll press enter. Once you'll press enter, it will attach your pod to a running container. Let's press Ctrl+C to come out of the process and use the command called kubectl followed by a space, followed by describe, followed by a space, followed by pod/nginx. And we'll also specify a space. After space, we'll write -n. We'll give a space and we'll write default. This will help us to see all the containers in the current pod. We'll press enter. Once we'll press enter, you'll find containers and their status. This is how you'll be able to manage pods. Now let's clear the screen and try to understand how do we scale a deployment. To scale a deployment, first we need to decide which deployment we want to scale. And to do that, we need to first know all the existing deployments in the current cluster. And we'll do that by writing Cube Ctl, followed by a space, followed by get, followed by a space, and we'll write deployments. After writing deployments, we'll press enter and you'll find the current deployment. Our current deployment is web-deployment. Now let's go ahead and see the replica set which is created by the current deployment. And to do that, we'll write kubectl followed by space, followed by get, followed by a space and rs to list all the replica sets. We'll press enter. Once we'll press enter, you'll find the replica sets where two important entries are desired and current. Desired displays the number of replicas of the application and current displays how many replicas are currently running. Let's have a look over the third entry of the current deployment. And third entry says 3 in desired and 3 in current, and all 3 are ready. Now let's go ahead and scale the deployment to 4 replicas. And to do that, we'll write kubectl followed by space, followed by scale, followed by space. We'll specify deployments / name of the deployment, which is web-deployment. After specifying deployment, we'll give a space and we'll write -- replicas. After specifying replicas, we'll use equal to and we'll specify 4. We'll press enter. Once you'll press enter, you'll get a message that indicates that it has been scaled up. Now let's go ahead and see the deployments. To see the deployments, we'll write kubectl followed by a space, followed by get, followed by space, followed by deployments, and we'll press enter. Now once you'll press enter, you'll find that your deployment has been scaled up and the changes were applied. Now we can go ahead and we can check if the number of pods also have changed. And to do that, we'll write command called kubectl followed by a space, followed by get, followed by a space, followed by pods, followed by space. We'll specify -o followed by space and void. We'll press enter. Once you'll press enter, you'll find that number of pods are also increased to 4 of your web-deployment. Last 4 entries of the current output indicates that. This is how you will be able to scale up your deployment. Let's clear the screen and try to customize the resource definition of deployment. And to do that, we need to create a custom resource deployment manifest or configuration file. We have already created one. Let's open it. To open it, we'll write vi followed by space, followed by name of the file. In our case, it is crd_sample.yml, and we'll press enter. It will launch the file where we have specified some entries in the manifest file. The first 2 lines defines what the API version is, and we are saying that we want to create a custom resource definition by using kind. Metadata field, which is the third line, helps us to define what the name of the resource is. Then comes spec, which contains group, that helps us to define what the group name will be. It also follows version, that helps us to define the version. We are giving a name to the version as v1, and we want this version to be our storage version. Next is the scope. We have specified scope to be namespaced. And finally, we have specified names where we have defined plural, singular, kind, as well as short names. This is a simple file that we need to create. After creating the file and making relevant entries, we'll save it by pressing escape followed by WQ. Now our file is saved. Let's clear the screen by writing clear. Our next objective is to create. In order to create custom resource definition, we'll be using command that starts with kubectl space followed by create. We'll give a space and we'll specify -f followed by space followed by name of the file, which is crd_sample.yml. We'll press enter. Once we'll press enter, we'll ignore the current warning and we'll go to the last line, which indicates that your custom resource definition file is created and it can be used. This is how we'll be able to use kubectl commands to manage pods, scale out and customize the resource definition of deployments. In this video, we'll recognize the scenarios of using the stateful workload API object, its components, and limitations that need to be considered when utilizing stateful set in deployments. Now we'll be taking up three critical scenarios. First is the cluster administration, second is namespace user, and third scenario is dynamic provisioner. Now the cluster administrator installs or uses any of these three different ways of managing stateful set workload. Now let's go through the configuration of each. Taking the first case, that is cluster administration, as it is displayed in the diagram currently present on the screen, we have to use kind to be storage class. API version should be storage.k8s.io/v1. Metadata will help us to give a name. You need to be careful when you are specifying provisioner, which is hpe.com/driver. We are using a provisioner in the current case. Parameters that we are specifying is option value. Second is when you specify a namespace. A namespace user will bind the object of storage class within a namespace. And that they will do by using kind:storage class, API version, which will be similar to the previous one, metadata, you'll specify a name to be my app, provisioner, you'll specify a provisioner along with the driver, that is hpe.com/driver, and parameter. You need to ensure that when you are creating this object, you are creating it within a particular namespace. Then comes dynamic provisioner that creates a storage class object as it is specified in the configuration. We have specified API version :v1, kind is persistent volume. Metadata helps us to give it a name followed by spec, which includes what all access modes are permitted. In the current, it is read write once. Capacity, that is storage, 500 gigabytes, followed by flex volume, driver, and options. And finally, after specifying all the details, we'll specify storage class name, which is my storage. You need to ensure that dynamic provisioner is bound to namespace user. So you start with creating the storage class, specifying the namespace, and finally binding it to dynamic provisioner. All these requests will be intercepted by API server present in Kubernetes, and it will create the objects. Now, what all are the possible access modes in Kubernetes? There are three. First, read write once. It is abbreviated as RWO. Use case of using read write once is specific cases when you need high performance stateful workload where PV can be mounted read write on one compute node at a time. Second is read write many, abbreviated as RWX. Use case of using read write many is that it is typically served to a container over network file system, that is NFS, and the PV can be mounted read write by not one compute node at a time, but in current case multiple compute nodes at the same time. And finally, we have read only many, abbreviated as ROX, which means it can be used in scenarios where you want read-only access for NFS exports, and the PV in the current case can be mounted read-only by multiple compute nodes. Now we'll try to understand stateful deployment using a scenario. In the current case, you will find various different objects. Let's try to interpret the diagram which is currently displayed on the screen. At the top, we are having MySQL, which contains configuration details. These configuration details are stored in config map. Using configuration details, you'll be able to create a stateful set, which we can see at the center of the diagram, indicated by MySQL, which is pointing to config map, which contains master and slave configuration. Internally, you will plan replication of MySQL by maintaining its state. And that you will do by using read-write -h MySQL -0 -MySQL. This will help you to communicate with MySQL using application or any CLI that supports MySQL. At the left-hand side, we have headless service that is consuming MySQL, and it does it by maintaining DNS record. Headless service communicates with MySQL using DNS record, and MySQL, which is stateful set, uses config map in order to get configuration detail. And finally, you have cluster IP service, which can be used by clients using app or CLI in order to communicate with MySQL. So by combination of headless service, cluster IP service, and stateful set along with config IP, we'll be able to utilize stateful deployments. Now we'll take final scenario, that is stateful set in multi-primary mode, which indicates that each node in the cluster will play the same role and the notation of primary secondary does not apply. It means all are primary. If all are primary, each node can process read-write request from user. Now let's try to understand using a diagram which is currently displayed on the screen. From the right-hand side, we can see we have two pods, which contains your app and dependencies along with router. They will place their request to router, and router will take responsibility of communicating with pods, which are part of stateful set, configured to run agents of MySQL in order to provide communication to service, which is router. In the current case, since you are using multi-primary mode, you are using only one global object storage. And to the same global object storage, you will have multiple different primary nodes with their pods communicating with object storage in order to provide the same data. And this is the reason why we will find that pods will follow group replication mechanism. Now, whenever a MySQL operator will send CRD request to Kubernetes API, it will communicate with stateful set, which is being used by headless service in order to facilitate consumption of service to MySQL operator. This is how you can utilize stateful set in multi-primary mode. So there are various different scenarios. You need to identify what all scenarios needs management of stateful data or the state, and accordingly derive the right approach of using stateful set. In this video, we'll use Cube Ctl commands to list stateful set and scale specific stateful set by increasing replicas. Stateful sets are intended to be used with stateful applications and distributed systems. Assume that we have created a stateful set, and name of the stateful set is nginx. Our first objective is to launch two terminals. After launching two terminals, in one terminal, we will watch the pods in the specific stateful set. And to do that, let's go ahead in the first terminal and write kubectl followed by a space, followed by get, followed by space, followed by pods, followed by space, followed by -w, followed by space, followed by -l, and followed by app equal to name of your stateful set. We'll specify nginx. We'll press enter. Once you'll press enter, you'll find that it is watching. Now we'll move to other terminal. After moving to other terminal, we will now use kubectl scale to scale the number of replicas. And we'll do that by writing kubectl followed by space, followed by scale, followed by a space, and we'll specify sts, which indicates that it's a stateful set. We'll specify name of the stateful set, which was web, as it was displayed in the first terminal when we used kubectl getPods command. We'll come back to the terminal. After writing web, we'll give a space, we'll write -- replicas equal to 4. After writing the command, we'll press enter. Once you'll press enter, you'll find a message indicating that stateful set.app/web has been scaled. Now let's go to the previous terminal. Press Ctrl C and re-execute the command once again. To re-execute the command, we'll write kubectl followed by space, followed by get, followed by space, and we'll write pods followed by space, followed by -w, followed by a space, followed by -l, followed by space, and app equal to nginx. We'll press enter. Once you'll press enter, it will take some time in order to list the scaled pods. You have to wait for some time to ensure that Scaleful Set controller has scaled the number of replicas. This is how you will be able to use Cube Ctl commands to list stateful set and scale specific stateful set by increasing replicas. In this video, we'll use kubectl commands to diagnose pods by listing the init container status of the pods, including all the running and if any unhealthy pods are there. Fundamental objective of init container is to ensure that you are able to execute scripts that are required for setup if they are not present in apps images. You can specify init containers in the pod specification. Let's go and see a simple example of manifest where we have specified init containers. To do that, we have created a file. We'll open the file by connecting to master and launching command prompt. After launching command prompt, we'll write vi followed by the file where we have defined init containers. In the current file, we have a simple pod. And this is the reason why in the second line, kind is specified as pod. It has two init containers which are specified at the end of the file. First init container's name is install and it installs busy box image along with the rest of the details. Second is work_dir which creates an empty directory. Now these containers which are configured in the file will run when your pod initialization will take place. Let's go ahead and save and exit. Now we have a pod definition with init containers. Now let's go and see the status of init containers. And that we'll be able to see by using a command that starts with kubectl, followed by a space, followed by get, followed by a space, we'll specify -f, followed by a space, followed by name of the file, which is initcontainer demo.yml. You need to ensure that you have used kubectl apply command in order to create the pod. After creating the pod, we'll be using get command as specified and press enter. Once you'll press enter, it will show you the current status, where it gives name, state, status, how many restarts, and what is the age. In case if you want more details to diagnose pods, you can do that by listing the init container status of pods, including all the running and unhealthy pods. We'll do that by using command that starts with kubectl, followed by space, followed by describe, followed by space, we'll specify -f, space, followed by name of the file. After specifying name of the file, we'll press enter. Once you'll press enter, you'll find that it displays the detail of every pod, where you'll find some of them are pulling, some of them are pulled, some of them are created, some of them have started. In certain cases, you will get status that indicates unhealthy as well if there are any. And finally, you can also use kubectl log command in order to see logs of the pods. But before that, let's go and get the pods. To do that, we'll write kubectl, followed by space, followed by get, followed by space, followed by pods, and we'll press enter. Once you'll press enter, you will get init sample as your pod. Let's go ahead and write kubectl, followed by a space, followed by logs, followed by a space, and we'll write init sample, followed by a space, and we'll press enter. Once you'll press enter, you will get details that you need to visualize and understand in case if any problems are there. This is how you will be able to diagnose pods by listing the init container status. In this video, we'll set up an autoscaler for deployment and specify the minimum and maximum number of pods based on the CPU utilization of existing pods. You need to ensure that you have a deployment and a service created. We have already created a deployment and a service. Let's go and see the deployment and the corresponding service. To do that, at the command prompt, we'll write kubectl, followed by a space, followed by get, space, followed by deployments. We'll press enter. We have a new deployment that is PHP-Apache. Now let's go ahead and see the corresponding service for the deployment. To do that, we'll write Cube Ctl followed by a space, followed by get, followed by a space, and we'll write services. We'll press enter. Once you'll press enter, you'll find a corresponding service as well, that is php-apache. Type of service is cluster IP and it has been allocated a cluster IP address. Now let's go ahead and set up autoscaler for the current deployment. Now we know that server is running. Once server is running, our objective is to create a pod autoscaler that maintains between 1 to 5 replicas of the pods. But yes, it will be controlled by your deployment, that is php-apache. In order to set up an autoscaler, we'll be using a command that starts with Cube Ctl. We'll give a space and we'll write autoscale. After writing autoscale, we'll give a space and we'll write deployment to ensure that we are able to specify that this autoscaler need to apply on a particular deployment. After writing deployment, we'll give name of the deployment. We'll give a space. Name of the deployment is php-apache. After naming the deployment, we'll give a space and we'll specify that in order to maintain an average CPU utilization across all pods, which is 40%, we'll specify that by using --CPU-% equal to 40. After specifying 40, we'll give a space and now we'll be specifying the minimum and maximum number of pods. To do that, we'll write --min equal to 1. We'll give a space, we'll again use --max equal to 5. We'll press enter. Once you'll press enter, you'll find that it will give a message that autoscaling is now set up. You can also go and check the status of autoscaler, and in order to do that, first we'll clear the screen. After clearing the screen, we'll write Cube Ctl followed by space, followed by get, followed by space, and we'll write HPA. We'll press enter. Once you'll press enter, it will show you the pod. It will also show you the reference of the deployment along with targets, that is unknown, but 40% is the scale, min pods and max pods. This is how you will be able to set up autoscaler for deployment and also specify minimum and maximum number of pods which are based on CPU utilization of existing pods. So in this course, we have examined how to perform key Kubernetes deployment tasks, which includes implementing and updating deployments, diagnosing and managing pods, rolling back updates and deployments, scale, stateful set, and set up autoscaler for deployments. We did so by exploring the key Kubernetes deployment strategies, the elements of the manifest file of the deployment strategies, the different states of deployment lifecycle along with the characteristics of each state. How to implement deployments with 3 replicated pods, update deployments and view deployments, rollout status and deployment update information. How to inspect rollouts as they occur, pause and resume rollout to rollback updates, check the revisions of deployments and rollback deployments from current version to previous version. How to list stateful set and scale specific stateful set by increasing replicas. How to diagnose pods by listing the init container status of pods. Set up an autoscaler for deployment and specify the minimum and maximum number of pods. In the next course, we will explore the role of config maps and secrets, the different approaches of using config maps and secrets in Kubernetes, learn to create config maps, use config maps to define environmental variables, create secrets and define container environment variable using data from secrets. In this video, we'll describe the role of config maps and the different approaches of using config maps and configuring containers inside pods. So let's try to describe fundamental features of config maps. Config maps' primary objective is to decouple environment-specific configuration from container images. Apart from that, we need to understand that config maps will not store confidential data. Rather, it stores non-confidential data. Data structure which is adopted by config maps is key value pair. It does not use any encryption, and it is not designed to hold large chunks of data. Now, what all are the different ways of using config map so that we are able to configure containers? First approach is to use config maps inside a container command and command line arguments. Second, we can go with read-only volume. It means we can add a file in read-only volume for the applications to read. Third approach is to use environmental variables for a container. And finally, we can write code to run inside the pod that uses Kubernetes APIs in order to read a config map. Now let's go ahead and discuss the way manifest file need to be written to define and create config map. And to do that, we will evaluate various different statements that are written in YAML file. First line is API version, which we have specified to v1. Kind is pod. Name is specified under metadata, and name that we are giving is pod-cmd-line-config. Then comes the most important part, which is spec. We'll specify containers. We'll give a name to the container that will be used in order to build environment for pod. We need to specify image. We have specified image to be busybox, and also command that need to be executed once container is instantiated. Then comes environmental variables. We'll specify env. Under env, we'll give name. Current name that we are giving is log_level. Now, this particular name of environmental variable must be populated with some value. And that value we will get using value from. And below value from, we have to give reference to config map. And that we are doing by using config map keyref. We are giving name of the config map that is present, which is log-config, followed by key, which is log.level defined in your config map. We can go ahead and utilize various other environmental variables as well. For example, second environmental variable is log_location. And for log_location, we are getting value from config map keyref, which is named as log-config. But key from where it will pull the value to populate it in log_location is log.location. Finally, you will have image pull policy, which is if not present, and restart policy is never. This is how you can write configuration file that creates a pod fetching value from config map and populating its environmental variables. Now let's try to understand how do we inject config maps into pods. And for that, we'll be using a diagram which is currently displayed on the screen. At the bottom, we have config files, C1 and C2. At the right-hand side of the bottom line, we have config maps, which is created using manifest file. That config map is being used by deployment and replica set, which is specified in the config files. Now our objective is to utilize injected config map from the pod. To do that, we have two different routes. First, we'll be using ingress that will invoke the service and it will pull the data stored in config map. Second, ingress will make call to ingress controller, which will send request to load balancer, and load balancer will pick up data from config file which is injected in configuration files. This is how you'll be able to inject config maps into pods. In this video, we'll use Cube Ctl command to create config map using commands and creating config maps from single as well as multiple files. Now, primary objective of config map is to ensure that you are able to decouple your configuration artifacts from the image. And that helps you to come up with portable containerized applications. Now let's go ahead and see how to create config map using a command. To do that, we need to launch our terminal, and at terminal, ensuring that Cube Ctl is installed, we'll write a command that starts with Cube Ctl, followed by a space, followed by create, followed by space, followed by config map. We'll give a space and we'll specify a name to our config map. We are using my-config. After writing name, we'll give a space and we'll specify dash dash from dash literal equal to key.sample1 equal to data1. Similarly, we can give space and we can specify dash dash from dash literal equal to key.sample2 equal to data2. So it depends how many config map variables, which is combination of key value pair, you want to create. After specifying all, we'll press enter. Once you'll press enter, you'll find that your config map is created. Now let's go ahead and see what is the content of the config map that we have created. To do that, we'll be writing command called Cube Ctl at the prompt. We'll give a space. We'll use describe. After describe, we'll give a space. We'll write config maps. After writing config maps, we'll give a space and we'll write my-config, which is name of the config maps that we have created in the previous step. After writing the command, we'll press enter. Once you will press enter, it will give you details of config maps. You need to directly move to data and see what all are the variables which are defined. You have key.sample1, for which value is data1, and you have key.sample2, for which value is data2. We'll clear the screen for now. Now our objective is to create config map using a single file, for which we have already created a properties file. Let's go and see the content of the properties file. To do that, we'll go to the directory where we have created the file. We'll write ls, which will list all the files which are there. After writing the command, we'll press enter. For now, we have a file called as sample.properties. We'll open the file by writing vi. We'll give a space sample.properties and we'll press enter. In the current file, we have specified two entries. First line is key.dns equal to web.com and second line is key.rul equal to http://ip.com. You can have any combination of key value pair that you intend to use in your Kubernetes cluster configured in config maps. We'll exit from the file by pressing escape key and writing :wq. Once you are out of the file, you have to use command in order to create config map using a particular file. Let's go ahead and start writing the command. It starts with Cube Ctl, followed by a space, followed by create, followed by a space. We'll specify config map. After specifying config map, we'll give a space and we'll write dash dash from dash file. After writing from dash file, we'll write equal to followed by name of the file. Name of the file is sample.properties. After specifying name of the file, we'll press enter. This error comes because we haven't specified name of the config map that we want to create. Let's go and write again by writing kubectl followed by a space, followed by create, followed by a space, followed by config map, followed by a space, and never forget to give a name to it. We'll write sample3, which will be name of the config map, followed by a space, dash dash from dash file equal to, and now we'll specify name of the file, which is sample.properties. After writing name of the file, we'll press enter. Once you'll press enter, you'll get message indicating that your config map is created. After creating the config map, we'll write kubectl followed by a space, followed by get, followed by a space, followed by config maps. We'll give a space, we'll specify name of the config maps that we have created, which is sample3, followed by a space, followed by dash o, followed by a space, and YAML, which specifies the format. We'll press enter. Once you'll press enter, you will get detail of config map that you have created in YAML format. Now let's go ahead and clear the screen. Now our final objective is to find out how do we create config maps from multiple files, for which we have created a directory called config map dir. We'll move to that directory by writing cd space config map dir. After writing the command, we'll press enter. And once we are there in that directory, we'll write ls. We'll press enter. Now we have two different properties files, sample1.properties and sample2.properties. We want to create config map using content of these two properties files. We need to use command that has capability of packaging each file into a single config map object. Let's move out of the directory by writing cd space ... We'll press enter. We'll write pwd in order to get the present working directory. After writing the command, we'll press enter. And finally, we'll start writing Cube Ctl followed by a space, followed by create. We'll give a space. After space, we'll write config map. After config map, we'll give it a name. We have given name as combined map. After giving it a name, we'll give a space and we'll specify --from -file equal to the path where your directory is. We'll specify /root /examples /name of the directory, which is config map dir followed by a /. After writing the command, we'll press enter. Once you'll press enter, you'll find that it has created combined map config maps, which contains key value pair from both the files. This is how you'll be able to create config map using kubectl command, create config map from a single file, and finally create config map from multiple files which are present in the same directory. In this video, we'll create config maps from generators and apply them to create config map object on the server. From version 1.14, Kubernetes came up with support for customization.yml file, where you can use it to create a config map from generators and then apply it to create the object on the API server. To do that, we need to first create properties file. We can see on the screen we have a configuration file with two different key value pairs, key1 equal to value1, key2 equal to value2. After creating the file, we'll save the file and we'll exit. To save and exit, we'll press escape key, followed by colon, followed by WQ. We'll press enter. Now, our next task is to create customization.yml file, and we'll refer to the properties file in order to create config map object on API server. In order to do that, let's first clear the screen. We have already created a file called customization.yml with relevant entries. Let's open the file. To open the file, we'll write vi followed by space, followed by name of the file, which is customization.yml. We'll press enter. Line number 1 is config map generator, followed by colon, and then we are specifying the name. Name we are specifying as sample-config-generator. And finally, using files element of the current YML file, we are specifying the path of the file, which is the properties file that contains our key value pair. After creating customization.yml file, we'll save and we'll exit. To save and exit, we'll press escape key, followed by colon, followed by WQ. We'll press enter. Now, our next objective is to be in the directory where we have created customization.yml file and create config map object. To create config map object, we'll be using Cube Ctl, followed by space, followed by apply, followed by space, followed by -k, followed by space, followed by dot. After writing the command, we'll press enter. Once we'll press enter, you'll find that it has created the config map on the server. Let's go and get the config map that it has created. To do that, we'll write Cube Ctl, followed by space, followed by get, space, followed by config map, and we'll press enter. Once you'll press enter, you'll find that it has created sample-config-generator-alphanumeric identifier. This is how you'll be able to create config maps from generators and then apply them to create objects on the API server. In this video, we'll define container environment variable using data from a single config map. Sometimes you would like to use container environmental variables using config map. Let's go ahead and define a container environmental variable with data by creating a single config map. In order to do that, we will write command at the command prompt that starts with kubectl followed by a space, followed by create, followed by a space, followed by config map, followed by a space. We'll give a name to our config map, that is env-sample. We'll give a space and we'll use -- from -literal because we want to create a single config map, and instead of using file, we are specifying using literal. Literal that we are using for environmental variable is key.sample1 equal to useme, where useme is the data. We'll press enter in order to create config map, which is bundled with environmental variable. Now our objective is to use the environmental variable. To use the environmental variable, we'll create a configuration file and we will map a value of configuration file to our environmental variable that we have created using config map. To do that, let's go ahead and open the file where we have used config map environmental variable. We'll open the file by writing vi followed by a space, config map env.yaml. We'll press enter. Once you'll press enter, you'll find a manifest file which creates a pod. First two lines specifies version and kind, which is pod. Then we have metadata to name. We are specifying name as sample-pod-env. And then we are using spec. Under spec, we have container. We have specified name, image, and command. We need to focus on env element of current YML file, where we are first defining the environmental variable. We are giving a name to it, and name that we are giving in the current context is key_from_config. Now we need to get the value from config map, for which we are using element called value from. Under value from, we are using config map key ref so that we can provide reference of config map object that we have created in step 1. To do that, we are using name : followed by env-sample, which is name of the config map object created in step 1. And then we have to identify that we want to associate key_from_config with what key present in config map. To do that, we are using key::key.sample1. And finally, restart policy : never, which will not have impact over configuration variable. We'll save the file by pressing escape key, typing :wq. Now you have your file ready. You need to create the pod using the configuration file that you have created. And to do that, you'll write kubectl followed by a space, followed by create, followed by space, followed by -f, followed by a space. You'll have to specify name of the configuration file where you are using config map object. After specifying name of the file, we'll press enter. Once you'll press enter, you'll find that pod is created. Finally, let's go and describe the pod. To do that, we'll write kubectl followed by a space, followed by describe, followed by a space, followed by pod, and we'll give a space and we'll specify the name of the pod, that is sample-pod-env. We'll press enter. Once you'll press enter, you'll find that pod is created. And in details, you'll find that under environment section, it specifies key_from_config, and it indicates that it's set to the value key.sample1 of the config map env-sample. This is how you will be able to define container environmental variable using data from a single config map. In this video, we'll create config maps containing multiple key value pairs and then define config maps data as container environment variables. Now let's go ahead and first define a file where we will create multiple different config map objects. To do that, we have created a file named c6maps.yml. After writing vi, giving a space and specifying the name of the file, you'll press enter. Now in the current file, we have created two config map objects. First two lines specifies that its API version is v1 and kind is config map. Then we are giving metadata in order to provide it an identifier by using name :env-config1. We are also specifying namespace, which is default. Then we are specifying key value pair under data. After completing configuration of first config map, we are giving triple dash so that we can specify more objects. After triple dash, we are again specifying API version :v1 kind :config map followed by metadata and data, which is log.level followed by warning. This is how you will be able to define multiple config map objects using a single manifest file. After writing the file, we'll save. To save, we'll press escape key followed by :wq. Now, after making declarations in your manifest file, you would like to create config map objects. To do that, we'll be writing Cube Ctl followed by a space, followed by create, followed by a space, followed by -f space, followed by name of the file, which is c6maps.yml. After entering the command, we'll press enter. Once you'll press enter, you'll find that it displays message indicating that it has created two config maps. And these are the config map objects which you will use in order to declare properties of your container by creating pod, for which we need to write a configuration file and provide reference to these config maps and environmental variables within that particular file. Let's go and open the file. Name of the file is v6pod.yml. After writing vi, giving a space and specifying the name of the file, you'll press enter. In the current file, we have specified API version :v1 and kind :pod. We have given metadata in order to give it a name. Then we are providing specification of container. Let's move to line number 10 where we are defining environmental variables. First environmental variable that we are creating for the container is env_key1. After defining the name of the environmental variable, we have to specify from where it should get value. And to do that, we are using value from :config map key ref : we are giving name of the config map and the key from where we want value to be allocated to containers env_key1. We are doing the same for the second environmental variable as well, that is env_key2. We are specifying value from config map key ref and we are giving reference of second config map which was created in step 1. We are also specifying the key. You need to ensure that key that you are specifying is correct. You'll save the file by pressing escape :wq and you'll press enter. And finally, you need to now create the pod using Cube Ctl followed by space, followed by create, followed by space, followed by -f, followed by space, and you specify name of the file, that is v6pod.yml. We'll press enter. Once you'll press enter, you'll find that it indicates that sample pod v6 is created. This is how you will be able to create config maps which contains multiple key value pair and then define config maps data as container environmental variables. In this video, we'll create configuration files to populate a specific path in a volume with data that are stored in config map. As seen in earlier labs, we have created config map using various different methods. Let's go ahead and create config map, which we will use in order to store data in a volume. To do that, we have written a file named config map for volume v7.yml file. We'll open the file. In the file, first two lines defines API version to be v1, kind to be config map. Then we are using metadata in order to give a name, that is config-for-volume. Namespace is default, and data that will be stored is level 1 : high, level 2 : low. Data is present in form of key value pair, where level 1 and level 2 are keys. After writing the file, we'll save and we'll exit, and that we will do by pressing escape : WQ. So now we have written the file where we are defining the data that we would like to add to our volume. Now let's go ahead and create the required config map. To do that, we'll write Cube Ctl, followed by a space, followed by create, followed by space, followed by -f, followed by a space, followed by name of the file. After specifying name of the file, we'll press enter. Once you'll press enter, you'll get a message that will indicate that config-for-volume is created. Now we would like to populate a volume using data which is stored in config-for-volume config map. And to do that, we will open the file which we have written in order to configure the volume so that it can use data present in current config map. Name of the file that we have created is config-volume v7.yml. We'll press enter. Now, first two lines are about what resource we are creating, and that we have specified using API version :v1 kind :pod. We have given metadata which specifies name of the pod, and then we are specifying specification by using spec : container : We'll directly move to volume section of the spec, where we are using the name called config-volume, and we are binding it to config map by specifying name of the config map which we have created in previous step. And that we have done by writing config map : name : and specifying name of the config map that we created in previous step, and that is config-for-volume. Finally, we are writing restart policy to be never. We'll save the file by pressing escape : WQ, and we'll come out of it. Now let's go ahead and create the resource called pod, which will use data present in config map in the current volume. To do that, we'll write Cube Ctl, followed by a space, followed by create, followed by a space, followed by -f, followed by a space, and followed by name of the file, which is config-volume v7.yml. We'll press enter. Once you'll press enter, you'll find that it has created the pod. This is how you'll be able to create configuration files to populate a specific path in a volume using data that is stored in config map. In this video, we'll recall the concept and different types of Kubernetes secrets along with the different approaches of using secrets in pods. Now let's first go ahead and describe what is Kubernetes secrets. Kubernetes secrets are used to store and manage sensitive information. These are the objects that contains a small amount of sensitive data. And fundamentally, secrets are needed in containers in order to invoke access to internal resources. Now, how to use secrets in pods? First approach is to use secrets as files in a volume that is mounted on containers. Second approach is we can use secrets as container environment variables. And third is by using kubelets when pulling images from pods. Now there are different types of secrets which are inbuilt in Kubernetes. Let's go ahead and discuss some of them. First is opaque. Usage is to store arbitrary user-defined data. Second built-in type is kubernetes.io/service-account-token. Usage. is to come up with service account token. Third is kubernetes.io/docker-cfg. Objective usage is to serialize it in docker cfg file. Then comes kubernetes.io/docker config.json. Usages, it is serialized to config.json file present in docker folder. Next built-in type is kubernetes.io/basic-auth. Usages to store credentials for basic authentication. Then comes second type of auth, which is kubernetes.io/ssh-auth. Objective is to store credentials for SSH authentication. Next is related to TLS, where Kubernetes provides built-in type called kubernetes.io/TLS, and it is used to manage data for TLS client or server. And finally, we have bootstrap.kubernetes.io/token. It stores Bootstrap token data. After exploring types, let's try to understand how do we create secrets in Kubernetes. And that we will do using a diagram which is currently displayed on the screen. At the left-hand side, we have developer who will send a create request to Kubernetes API, which in turn will store secret in etcd, which is present in your Kubernetes node. After storing, whenever there is a request made by developer, they will send the request, which will be now to consume the secret. They will send that request to Kubernetes API server, which is part of Kubernetes, as a result of which pod will consume the secret which is present in etcd store. This is how secrets are created in Kubernetes. All the commands to create secrets can be invoked using Cube Ctl. You can also configure specific manifest for your secret creations. In this video, we'll demonstrate how to create a secret config file and create secrets using the secret config file. In various scenarios, you would not like to store sensitive information in form of clear text. And there comes role of secrets. Secrets will provide you with a mechanism to use such information in a safe as well as in reliable way. And it does it by adopting certain properties like secrets are namespaced objects. In short, they exist in the context of namespace. You can access secrets using volume or an environmental variable from a container which is running in a pod. We need to also understand that secret data on nodes is always stored in TMP-FS volumes. Specifically, from perspective of size, you will have per secret size limit of 1 MB. So you need to decide what kind of data need to be stored in form of secrets. Now let's go ahead and create some sample secret in order to understand how to create a secret file and create secret object out of it. To do that, we need to ensure that first we are converting the data in form of base 64. For example, let's go ahead and create, for which we need to connect to Kubernetes cluster using console by writing command called echo followed by space, followed by -n, space, followed by a secret value. Let's give user1 within single quotes, followed by a space, a pipe, a space, and base 64. We'll press enter. Once you'll press enter, it will generate base 64 value for your user1. Similarly, we'll convert password as well. We'll write echo space -n space followed by p@SSWORD in single quotes. We'll give a space, we'll specify pipe, we'll give a space, and we'll write base 64. We'll press enter. So now we have generated base 64 values. You need to ensure that you are storing these values somewhere so that you can use it while you are configuring. Now let's go ahead and write secret config file, for which we'll write vi followed by space, followed by mysecret.yaml. After writing the command, we'll press enter. We'll write the content which starts with API version :v1. We'll be careful, we'll specify kind :secret, followed by a name that we have given as mysecret.
type of secret that we are creating is opaque, and then we are specifying our secret data, which we are doing by writing data colon, and under data colon we are specifying username colon, password colon, and we are copying the relevant data that we have generated in previous step in form of base 64. After writing the file, we'll save the file and we'll exit. To save and exit, we'll press escape followed by :wq. So now we have written our secret.yml file. Let's go ahead and create the secret object using the configuration file. To do that, we'll write Cube Ctl followed by space, followed by apply, followed by space, followed by -f, followed by space, and we'll give the name of the file where we have configured our secret object. We'll press enter. Once you'll press enter, you'll find that it displays a message indicating that your secret called my secret is created. Now let's go ahead and check the secret. To check the secret, we'll write Cube Ctl followed by space, followed by get, followed by space, followed by secret, followed by space, and name of the secret that is created. After writing name of the secret, we'll press enter. Once you'll press enter, it will show you details of the secret that you have created. If you want it in form of YML, you can just go write the same command that you have written earlier, give space, write -o, give a space, and write the format in which you want. We want it in YML format, so we have written YAML. We'll press enter. Once you'll press enter, it will show you detail of the current secret object in form of YML. This is how you will be able to create a secret config file and using the file create secrets. In this video, we'll demonstrate how to generate a secret by defining a secret generator in a customization.yml file. One of the approach to work with secret is to use secret generator. And to do that, you need to use customize template tool. Let's go ahead and create a customization.yml file that will help us to define secret generator, where we will provide certain literals in order to keep data that we want to secure. To do that, we'll launch our terminal and at prompt we'll write vi followed by space followed by customization.yml. We'll press enter. After we press enter, we need to write secret generator in the first line followed by name colon. We have specified web-user-cred. Now there are two ways. You can specify files and you can give the path of the file from where your secret generator will pick up the data and generate secrets. For now, we'll be using literals. So we are using literals colon followed by data. In the current file, we are defining username equal to author and password equal to p@ssword. After specifying the literals, we will save the file. To save the file, we'll press escape followed by WQ. So now we are ready with our customization.yml, which will use secret generator in order to generate secret. Now let's go ahead and create the secret, and that we will do by writing Cube Ctl followed by space followed by apply. We'll give a space and we'll write -k, which indicates that it has to use customization.yml file followed by space. Since our customization.yml file is in current directory, we'll write dot. After writing dot, we'll press enter. Now, since you are able to see the error where it indicates that it is unable to find the file because you have written k in caps, let's go and rename it. To rename it, we'll write mv followed by customization.yml followed by the new name that you want. So we need to ensure that all are in small letters. We'll write customization.yml and we'll press enter. Now let's go ahead and execute the command, which starts with Cube Ctl followed by space followed by apply followed by space followed by -k followed by space and dot, because we want it to locate for customization.yml in current directory. We'll press enter. Once we'll press enter, you'll find that it has created the secret. Now that when a secret is generated, the secret name is internally created by hashing the secret data and appending
the hash value to the name. Now let's go ahead and check the secret that we have created. To do that, we'll write Cube Ctl followed by space, followed by get, followed by space, followed by secrets, and we'll press enter. You'll find all the secrets that are created. We have created web-user-cred, which is displayed as the last secret that was created. This is how we'll be able to generate a secret by defining a secret generator in a customization.yml file. In this video, we'll create a configuration file and use the kubectl apply command to create a pod and provide access to the secret data through a volume. One of the ways of using secret is to mount it as a data volume, or you can also expose it as environmental variables, which can be used later by container in the pod. Apart from that, secrets can also be used by other parts of systems without being directly exposed to the pod. Now, how do we do that? Now, let's try to understand approach of consuming a secret in a volume in a particular pod. To do that, let's go ahead and first explore what all secrets are there which are already created in our system. To get all the secrets, we'll write kubectl followed by space, followed by get, followed by space, and we'll write secrets. And we'll press enter. Once you'll press enter, you will get all the secrets which are currently present. Now, assume that we want to consume my secret in volume in a particular pod. To do that, we need to make some changes in pod configuration file. Let's go ahead and open the file. To do that, we'll write vi followed by space, followed by name of the file where we have configuration. Now, in the current file, we have specified first two line as API version :v1 kind :pod because we are going to create a pod. We have specified metadata to specify name. Name is pod sample for secret. And then we are specifying spec, which contains containers. We are giving a name to the container, my container. We are specifying image to be MySQL. And then we are using volume mounts. We are giving a name to the volume mounts, that is data. We are specifying mount path, which in current case is /etc/data. We are making the mount as read-only by specifying read-only to true. And finally, we are using volumes, where we are specifying name of the volume, that is data, and we are associating it with secret by using secret : and just below secret : we are using secret name : we are specifying name of the secret. This is how you will be able to configure your pod so that it can use secret as a volume. We'll save the file by pressing escape :wq. And once we are there out of the file, we need to create the pod which consumes a secret in a volume in the pod. And to do that, we'll be writing kubectl followed by space, followed by apply, followed by space, followed by -f, followed by space, and we'll give name of the file which contains configuration where we are consuming secret in the volume of a particular pod. After specifying name of the file, we'll press enter. Now, once you'll press enter, you'll find that pod is created and the current pod will be using secret in a volume. This is how you will be able to create a configuration file and use kubectl apply command that creates a pod and provides access to the secret data through a volume. In this video, we'll define container environmental variables with data from secrets and configure all key value pair in a secret as containers environmental variables. We can use secrets as environmental variables as well, for which we need to either create a new secret. You can also use an existing secret. Let's go ahead and see what all secrets are there currently created in our cluster. To do that, we'll write kubectl followed by space, followed by get, followed by space, and secrets. We'll press enter. Once you'll press enter, you'll find all the secrets that are currently created. Let's go ahead and use my secret object. To use mySecret object, you have to modify your pod's definition in each container that you wish to consume the value of a secret key. To do that, you need to also add an environmental variable for each secret key that you wish to consume. Let's go ahead and open the file where we have used secrets as an environmental variable. To do that, we'll write vi followed by space followed by pods using secrets v11.yml file. We'll press enter. First two lines indicates that we are creating pod of API version v1. We have also given name to the pod under metadata. Name of the pod that we are creating is pod-using-secret. After specifying name, we are specifying spec, where we are writing containers, colon. We are adding properties of containers using name colon db container, image colon MySQL. We are also specifying environmental variable in order to ensure that we are able to use secret. First environmental variable that we are using is specified using name colon secret underscore username. In order to get value from a secret, we are using value from colon. Below value from colon, we are using secret key ref colon. And then we are specifying name of the secret object by using name colon mySecret. Within mySecret, we have a key called username that stores username value. After specifying secret underscore username environmental variable, we are adding another environmental variable called secret underscore password. We are again specifying value from colon secret key ref. You can take value from other secret keys as well. For now, we are using the same secret, that is mySecret, specified using name colon mySecret, and key is password, that is specified using key colon password. After creating the file, we'll save the file by pressing escape colon WQ. Now we are ready. We have already created and configured our pod to use secret that we have created earlier. Now let's go ahead and execute the file. To do that, at the command prompt, we'll write Cube Ctl followed by space, followed by apply, followed by space. We'll use -f followed by space and we'll specify name of the file. In our case, it is pods using secrets v11.yml. We'll press enter. Once you'll press enter, it will show that it has created the pod using secret. You can go and you can describe the pod. To describe the pod, you will write Cube Ctl followed by space, followed by describe, followed by space, followed by pod, followed by space, and you'll specify name of the pod, that is pod-using-secret. After writing the command, you'll press enter. Once you'll press enter, it will show you current state of the pod. You can scroll up in the information and go to environment section where you'll find secret username and secret password, and you will find a message that indicates that it is bound and set to the key username in secret mySecret, as well as in the secret underscore password it has specified it is set to the key password in secret mySecret. This is how you will be able to define container environment variable with data from multiple secrets and then configure all key value pair in the secrets as container environmental variables. In this video, we'll create an image pool secret and add image pool secret to the service account. Now let's go ahead and first create a secret. In order to create a secret, you need to be aware about your registry FQDN. You need to be aware about username, password, and other details depending on what that registry requires in order to authenticate and authorize you. We are going to use our Docker registry. And to do that, we need to first ensure that we are able to successfully log in to our Docker registry. To do that, we'll connect to our Kubernetes cluster and we'll write Docker followed by space login. We'll press enter. Once you press enter, if it is first time login, it will ask you your username and password. If it is post that, it will use your previous credentials and it will tell you whether login is succeeded or not. As we can see the last message which indicates login succeeded, it means we are able to reach to our registry from the current system. We'll clear the screen by writing clear. Now our next objective is to create a secret. To do that, we'll write Cube Ctl followed by space create followed by space secret followed by space, and we'll give a name. We'll write docker dash registry. We'll give a space. After specifying docker registry, we'll give a name to the secret, which is reg secret. After specifying name to our secret, which is for docker registry, we'll specify space dash dash docker dash server. We'll use equal to, and we'll specify the endpoint of the Docker server. Endpoint of the Docker server is https://index.docker.io/v1/. This is what is endpoint for your Docker Hub. After specifying the endpoint, we'll give a space and write dash dash docker dash username. We'll use equal to. We'll specify the username. After specifying the username, we need to also specify space followed by dash dash docker dash password. We'll use equal to. We'll specify the password. After specifying password, we'll give a space and we'll write dash dash docker dash email equal to your email ID. So now we have specified the required details in order to set Docker credentials in the cluster as a secret object, and name of the secret object is reg secret. We'll press enter. Now you'll find that your secret is created. Now after it is created, we can also verify whether it's created or not. Now let's go and verify that it has been created successfully. To do that, we'll write Cube Ctl followed by space followed by get followed by space secrets. We'll give a space followed by name of the secrets. We'll press enter. Once you'll press enter, it will show you name, type, data, and age. Now we need to add image pull secret to service account. We'll add pull secret to service account by using a command that starts with kubectl space patch space service account space default, because we want to add it to default service account, followed by space dash p. We'll give a space followed by single quotes, and within single quotes we have to specify curly braces image pull secrets. We need to ensure that we are writing these strings in double quotes. So image pull secrets will also be present in double quotes, followed by colon, followed by space square bracket, followed by within curly braces we need to write combination of key and value. Key is name. We'll specify name. We need to ensure that values are in double quotes, followed by colon, followed by name of the secret. Name of the secret that we have created is reg secret. After specifying name and ensuring that double quotes, curly braces, square brackets all are in sync, we'll press enter. Once we'll press enter, you'll find that service account default is patched. This is how you'll be able to create an image pull secret and add image pull secret to the service account. So in this course, we have examined the role of config maps and secrets, the different approaches of using config maps and secrets in Kubernetes, how to create config maps, use config maps to define environment variables, create secrets, and define container environment variables using data from secrets. We did so by exploring how to create config maps from files and generators and create config map containing multiple key value pairs. How to create secrets using a secret config file, generate a secret by defining a secret generator, create a pod and provide access to the secret data through a volume. How to define container environment variables with data from multiple secrets and configure all key value pairs in a secret as container environment variables. how to define container environment variable using data from a single config map, how to create an image pull secret and add image pull secret to the service account. In the next course, we will explore the resource types and resource units that's used in Kubernetes. Learn to create and scale deployment and stateful sets, create and manage jobs, check downtime resistance, and install Helm and service catalog in Kubernetes cluster.